Hello, everyone. I'm very, very excited to welcome you to Sofia for Real World Crypto 2025. I hope you've already seen some of the city and you'll be enjoying more of it. But let me start by saying that as of 7:30 this morning, we are welcoming 657 attendees, and I think by now there are more. But this officially makes it the most attended Real World Crypto up to now. So I'm very excited about that. And also, these 657 people are coming from 47 different countries, which is something also very impressive for me. And another curious fact is that 228 of these registered participants are new to the IACR, which is the Association of Cryptography. So welcome everyone who is new to our community, and I hope this will be only your first IACR conference and many more to come. So first, the order of business is to tell you that IACR has a code of conduct. The IACR is committed to providing an experience free of harassment and discrimination in its events, respecting the dignity of every participant. Please follow the IACR code of conduct. And if for some reason you feel that you have been discriminated or harassed, please contact either me, Mariana Rajkova, or Douglas Stebela, who is another representative of the steering committee. You can also send an email to Tao Rabin, who is the IACR Code of Conduct liaison, or you can contact the IACR president, Michelle Abdallah, who is also here in person. All right, so what is ahead of us in the following 3 days? We will have a packed program. We will have 43 contributed talks. And another curious fact here is that 27 of the speakers will be new speakers to Real World Crypto. So it seems like we have a lot of new faces and a lot of exciting interactions. We will have also 4 invited talks by Adi Shamir, Yael Kalai, Joshua, and Silvio Petriconi, which will cover a wide range of topics, and I'm looking forward to all of them. Also new this year, we will have live streaming of all the talks and presentations in the conference. So if you have friends or if you know anyone who was not able to come to Sofia, but is still interested to follow the conference live, there are links in the program, and there will be live streaming for all 3 days of the program. So this great program was brought to us thanks to the amazing program committee with program chairs Martin Albrecht and Nick Sullivan. So let's give them a round of applause and thank them for all of their work. Apart from the interesting talks, we will also have the Levchin Prize award ceremony. We give awards that recognize people who have contributed significantly to the field of practical cryptography. And this will be today at 11:05. Hopefully, we will make up for the time that we were delayed with the opening. Also on Friday, we will have the lightning talks that are run by Nigel right here. This is an informal session where everybody who has some announcement can make the announcement. You have at most 2 minutes or whatever Nigel decides. And the format of this session is that everybody will be lining up here next to the stage, and Nigel will be calling you, and you'll come and tell your announcement. Okay, so about the venue. This venue is the National Palace of Culture, which is a venue that hosts a lot of concerts and performances. We are one of many halls in this building. So there are maps of the 2 floors where we are, the 6th and the 7th floor. So refer to these maps in the hallways or ask any of our staff, and they'll be happy to help you. So first, we have here the plenary hall where all the talks will be. All the food for breakfast and lunch will be in the food court, which is right in front of the doors, and also 1 floor below. This will be breakfast, lunch, and the reception, which will be today at 5 p.m. right after the end of the talks. We will also have places where we have electric outlets, which I assume many of you would want to use. So one of these spots is here on my right-hand side, where you see tables and chairs. And then on the floor below, we have a number of break rooms where you can go and like have meetings or use the power outlets. It's a big building, so follow the signs. You have to walk quite a bit to reach these break rooms, but there are signs on the way, and our staff will be happy to help you as well. We also have a lactation room. If anybody needs, please contact me directly for that. If you are a speaker, please be 15 minutes before your presentation in the speaker ready spot, which is here on the my left-hand side, where the technical people are just across the stairs. The default is the mic on here that you see I'm talking at. If you want a headset, you have to ask explicitly for it, and they will provide it to you. Also, if you get a headset, please return it to the technical staff. Please wear your badge. I know now, because we had a huge flood of people that was lining up at the reception, at the registration, some people came in before taking their badge. Please go back and pick up your badge. We will start screening, the security people will start screening for the badges at the entrance. All right, so of course, we need to thank our sponsors, which are very important for the conference. Let's have a round of applause for also our sponsors. Why do we want to thank the sponsors? Is because thanks to the sponsors, we were able to give 100 student stipends, which enabled a lot of students to come and enjoy this conference, which most likely would not have been able to do so. And they come from 47 different institutions. And apart from the student stipends, thanks to our sponsors, we have registration fee that is considerably lower than most other computer science conferences. So finally, I think it's also a rare event that all of the RWC steering committee members are here in person. So if you have any questions to us, please feel free to meet us in the hallways and talk to us. And on behalf of the whole Real World Crypto Steering Committee, I wish you an enjoyable conference. And now, since one of the main reasons that we are here in Sofia is because I found awesome partners in the new Institute of Computer Science, which has been established in Sofia. I will give the floor to Martin, who is running the institute, to tell you a couple of words about this institute. Thank you very much.
All right, so good morning, everybody. Welcome to Sofia. I hope you're enjoying the city. So I wanted to tell you a little bit about INSAIT. It's what I think is one of the most exciting initiatives in the world today in computer science research. So the problem statement we are trying to address here is, can you create a world-class research organization in computer science, in AI and computer science broadly, in Eastern Europe, and specifically in Sofia here in Bulgaria. And so that's what we're trying to do. And that's what we've been doing, I think, successfully over the last 3 years. So INSAIT was started in April 11, 2022. And so just to give you an idea, what happened over the last 3 years, so the government put some initial endowment of about, well, depending on the current rates of the dollar, about $100 million now, and some substantial funding from donations and support from big tech. By now, some of these numbers have actually doubled and tripled. So INSAIT was created in partnership with ETH Zurich and EPFL, and via a ratified agreement with the Bulgarian parliament, the Bulgarian government in 2022. And over the last 3 years, it has built up into a world-class research organization in various areas in AI, computer vision, robotics, AI safety, security, foundational models, quantum research, and I'll tell you a little bit what we're trying to do in security now. Okay, so I think the answer to this question, whether world-class research organization can be built in Eastern Europe for the first time, is actually yes, and it's happening historically here in Sofia. Okay. INSAIT, the way it's structured, it has a scientific director, myself, professor at ETH Zurich, and also the scientific director at INSAIT and executive director, as well as a governing supervisory advisory boards from various world-renowned scientists from the US, Switzerland, Israel, Austria, helping us build this super exciting project here in Sofia. INSAIT really has very basic principles. It aims to attract world-class faculty from around the world. So some of the people who joined INSAIT, helping us build it up, is one of the most renowned scientists in computer vision and robotics, Luc Van Gogh, who joined INSAIT right from the beginning, building up computer vision and robotics here in Sofia into what is now a world-class research organization in that area. And most recently, Baran Heupler from previously a faculty at Carnegie Mellon, then ETH, joined us in building up theory A, algorithms, complex theory here at INSAIT. So INSAIT actually goes beyond AI and into many other areas, just like any world-class computer science department would do. So just so that you don't get the impression that it's purely about AI, no, it's other things. So recently, Bob Tarjan spent some time at INSAIT. He's set to spend a lot more time this year. And some results that recently came out of INSAIT and collaborators from ETH and Princeton on the universality of Dijkstra. Again, researchers from INSAIT, postdocs, PhDs are involved in this very exciting result. Okay, so this is just some very high level. I don't want to take too much of your time. So if you're looking for world-class research organization in the region that provides amazing resources, similar in absolute terms to what you would find at ETH or EPFL, then INSAIT is that place. Just so that we connect it more to the theme of the conference and why am I presenting it here. The next vertical we are building up at INSAIT is security, cybersecurity, and all aspects of that. So cryptography, software security, hardware security, formal verification, protocol verification. So all these exciting areas. So I'm happy to say that Professor David Bazin from ETH will be joining INSAIT and helping us build up security to the world-class level, that has happened with the other areas at INSAIT. So if you're interested, definitely come by. I'm here in the morning and also later. Say hi. Happy to chat. If you want to visit INSAIT, we can arrange just to meet everybody. So faculty, postdocs, research scientists, PhDs, we're hiring at all levels. If you have general questions, you can just write an email. So thank you very much, and I hope you have a great conference.
All right, good morning. We'll now begin the first session of the conference, which will be on secure messaging. So we'll get the slides pulled up and then we'll get started. Oh, great. All right, so our first speaker. And before we get started, I'll remind our next speakers to please make sure you're going to the speaker ready spot over on that side of the room. Our first speaker in this session is Teofil Valles, and he'll be speaking about formally analyzing a cryptographic protocol standard.
Thank you for the introduction. So today I will talk to you about what I've done during my PhD, whose goal is to become a cryptographic protocol analyst by producing a machine-checked proof of MLS, which is a secret group messaging protocol standardized as IETF. And as the adage says, the journey is more important than the destination. And throughout this journey, I found flaws in MLS and helped the working group to fix them before its standardization. I identified and filled gaps in formal security proofs. That is, they don't deal properly with meshing formats. And I improved the tools to be able to conduct such an analysis by improving the tool called DWASTAR. And during this talk, I will share with you the lessons I've learned throughout this journey, both for protocol analysts and for protocol data designers, that is, how to best cooperate. So before diving into the heart of the talk, let's talk about how do we analyze a cryptographic protocol. The most traditional tool we have is to produce a pen and paper proof that the protocol is secure. So this is effective, but it requires expert humans to check that the proof is correct. And so to solve this problem, we can produce a machine-checked computational proof. So now a computer is checking the proof, but it is very hard to convince a computer. So this comes with limited automation, and it is difficult to analyze large protocols. And so to solve this problem, we can use machine-checked symbolic proofs. It has good automation with the trade-off that the symbolic model is less precise than the computational model, but still, symbolic proofs had many successes during the last decade. Hence, we choose this method to analyze MLS. To be more precise, our approach we develop to analyze MLS is that we take the MLS specification written in English in prose and translate it into a precise mathematical specification in the F-star proof assistant. And then we use DWASTAR, a symbolic analysis framework, to do security proofs. But how can we be sure we did no mistakes during the translation? To increase our confidence that the translation is correct, we use HackerStar on our specification. We obtain a bit-precise executable implementation that we use to run interoperability tests. And the result is that we increase our confidence that our specification correctly implements MLS, hence that our security proofs actually deal with MLS and not some subtle variant of it. So now that I gave some overview of our methodology, let's talk about the analysis itself. In short, what we have done is that we took the MLS protocol written in 120 pages of English. We showed how to modularize it into 3 subprotocols, which we called TreeSync, TreeChem, and TreeDem. We found various design flaws and helped the working group to fix them. And we proved security theorems about TreeSync and TreeChem in the symbolic model, and TreeDem is still future work. So, So in our modularization, TreeSync is in charge of group evolution. That is, throughout the lifetime of a messaging group, participants can leave and join a group, and TreeSync deals with that and maintains an authenticated state, which internally is a tree that apparently goes upside down, and gives this state to TreeChem. TreeChem is in charge of updating keys and rotating them, which provides to MLS strong confidentiality guarantees, such as post-compromise security and forward secrecy. And TreeChem gives these epoch keys to TreeDem, which is finally in charge of sending and receiving messages. This modularization was crucial for us because it allows us to analyze the protocol modularly, and analyzing MLS as a single monolith would have been too difficult. And at the beginning, it was not possible to modularize TreeSync and TreeChem like this. Indeed, the guarantees offered by TreeSync were too weak, and it was difficult to analyze it standalone. So we discussed with the working group and ended up doing about 30 lines change in the specification that strengthened the guarantees of TreeSync and allowed us to analyze it as a single interesting protocol. So this leads me to my first lesson for protocol designers: modularize your protocols. Of course, it's easier said than done. So I encourage you to chat early with a protocol analyst in the design process, see how they would modularize your protocol, and what you can do to improve the abstraction boundaries. So this will make the life of analysts easier. As a bonus, I think your protocol will be easier to understand because I think readers want to have some kind of mental model on why the protocol is secure. And it will also help implementers by showing them how to implement your protocol modularly. We started by proving security theorem for tracing. We prove an agreement theorem, that is, members agree on the group state, which in particular covers group membership agreement. Everyone agree on who is in the group, which is important because you want to make sure that an attacker cannot be in your messaging group without your knowledge. And our proof relies on minimal assumptions on TRICM and TRIDEM. However, at the beginning, these assumptions were not true. So this could be used as a first step to create an attack on MLS. The problem here is that in tracing, we have a signature, and signatures don't operate on high-level types, they operate on bytes. So we need to serialize the signature input to bytes. And TRIDEM also relies on signature with a different high-level types for signature input. The problem here is that tracing and TRIDEM rely on the same signature key, but use different type for their signature input, hence different serialization functions. And so what may happen is that a signature input in TRIDEM and in tracing have the same serialization, meaning that even though it's different types, they have the same bytes representation. And in that case, we can use a signature in TRIDEM to forge a signature in tracing. So we notify the working group, propose the fix that was accepted, and now this attack is not possible. So that's good. So this signature ambiguity raised two questions. The first one, from the protocol designer perspective, how did this attack survive so long? It's a well-known problem in the cryptographic community known as lack of domain separation. And so I think the problem here is that there is no rigorous definition for what is domain separation. As far as I know, it means frequent tags in serializations to avoid problems. And also domain separation is hard to enforce in large standard because here the signatures are pages apart in the specification, and you cannot really skim through the document to find the problem. And second, from a protocol analysis perspective, each time we find an attack on a protocol that was analyzed, we have to ask the question, why was this attack missed? To answer this question, we must first say, what does it mean to prove that MLS is secure? So what is a security proof? We translate the MLS specification written in English into a mathematical model. Then we prove security properties on this mathematical model. And so there are three places where we can miss the attack. Either the security properties don't catch this attack, either there is a problem in the security proof, or maybe the mathematical model is imprecise, meaning that it is secure against this attack, but the actual protocol is vulnerable. And that is what happened. In mathematical models of MLS, we find that there is no message formatting, there is no serialization. Signatures operate directly on tuples, hence they miss this message formatting attack. So this leads me to my lesson for protocol designers, analysts. Reason on precise mathematical models, it will allow you to catch subtle attacks such as message formatting attacks. And as a bonus, in our case, it also allows us to provide a reference implementation. So I think it's not breaking news. People already know that we don't deal with message formatting in security proofs because it's boring and it would make proofs more complex. And as a fun fact, I once had an analyst that told me, yeah, each time I do a reduction, I do realize that the encoding of these tuples must be important, but I really, really want someone else to think about it. So thankfully, I am someone else, and I did think about it. And I propose a solution in 3 steps. First, we define a rigorous definition of what is a secure format, then such that secure formats can soundly be abstracted away in analysis, and we make a tool to check whether these formats are secure. So we do a little bit of detour through security critical formats for cryptographic protocols, and we'll go back to MLS later. So although our example is on signature, the problem is everywhere in cryptography. Every cryptographic function takes as input bytes, and the cryptographic assumptions we have are when we use them with bytes. However, the security properties actually used are when we use them with high-level protocol data. And we see there is a gap here, which is filled by the study of format properties. So in our paper, we propose definitions of security properties for message formats, and for several cryptographic functions, define what is good domain separation. And for signatures, we define good domain separation as the formats used with signatures must be injective, that is parsable. Otherwise, if M1 and M2 have the same serialization, you can use a signature on M1 to forge a signature on M2. And furthermore, for each signature key, we must decide on only one format to use that must not depend on external context, because otherwise we have a problem as we had in MLS. You can take a signature done with one format to forge a signature done with another format. And this, if your signature key will be used in future versions and extensions of your protocol, you must make sure that this property stays true, and you must design your format in a forward compatible way. And the next thing about this condition is that it is sufficient and necessary. It is sufficient because if your format obeys this property, you can reduce the security properties you want to use on high-level types to the security properties, the security assumptions you actually can make on bytes. And it is necessary because if you don't obey this condition, there is clearly something fishy going on, and maybe you have problems, or your security proof will be very hard to make considering these issues. And so we may ask, is it difficult to create a format with these properties? And I claim that in real-world protocols, when some data is sent on the network, it will obey this good domain separation property because it must be passed. And as an example, if you look at the TLS13 handshake message, it's a tagged union, and the tag is designed in a way that it can evolve throughout different versions of TLS. So this handshake type here exists since 1996. So I claim that the TLS13 handshake message is well domain separated since I was born. So we have all the engineering and process and best practices to design such message formats. And I think we should apply it for formats of cryptographic functions. And actually, when we design a message format for a cryptographic function, such as a hash, there is little care given to it. For example, the transcript hash is defined as, well, let's concatenate every message and it will be fine. Actually, are we even sure that we don't introduce a collision before even hashing? So here, actually, it's fine because every message has internal length tag, but still, if this list of messages had to be parsed, you would never define it like this. So this leads me to my lesson for protocol designers. Please love all message formats equally, whether it has to be parsed or if it's an input for cryptographic functions. If you do that, you will rule out a whole class of attacks, that is message formatting attacks, but also cross-protocol attacks, at least some kind of protocol attacks. And you will tremendously help protocol analysts that are willing to model message format properly. We now go back on MLS with our analysis of TRIChem. So we proved a confidentiality theorem on TRIChem. And the main challenges here are that TRIChem relies on recursive data types, that is trees. So the proof must be inductive. And TRIChem relies on an unbounded sequence of key derivations, unbounded sequence of public key encryptions, all of this within a tree. And so I think that it's currently out of scope for automatic symbolic provers. And TWASTOR is really a tool of choice because it was designed initially with these challenges in mind. So initially, Diwastar was not able to prove TRICAM, and we had to heavily improve it and manage to do our proof, which means that in addition to have a security proof for TRICAM, we also have, as a byproduct, developed a tool that is capable of proving such a protocol. And so this leads to a lesson for protocol analysts. New to protocols may require new tools. And I can't think we can have one tool to rule them all. I think we always will have different tools. And I think it's fine because pen and paper people also have different tools. And today, Diwastar is a good tool for TRICAM-like protocols. And maybe tomorrow, we will have a new protocol that is out of reach of every method we know to produce a machine-checked analysis. And we will have to design a new one. And I think it's fine. So to conclude, I made a good step towards the destination of my PhD by proving two subprotocols of MLS. And during this journey, I developed a methodology to reason on precise mathematical models of cryptographic standards. I showed the importance of message formatting in cryptographic protocols and proposed a rigorous definition for domain separation. And finally, I heavily improved a tool to produce such analysis, and which means that now we can use it for other analysis. So I thank you for listening, and I am ready to take questions.
All right, we have microphones, I think, on all aisles of the room. So please feel free to come up to the microphone if you have a question.
There is an alternative to proving the full correctness of a protocol, which is less ambitious, but might be more widely applicable. And this is to try to compile a list of all the known types of attacks, like the domain separation problem you mentioned. So assuming that you have this very long list of known attacks, do you think that it will be easier to automate the process of showing a full checklist that the new protocol is not susceptible to any of those? We are doing it, for example, in cryptanalysis, where we know about differential cryptanalysis, linear cryptanalysis. We have a list of things, and every new crypto system is shown not to be susceptible. So how about doing this less ambitious, but potentially more applicable, kind of just a checklist that the new protocol is not vulnerable to any of the known attacks?
Yeah, so thank you for the question. So I think the different criterion we designed for different cryptographic functions are easy enough to check. So the methodology, so I didn't really dive into it, but I think is like in a protocol, let's gather every signatures performed in the protocol. And so each time I have a signature key, check the format and see if it obeys the property. And you can do the same for other functions like AEID, MAC, KDF. It's also similar criterions. And I think just needs to actually make the effort to gather of this usage and check the message format.
Thanks.
Yeah, thanks for the talk. So I'm interested in the problem of taking a pile of natural language in, say, an IETF spec and sort of translating that into the model. If you can do one thing to improve the IETF spec, what could people developing IETF specs do better in your opinion?
Well, I don't have a good answer for that. My process to create the specification was to struggle reading through the document while at the same time learning cryptography. So it may not be a good example. Yeah, I don't know. We'll need more time to think about this.
Good.
I'm afraid we need to move on. So please join me in thanking the speaker for the talk. Right. The next talk in this session will be about mesh messaging for large-scale protests, and our speaker will be Tushar Joa.
All right. Good morning, everyone. My name is Tushar Joyce. I'm an assistant professor at the City College of New York and a cryptographer in denial. And I'm here to tell you all about our work on mesh messaging for large-scale protests and why cryptography alone won't save us. So, large-scale protests are increasingly being the ways that everyday citizens can express grievances with their government. For example, in Hong Kong, in Iran, and currently ongoing in neighboring Turkey. And in these scenarios, communication is key to an effective and safe protest. And if I want to communicate with someone, what's going to happen is I'm going to have some kind of cell tower, I'm going to use a messaging app, and send that message to someone else. Now, in an authoritarian regime, of course, the infrastructure can be controlled, right? The centralized infrastructure is owned by someone else, and they can do things like intercept any communication they want, maybe like a Stingray or cell site simulator, or simply by tapping into the cell tower. Now, at the extreme, you may consider that an authoritarian regime will just prevent any communication, straight up shut down the internet, so no one can talk to anyone. So how can we bypass this need for centralized infrastructure? Enter smartphone mesh messaging. Now, this is a pretty simple setup, right? Smartphones are pretty ubiquitous. Urban protests are dense. Send messages from smartphone to smartphone. If I want to talk to someone on the other side of the city, I just bounce it along a path of smartphones, which is pretty intuitive. Now, of course, the authoritarian regime can still monitor this network, but there's no single point of failure in a mesh infrastructure. So there's been a lot of academic work, therefore, on this scenario. So for example, protocols that enhance the anonymity of this setting, protocols that add DDoS resistance and trust, protocols that add improve the cryptographic guarantees. And in parallel with all this academic work, there's been some open source work. It started with FireChat and then went on to Bridgify and Call, but now there are apps that can actually do this mesh messaging thing. So you would expect that this is pretty popular, right? But unfortunately, mesh messaging isn't widely deployed. So our idea was to try to figure out why. So a good way to figure out why is try to figure out what protesters actually need. There's an excellent paper by Albrecht et al. That talked to the Hong Kong 2019 protesters, or at least some of them, to try to figure out what their information security needs were. And they found, among other things, that protesters work in groups, like specifically group chats of about 20 people. So our idea was, okay, well, if we can get better, more efficient group messaging, maybe then we can have a better deployment. So just as a sidebar, like a traditional group messaging scheme, a really easy way to do this is if you want to send a message to 5 people, you send 1, 2, 3, 4, 5 messages, right? So it's essentially linear in the group size. And this works well on the internet. Honestly, we have a lot of internet bandwidth these days. But in a mesh network, you can imagine it's not a lot of bandwidth, right? So a linear in the group size scheme is not going to be as efficient as we would want it to be. Okay, so where do we go from here? Well, we can talk about continuous group key agreement, right? So we talked a little bit about TreeChem in the last talk and how it's the cornerstone of MLS. Well, we used this TreeChem idea to develop a CGK scheme for the mesh case. So as a quick summary of TreeChem and TreeChem-like protocols, you have this kind of ratchet tree where the users are the leaf nodes of a binary tree, going all the way up to a root node. And each node in this tree has a public key and a secret key pair. And each user only has the path to the key material up to the root. So for example, this cyan node here only has these secret keys. Now, but note that everyone has the root's secret keys, right? So if during normal communication, you can use this root in order to communicate with the entire group, right? This is really great because now we're reducing the mesh bandwidth needed, right? We're only sending 1 message instead of 7. And the cool thing about this tree structure is it really lends itself to efficient group state operations. So an important one in this case is revocation from the group. And this is really important in the protest setting. Like suppose that you're this green node here and you realize that your best friend, the yellow node, has been arrested by the regime, right? And we know from prior work that if you are arrested by an authoritarian regime, they're going to download your phone and potentially break all of the secrets. So we have to assume that the phone will be compromised. So what you can do is in this tree setting, you can send 2 state updates to really efficiently eliminate or exclude this yellow node. You can basically say, hey, if I send these two updates and propagate them through the tree, I can make sure that the yellow node no longer has access to secret material in this new root setting. So essentially now we can just communicate using this new root, and we've excluded it. And again, because of the incidences of arrests and protests, having an efficient way to do this is really helpful. Now, I said we adapted it from TreeChem. We didn't just wholesale rip it off. A couple of considerations in the mesh case. For one thing, you need to make sure that you can support out-of-order message delivery, because we don't have centralized infrastructure to enforce order. So we use some ideas from the causal TreeChem line of work to enable concurrency. We also use updatable public key encryption and some related work to provide better forward secrecy and post-compromise security claims. And we also talk about outsider anonymity, because we think that this model fits group mesh messaging much better than the full anonymity of prior work. So our solution is called Amigo. Read our paper for details. The end. No. Because this would be a great talk if this talk was at Ideal World Crypto, because we found something, we solved it using cryptography. We wrote a paper, we put it on ePrint. The end. But we are not at Ideal World Crypto. We are somewhere else. We are at Real World Crypto. And in Real World Crypto, we ask, how can we be sure that it works when deployed in the real world? And this is a hard question to answer, right? Like, it means you throw your micro benchmarks out the window, right? You're not going to just use those for everything. And I also want to point out that we can't get so real world here. Like, we can't go out and start a protest. Could you imagine the IRB you would have to write for that? And then also, just like ethically, like, why would we collect protester data when this is exactly the kind of attack we're trying to prevent? So like prior work, we have to use simulations. But we focus on making them as representative as possible. So this was not easy. It requires answering two questions. The first question is, how do we simulate protester movements? Why do we ask this question? Well, I would argue that modeling node dynamics is really important for talking about mesh behavior. You can imagine that this mesh network, really densely packed, has better routing characteristics than this mesh network, which is more spread out. And when you start to involve mobility, people moving around, it gets even more complicated. So how do we do that in this setting? Well, the Hong Kong 2019 protesters actually wrote a protest manual. They have a good description of all of their protest actions. And this protest is one of the most covered protests in modern memory, a lot of footage. What can we do? Well, we can develop representative mobility models based on this protest manual, based on protester experiences, and based on newsreel footage of the protests. And that's exactly what we did. So here's a still from our urban protest mobility simulator. I'm sorry, it would be animated, but I had to submit a PDF. Now, you can see here a couple of things, right? This is a city area in a city protest. And we can see there are individual dots that represent people or mesh nodes. And we can see here that there's a march of a densely packed group of people all moving down the city street. And there's also a couple of gatherings here where people are observing a demonstration or a performance of some kind. But I think kind of unique to this case, there's also this notion of a blockade where people are trying to prevent access to a specific area, for example, by the police. And then there's also this human chain, which I thought was really interesting, of people just passing supplies back and forth. So we use all four of these mobility models, as well as a couple others, in order to develop our experiments. But this leads us to a second question, and maybe the most important question, which is, how do we simulate mesh communication? We have to have an unfortunate detour through networking. So the OSI model has 7 layers. And typically, in secure mesh messaging, people talk about the first 3, right? And it makes sense, because a lot of these papers are talking about cryptography, and they just kind of assume that these lower layers exist, and people have figured it out. Maybe they use Wi-Fi direct, which is pretty common. A couple works claim they use Bluetooth. But these layers are understudied, right? So I'm like, okay, well, we have an opportunity here to do an end-to-end evaluation, right? As I told the PhD student on this, Sarah, let's go in and out, 20-minute adventure. And a 20-minute adventure, it was not. So let's talk about why. The NS3 network simulator is what we picked. It's a discrete event simulator that some of you may have heard of because it is the standard in networks and systems for evaluations. Why? It has really good detailed simulations of each layer of the OSI reference model. So great. What we're going to do is we're going to validate our solution compared to prior work by implementing the simulator. Sounds easy, right? No. And here's why. Well, first off, NS3 doesn't even support Wi-Fi Direct, which is like what every secure messaging app says it uses, which sucks because we had to spend a bunch of time implementing it on top of ad hoc Wi-Fi. And the second thing is it takes a long time. These are detailed simulations. It took, for one run, 1 week of wall clock time. And I was spending like $500 a day on cloud credits, so this was really burning a hole in my pocket, right? And this is probably why prior work doesn't include high-fidelity simulations of lower network layers, right? It's just simply too hard. But we did it anyway, so what's your excuse? So, what did we learn? We learned that it's kind of a bleak situation. Existing mesh routing just doesn't work well in practice. So let's talk about why. I think a lot of works assume this notion of flooding, which I think makes sense intuitively. If you want to send a message to someone, you just kind of send it to your neighbors in the network, and then their neighbors send it to your neighbors, and ongoing and so on, right? And again, intuitively, it makes sense that your message packets will get there. But in practice, we saw that the message packet delivery rate was about 21%, right? And that's what gives, right? But this is where that lower layer simulation really matters. We basically have message collisions that occur because of the properties of Wi-Fi. At lower layers, you have several nodes broadcasting, their messages collide, inducing congestion, right? So that just results in a 21% packet delivery rate. And interestingly, we found that really well-meaning optimizations don't actually work in practice. So the secure messaging work of Perry et al. Proposes using digests to alleviate some of the problems with flooding. So for example, in this case, maybe you can, if you want to send a message to your neighbor node, instead of just sending the message immediately when you receive it, you can basically say, hey, these are the digests of the messages I have. Basically have some kind of summary. And then your neighbor node can request exactly those messages it doesn't have. So you just send that to them. And the authors claim that it reduces the number of messages, and it indeed reduces the number of message packets sent than in the traditional flooding case. But unfortunately, we only see a 31% packet delivery rate, which is more than the flooding protocol, but I will say it's not nearly as good as we would want it to be. And so why is that? So yeah, we've reduced the number of message packets, but we've added a new packet to the mix. We've added the digest packet, right? So now these digest packets and the message packets are entering the collision domain. So we don't actually see a superlative increase. And this is actually really frustrating because these numbers are much lower than previously assumed. And when you start to add the protester mobility I talked about earlier, things get even worse. As a sidebar, in our paper, we have some information on alternative routing schemes and maybe some new ones that could help alleviate this. So check those out if you want. So what's the takeaway from all this? I gave it away in the title. For mesh messaging in large-scale protests, cryptography alone won't save us. I have an inconvenient truth to share with you all. The relationship between our community and the lower layers of the network stack is this. We have to use simulations. The simulations don't implement the protocols we want to use. When we implement the protocols we want to use, it takes forever and costs a bunch of money, and then the results show that our protocols suck. So it's not exactly a friendly relationship. So what can we do about it? I think there's a clear need for more networks and systems research here, right? We want mesh networking that supports the secure messaging case, right? And I think there's a really cool opportunity here for co-design, right? We have some characteristics from our work about how the mesh network will operate in practice. Maybe that can influence the design of future work in CGKAs. And in the reverse, maybe new cryptographic primitives can help us architect the mesh in a different way. So contact your local systems researcher today. Now, another thing you can do, I think, and I think it's really important, is to try to also figure out from the other angle, the human factors angle, right? I think we talk a lot about Hong Kong, and I talked a lot about Hong Kong. And it's a great example of a large-scale protest, right? But Hong Kong is very unique in that it is a very affluent digital society, right? There are more mobile phone subscriptions in Hong Kong than there are people, right? So it's kind of a unique case. And while work on Hong Kong and Hong Kong protests are super important, right, we can't use it as a blueprint for the rest of the world. And what we need is we need interview studies with more activists from varied geographies. We want to get a broader picture of this whole space. And I also think that what we can do is once we have tools that we think are useful, go back to these activists, do user studies. Because there's this gap between what academics think protests are like and what they're actually like on the ground. And that gap is preventing us from getting usable tools. And yeah, I kind of rag on cryptography a lot here, but I think cryptography is still important. I think with the rise of authoritarianism all around the world, the time is now to really develop the cryptographic systems that can be deployed when and where they are needed, right? We have the tools to provide the security and privacy guarantees that the users need. But as a community, we kind of need to acknowledge that this is going to be an interdisciplinary problem, which means there's going to be an interdisciplinary solution, right? And once we acknowledge that, I think then we can engage in researchers with networking systems, human factors, beyond, for a more holistic approach to this. And I think then we can start a broader conversation about how academics can achieve tangible impact on sensitive populations like protesters. I think only then can we achieve truly practical, efficient, deployable mesh messaging. So that's my talk. I'm Tushar, and my email and website are on there. You can also follow me on Blue Sky. I didn't delete my Twitter, but it's still there. Our paper is available on ePrint, so check it out. Please scan the QR code. We'd love to hear your feedback on it. Also, 2 of the students who worked on this paper are here as well, David and Sarah. So come find us afterward if you want to talk more. Thanks, everyone, for your time.
I have a question about, you have this simulation with a bunch of mesh nodes. How does the adoption rate of the tool influence the effectivity of the delivery of the packets?
Can you repeat the middle part of what you said?
So what if only 10% use this specific app?
Oh, I see, adoption, yes. That's a great question. That's actually something we're trying to consider right now. In our prior simulations, we considered everyone was using it. But I think what we want to do is figure out what happens if only a fewer people are using it. And maybe afterwards we can share some of our initial results, and I'm happy to tell you more afterwards. Yeah, thank you.
Hi, Tushar, thanks for the talk. This is a very interesting topic. In Belgrade, Serbia, there was a protest with 500,000 people 3 weeks ago. And the main problem was people didn't know what app to install. So this app that you're talking about needs not only to be available, it needs to be hyper available. It needs to be kind of a go-to thing that a random person in a random country knows that they should install. So I guess my question is, how do we kind of approach that goal to make the app hyper available?
Yeah, that's a fantastic question. And I think one thing that we realized is that we don't have the connections in the community to try to deploy this ourselves. So, we can't go out and just start giving this to people. We're not really integrated in that. So what we've been doing is we've been partnering with people in that space. So I mentioned call.net. It's one of the apps that's used. We actually are working with them to try to see if we can integrate some of our ideas into their system. And I think partnering with open source is actually the best way to go about this, only because, there's more authenticity there. And also it allows us as academics to kind of speak with more technical people who can relay it to the activists on the ground without that technical knowledge, but ongoing.
All right, please join me in thanking our speaker. The next talk in our secure messaging session is on analyzing chat encryption in group messaging applications, and our speaker is Akshaya Kumar.
I'm excited to share our analysis of I'm excited to share our work on analyzing group chat encryption algorithms in messaging applications. This is joint work with Joseph Yeager and Igor Stepanovs. For a few years now, the cryptographic community has tried to provide the average user with end-to-end encrypted communication. To meet this need, end-to-end encrypted or secure messaging apps have seen massive success with deployment across various platforms that encrypt content under keys that are only accessible to the endpoints of the communication. Not just that, we as a community are also coming up with the messaging layer security standard that standardizes end-to-end encryption. Collectively, these apps are used by billions of people, so it's really important to study the real-world security of these applications. Our work focuses on group chat encryption algorithms in these apps. In the group setting, members of a group chat want to establish an encrypted channel with some help from a server. And broadly speaking, secure group messaging can be viewed as the composition of two building blocks. The first of these is key agreement, which establishes a shared symmetric key among group members. And this can be done in a variety of ways, depending on what security guarantees we want. This is considered the novel part of key agreement, of group messaging, and has received a lot of academic attention. And we don't focus on that part. Instead, we look at chat encryption, which is the second building block that actually uses the keys derived during key agreement. Now, what properties would we want from chat encryption? At the very least, we want privacy and integrity from an attacker that does not know the symmetric key. However, this allows group members to impersonate, and this can be achieved using secure symmetric encryption. But this allows group members to impersonate each other because all of them know the same symmetric key. And this is really bad because we saw in previous talks that protesters like to work in groups. And also, you might add an accidental outsider to your Houthi PC small group. And that way, achieving privacy is not really practical, but you still want that an outsider cannot impersonate group members. So normal privacy and integrity of symmetric encryption doesn't quite work in the group setting. We also want integrity against members in the group. In other words, we want chat encryption to guarantee sender authenticity against group insiders, as well as privacy and integrity against group outsiders. Naturally, we can achieve sender authenticity using digital signatures. This means that in addition to sharing a symmetric group key, group members additionally have their own signing key pair. And we formalize chat encryption in group messaging apps as the symmetric sign encryption primitive that aims to jointly capture the security goals of symmetric encryption and digital signatures. Across two papers, we introduced a formalism for symmetric sign encryption and defined security notions. Then we looked at various messaging applications, identified their core group chat encryption algorithm, and made it fit our model. Then we used our security definitions to either prove these algorithms secure or find attacks in our model. Whenever we found an attack, we checked if these attacks translate into real-world attacks against the protocol itself, and this required looking at the protocol beyond, details of the protocol beyond the chat encryption itself. When we were coming up with security notions for symmetric sign encryption, it made sense to think about security in terms of group insiders and group outsiders. An outsider is an attacker that uses the application and may compromise individual users' signing keys, but doesn't know the symmetric group key. On the other hand, an insider is part of the group itself and knows the symmetric group key, but does not know the signing keys of anyone but itself. And it's in this latter threat model that we found most of our interesting attacks. Since we said that we want chat encryption to jointly capture the notions of symmetric encryption and digital signatures, natural way for constructing these is by composing these two primitives in either the sign then encrypt or encrypt then sign fashion. A naive sign then encrypt would first sign the message using the sender's signing key, then encrypt the signature and the message under the symmetric group key, then the sender will broadcast the ciphertext to the rest of the group. Encrypt and sign is similar, except the order of operations is reversed. And this is actually what we saw in each of the applications that we analyzed. They used variants of either the sign then encrypt or encrypt then sign construction. And for this talk, I think I'll focus on the first one. Naive constructions are dangerous because they lead to what we call context switching attacks. And to see these, let's consider two group members who are both in groups 0 and 1. Let's say our user U sends a message by first signing it with their signing key and then encrypting under a group 0 symmetric key, then broadcasting the ciphertext to group 0. What a malicious insider can do is decrypt this ciphertext using the corresponding key, then re-encrypt it with group 1's symmetric key and broadcast this forged ciphertext to group 1, effectively impersonating you to group 1. The core issue here is that the same signature is being interpreted in 2 different contexts. We found variants of these attacks, of this attack in MLS in session, although there it allows an insider to replay messages in the same group. There are also attacks where the symmetric ciphertext can be interpreted in 2 different signing contexts. To prevent these context switching attacks, we additionally need to bind the signing and encryption components. And for this, we want to additionally sign what we call the group key identifier, which is a value that uniquely identifies the symmetric group key, and depending on the encryption scheme, also the nonce and the associated data. From the other direction, we want to additionally encrypt the sender identifier, which is a value that uniquely identifies the sender's signing key. With that background, we're ready to look at an overview of our analysis. We looked at 5 different messaging applications, and for each of them, we found different kinds of insider and outsider attacks. In MLS, we found insider replay and reordering attacks that resulted from the lack of context binding. In session, we found insider and outsider replays as well as outsider forgeries that also resulted from the lack of context binding. Although we didn't find any attacks in Keybase, its key reuse and key cycles made it really difficult for us to prove it's secure. In Signal, we identified the outsider forgery attack that was previously identified by Balbas, Collins, and Galland in 2023 that results from the use of a symmetric encryption scheme that does not provide integrity of ciphertexts. Finally, we did find attacks against Matrix in our model, but the way their algorithm was used in the broader protocol mitigated these attacks. That's a lot to talk about in 20 minutes, so I'll focus on the first 3, starting with MLS. MLF is the IETF standard for group messaging, standardized in RFC 9420, and has several implementations, including ones by Amazon and Cisco. MLS uses a really big data structure to derive encryption keys to ensure that each message sent in the group is encrypted using a fresh symmetric key. Members' public keys are used to derive the secret key. Then that key is used to derive a whole bunch of other keys. And then that key is used to derive another bunch of keys, eventually deriving the encryption keys. The encryption keys here are uniquely identified by what group you are in, where you are here, which is called the epoch, where you are in that tree, which is called the leaf index, and finally, where you are in that chain, which is called the generation. What you need to take away from this complicated looking picture is that every member in the group stores this big structure, and encryption keys are uniquely identified by this 4 tuple that we call the group key identifier. Now let's look at how encryption keys are actually used to encrypt chat messages. MLS composes an AED scheme, a signature scheme and an AED scheme in the signed and encrypt fashion. So first, it signs the message along with some metadata under the sender's signing key. Then it encrypts the message body and the signature under the keys from the previous slide using an AED scheme, and then the sender broadcasts the ciphertext to the group. Ideally, we want the signature to authenticate the key identifier of the encryption key so that an insider cannot re-encrypt the message with another key and replay it to the group. If we look at the group key identifier and what the signature authenticates, we see that the signature authenticates the group, the epoch, and the leaf index, but it does not authenticate the generation, which means that it does not entirely authenticate the group key identifier. This leads to attacks. If we look closely, the nonce is also not authenticated, and that leads to attacks with dubious values, so I will not discuss it here. However, not authenticating the generation leads to attacks because it allows an insider to move between generations here, and in practice, what this allows an attacker to do is replay and reorder messages. And I'll lay out in detail the replay attack for us. So let's picture this group chat where our user asks this benign looking question. Our honest member responds by saying yes. They first sign this message using their signing key, then encrypt the signature and the message under this encryption key, and broadcasts the ciphertext to the group. Let's say that the identifier for the encryption key is this 4 tuple. When members decrypt this ciphertext, their clients will display this message. What a malicious insider can do is leverage the fact that the signature doesn't authenticate the generation by using this decrypt then re-encrypt technique that we discussed before. So first, they would decrypt this message, the ciphertext using the corresponding key, then re-encrypt it with a different symmetric key that has the same identifier, except the generation 1 here is the future generation. And they save this forged ciphertext. Then they send a potentially incriminating question in the group chat and impersonate our honest member by forwarding the forged ciphertext to the group. To other members, it appears as though the original sender resent their message. MLS aims to specifically prevent insider attacks, where the attacker knows encryption keys, but should not be able to send messages as though they came from someone else. And the lack of authentication of the generation violates this very goal. We saw that the attack resulted from the lack of binding between the signature and the generation, so the fix is to bind them. MLS already signs the associated data, so an easy way to achieve this is by including the generation in the associated data, while still being compliant with the specification. However, this leaks the generation, since the associated data is sent in plain and could lead to some privacy risks. We disclosed our findings to MLS, the working group, by posting to the mailing list. The turnaround time was really quick. Highly recommend contacting the mailing list. They acknowledged our findings and invited us to present at last week's ITF 1-2 meeting. And since then, a PR has been approved that modifies the architecture document by disclaiming that MLS doesn't prevent insider attack. And this modification also suggests application layer fixes. Future versions of MLS are likely to fix it at the MLS layer by achieving this binding between the generation and the signature. We also found insider and outsider replay attacks in Session, which is a privacy-focused decentralized messaging application with about 1 million users, and it offers end-to-end encrypted group chats for groups with less than 100 members. We found insider replay attacks in Session, which, morally speaking, were the same as the attacks in MLS. And this resulted from the lack of binding between the signature and the group key identifier. This made us think about replays in general, and we found that Session doesn't cryptographically prevent replays in general. This is because every ciphertext that is sent in Session is accompanied by a timestamp, and receivers use this timestamp to detect replays. This timestamp is not authenticated. This allows anyone, including a group outsider, to simply modify the timestamp and forward a replay ciphertext to the group. Of course, an outsider doesn't know what message they're replaying when they're executing this attack, so a non-insider may find it difficult to extract value from this attack. When we disclosed our findings to Session, they acknowledged this attack and also corrected our understanding of some other attacks, but it turns out that they were already developing this new version for group chat encryption that they called Groups v2, that soon after replaced the legacy groups protocol that we analyzed, that is supposed to fix most of the important attacks that we found, though we've not formally analyzed Groups v2. I would like to conclude on a positive note by discussing Keybase, where we didn't actually find any attacks. Historically, this was the first of our analysis, and the explicit use of an algorithm that combines symmetric encryption in signatures and Keybase is what motivated this line of work. Keybase is a suite of encryption tools, including a public key directory, an instant messenger, and cloud storage. It has about 1 million users. We analyzed Keybase's group chat encryption algorithm. In Keybase, members of a group establish a shared symmetric key. Thereafter, every message sent on the group is encrypted using this key. To encrypt chat messages, Keybase uses an encrypt, then sign, then encrypt construction, where it first signs the message, encrypts the message body under the symmetric group key to produce the body ciphertext. Then it combines the hash of the body ciphertext with the sender and group key identifiers and the symmetric encryption key itself to produce the message header. This message header is signed under the sender signing key to produce a signature. To hide the signature itself, the message header and the signature are then encrypted using the symmetric group key to produce the header ciphertext. The sender will then broadcast the header ciphertext and the body ciphertext to the group. Previously, we said that we want the signature to authenticate the group key identifier, which is true in the case of Keybase, and that makes us really happy. However, Keybase additionally signs the encryption key itself, and that means that the signature is derived from the encryption key. Ultimately, the message being encrypted is derived from the key used for encryption, which is commonly known in literature as key-dependent messages. Generally, traditional symmetric encryption guarantees don't hold under the presence of key-dependent messages, and that makes us sad. To account for this, we had to show that the encryption scheme used in Keybase is secure under key-dependent messages that are derived in this specific way. And for that, we leveraged the observation that the signing algorithm here hashes the message before signing it. Then we showed in the random oracle model that the encryption scheme used in Keybase is secure under messages derived from a hashed key. This still doesn't make us happy because it wasn't easy to do. Another thing here is the same key is used in 2 different contexts. And we know from our first talk that this is a bad thing, and we want to prevent potential forgeries that allows an attacker to take a ciphertext from one context, move it to the other, and have it interpreted correctly. Once again, as we saw in the first talk, reusing keys across 2 contexts is okay if we have context separation, which can be achieved, for example, by prefixing the input of one context with a fixed string. Keybase did not implement explicit context separation, so we were sad once again. This should have led to an attack, but it did not. And that was because, on the one hand, the message body here is encoded using the message pack serialization format that leads to this body message always beginning with a fixed prefix. On the other hand, the input to the second context here always begins with a signature, which is highly unlikely to contain the prefix of the message body. We used a specific fact about the encoding scheme, along with the non-standard assumption that an attacker cannot find a signature that begins with the same prefix, to show that Keybase achieves implicit context separation, proving it secure. To wrap up, here are some key takeaways of our work, some of which are just retellings of folklore knowledge. First, sender authenticity is very important in group messaging apps, arguably even more than privacy. The second is that non-cryptographic encoding can oftentimes save the day, and we've seen this in previous analysis of Telegram as well. The third is that reusing keys across different contexts is bad, especially if there is no context separation. Combining encryption with MACs and signatures seems straightforward, but what we saw in our analysis was that their interactions can lead to subtle vulnerabilities. And the last is that formal definitions are important for real-world analysis because they inform secure designs that are simple constructions because we know what our goals are. And with the definitions in place, our attacks were in some senses easy to find. Details are in our papers. The second paper, with the grace of the ePrint editor, should be up soon, by the end of today, hopefully. Thank you.
The messaging protocols try to provide a deniability property so that, for example, the signatures that you have in these protocols can't be used later as evidence against, say, an activist group. So it's obviously difficult to get all of those properties at the same time, but it doesn't seem impossible because if you had pairwise independent keys, then you could do it. So that raises the question, is it possible to do that in less than ON squared communication?
I'm sorry, if I understand your question, is it possible to provide deniability under symmetric sign encryption?
Yes.
Yes. So when we were designing the primitive itself, we were trying to model what happens in the real world, and most of the times it is that people are using regular digital signatures, and so it doesn't provide deniability, is why our primitive is what it is right now. But yes, it can be extended with something like ring signatures to make it deniable, depending on what notion of deniability one wants to achieve, which hasn't quite clearly been defined in group messaging, because deniability against the server or like what offline, online, yeah. So
It's complicated.
there's
Thank you.
definitely good work there.
Thank you.
Please join me in thanking our speaker again. The final talk in our session on secure messaging will be on the triple ratchet protocol, and our speaker will be Shuichi Katsumoto.
Thank you. So my name is Shu, for short, and this is joint work with Benedict, Evgeny, Daniel, Thomas, and Rolf, and this is talk about the triple ratchet protocol. So I do say it's a talk about the triple ratchet protocol, but in detail, the triple ratchet protocol is a combination of Signal's current double ratchet protocol with this new novel piece called post-quantum ratchet. And this blue part is the main technical innovation that we have, so this will be the main focus of our talk. And combining these two primitives and getting this triple ratchet protocol is relatively straightforward, so I won't take too much time explaining that in this talk. So let me just get into the background. So the Signal protocol, what is this? So it's a gold standard for two-user secure messaging, and it provides for secrecy and post-compromise security. And it's a protocol already used within the Signal ecosystem, and also in WhatsApp, Google messages, and so on. And the key thing that I do want to highlight that it mainly relies on the hardness of the Diffie-Hellman assumption. So it's based on a classical assumption. So let me dive into a bit more about this Signal protocol. The Signal protocol can be broken up into two protocols, the X30H and the double ratchet protocols. And this first X30H protocol is the one that allows you to establish shared keys among two users. And once you share these keys, we use this double ratchet protocol to ratchet our keys forward and continuously share keys, which I'll explain a bit later. But essentially, this double ratchet protocol is the essence to provide us with strong security guarantees after once establishing these keys. Okay, and there has been talk about transitioning to post-quantum security. And let's look at the Signal, classical Signal protocol, the X30H and the post-quantum ratchet. The fire indicates for this slide that it doesn't have any post-quantum security. So what they did was that they made a first step towards post-quantum Signal in 2023 in September. So they moved this X30H protocol into a PQXDH protocol. But one thing to note is that it's not fully post-quantum yet. It's only secure against harvest now, decrypt later adversaries. But still, it's a great step forward into the post-quantum regime. But as I said, this is only the key agreement phase. And they still use the double ratchet protocol afterwards, which is now the weakest link. So once your state gets compromised at the later stage, then you don't actually get any post-quantum guarantees. So what this talk is really about is how can we make an efficient post-quantum double ratchet protocol? And for that, I'll have to explain a bit more about this double ratchet protocol. And as the name suggests, there's two ratchets involved. And the double ratchet protocol consists of a Diffie-Hellman public ratchet and a symmetric ratchet. And this public ratchet part, the Diffie-Hellman part, this is where you get the guarantee of PCS, so post-compromise security. And the symmetric ratchet is the part that guarantees for secrecy. So it has two kind of flavors of security, and each one of them gives us this really strong double ratchet protocol. And as I said, the double ratchet protocol is on flames, but where's this flame really coming from? It's coming from the Diffie-Hellman public ratchet. So when we break it down, you can see that the symmetric ratchet, it only actually relies on symmetric key primitives, so it's going to be secure. So now the question is, how do we make this Diffie-Hellman public ratchet post-quantum? And this is the core question. And theoretically, this is already known, so we can use chems to do that. But as I'll explain a bit later, practically speaking, this is going to be incompatible with Signal's constraint. So we have to devise new methods. And for that, I would now explain about this Diffie-Hellman public ratchet. What is this? So this is a two-party continuous key agreement. So in the previous talks, it was a continuous group key agreement, but there's no group, it's only two. And this is very easy to explain in pictures. So let's say Alice, which is red, and Bob is the blue. They initially share some keys, a Diffie-Hellman key. What Alice is going to do is that when Alice wants to talk to Bob, it's going to sample this new Diffie-Hellman key and just performs this key exchange and compute this K1. And it sends G to the A1 to Bob. And Bob can just compute the same K1. And when Bob wants to talk back to Alice, it's just going to ratchet forward in the sense that it's going to create a new key, and it's going to perform another round of Diffie-Hellman key exchange. And this just keeps on going in a ping-pong communication pattern. And this is why it's called ratchet, because it's moving forward. And the question is, why do we need this continuous flow of key agreements? And this provides us with good security guarantee. So let's say at some point, Alice's state becomes compromised, so the adversary knows this red part. When you look at it in detail, this red part just propagates to all of the other areas too. So all these red components are going to be insecure as well. But the good thing is that if Bob and Alice takes 2 rounds to sample new keys, and assuming that the adversary is passive, what's going to happen is that their state's going to heal again, because all this red component doesn't seek into the new fresh randomness pool. And in Eurocrypt 2019, Alvin Corretindores proposed a post-quantum ratchet based on chems, which kind of emulates this Diffie-Hellman construction. And one thing I do want to know is that this healing process is inherently a very heavy public key operation, because you need to sample new randomness and send it across to your peer. So now that we have this Diffie-Hellman public ratchet, I want to explain how we kind of combine this with a symmetric ratchet to get the double ratchet. And I'm going to provide you with the naive construction, which is not used in practice, but to illustrate how it can be used. So this red part, this is the Diffie-Hellman public ratchet. And what Alice is going to do is that it's going to put it into its local state, and it's going to, this black box is the KDF function, so the KDF, and it's going to create this MK1, which is the message key, let's say. And it's going to further run it through a KDF. And for a message M1 that it wants to send, it's going to derive a unique secret key 1 and sends it with that. And this is just going to keep on ratcheting internally. And this is why it's called a symmetric ratchet. So every time Alice wants to send a new message 2, it's going to ratchet forward again, in like the symmetric part, and create a new SK2 and just keeps on moving. And it's easy to see why this provides us with forward secrecy, because if Alice erases SK1 or SK2, then you can't decrypt the past messages. And it's easy to see that this ping-pong communication is very intuitive, because Bob, having this K1, can derive the same state as Alice and decrypt everything. So it looks very nice. But in practice, this is actually not the best idea, because the scheme is not really robust, in the sense that, let's say Bob does not receive this Diffie-Hellman ratchet message, which is this G to the A1, or it arrives out of order. Then what happens is that Bob can't really compute this K1, so it can't create these symmetric ratchets, meaning that it can't immediately decrypt these incoming messages from Alice. So it loses immediate decryption. In the worst case, it can't decrypt at all. And this is why, in practice, what Signal implements is a different strategy. So it batches this G to the A1 with the actual message encryption. And it's just going to batch them together every time they send it out. And this way, it's kind of obvious to see that even if this initial first flow is lost, that's fine, because Bob will be able to derive the same K1 and decrypt the message. Because the symmetric ratchet, you can just keep on moving forward locally. So you get immediate decryption, which is very useful. But one thing to note is that we're using this Diffie-Hellman message, and we're going to continuously resend this. So it's kind of like wasting bandwidth. But on the same, but that's not really a big issue for the current schemes, because in classical crypto, this is a very small component. But I hope this kind of motivates why post-quantum ratchet has been a theoretical thing mostly. So if we follow the ACD approach of creating a post-quantum ratchet using chems, then we'll have to send this encapsulation key and this ciphertext, and we have to repeat this over and over again. So one post-quantum ratchet is roughly now 2 kilobytes. which is 70 times bigger than the Diffie-Hellman ratchet. And to keep the impact on performance and bandwidth consumption minimal, Signal aims to limit this overhead to 40 bytes per message. So this is a strict requirement that they impose. So there's a lot of compression that we have to do, and it's not really clear how to make this all work. And this brings us to our efficient post-quantum ratchet idea. So there's three main ingredients for our construction. So idea one is that we're going to create this new notion of ratcheting chem and construct this thing called Katana. This is just a better post-quantum ratchet than running two chems in parallel that was done previously. But this itself doesn't allow you to just squeeze everything into 40 bytes magically. So what we do next is that we have this idea two, which is chunking using erasure codes. So we're going to force a smaller bandwidth using erasure codes. And this will provide us with worse PCS guarantees. So in the final idea, what we're going to do is that we're going to boost this PCS guarantee with a better sending strategy, which we call opportunistic sending. So I'm going to explain each of these steps, and I think they're relatively intuitive, that it's very easy to understand. So the first thing is this ratcheting chem. What is this? And to understand this, I think this example is very nice to see. So in Signal's Diffie-Hellman ratchet, when you look at this G to the A1 component, you can actually see that it's being reused for two purposes. So this component is used for a Diffie-Hellman key exchange, but it's used once as a receiver and once used as a sender message. So it's being reused in two places. But unfortunately, if we try to replace everything with chems, this kind of idea doesn't work anymore because an encapsulation key and a ciphertext can be interchanged. And this is why in ACD19, you required two chems to kind of emulate this behavior of this Diffie-Hellman ratchet. And this comes this notion of ratcheting chem, which we introduce. So this is a special chem where the encapsulation key can be reused as part of the ciphertext. And on first glance, this doesn't really make much sense, but when you look at the concrete example, it's really easy. So I'll give you one common lattice-based chem. Encapsulation key is this LW sample AS plus X, where A is this public matrix that everybody knows. And the ciphertext is also in this format, CT0 and CT1, where CT0 is again an LWE sample with respect to this public matrix A. And it's only the CT1 that really depends on the encapsulation key. So although the format is a bit different, we can work around that. And what happened is that we can reuse this encapsulation key as part of this ciphertext now. So what it means is that if somebody already sent an encapsulation key and at a later point wants to send this ciphertext, it doesn't have to send this CT0 anymore because it's going to reuse it there. And CT1, this much smaller part, will be the actual ciphertext now. And in lattice-based crypto, what's really lucky for us is that this CT0 is the much dominant part within this ciphertext. So CT1 is much smaller. So this provides us with a significant size reduction. So to give a flavor of how much size reduction is that compared with MLChem, in Katana, you can see that the ciphertext is much smaller now. So the actual message that we have to send, which is this encapsulation key plus ciphertext, it's about 40 to 50% smaller now. And one thing I should note is that reusing things always, is not secure. So we have to provide like a new security proof claiming that it's really secure. And for that, the parameters has to be kind of modified from MLChem a bit. And that's why the encapsulation key is not the exact same size. So that's the first idea, but still, it's 1 kilobyte. And we have to put it into 40 bytes, which is much smaller than what we can. And this is why we're going to use erasure codes to chunk these really big components into smaller pieces, each of going to be smaller than 40 bytes. So this is a very easy idea. And there's an instant pro, which is that now we're only going to send these chunks repeatedly. And overhead per message is small and fixed because we can control that now. And when you think about it, so when Bob is offline for a while and Alice has to send a lot of message, then this is very optimal because Alice never has to repeat these really big components, which was the encapsulation key plus the ciphertext. It's just going to repeat different chunks over and over again. And if Bob has enough chunks, then it can decode. But on the flip side, there's this obvious con, is that Bob now requires multiple chunks to decode this encapsulation key. So, and if it doesn't have this encapsulation key, it can't actually run this public ratchet, so it can't really move forward. And okay, so I was using PowerPoint, so you can't see, but I think this slide, is enough. But you can see that there's a bot symbol being sent from Bob, meaning that Bob is wasting its bandwidth a lot because it can't really do anything unless it has this encapsulation key from Alice. And this means that the public ratchet is going to move slower, so it's going to give us worse PCS guarantees now. So this brings us to our final idea, which is opportunistic sending. And for this talk, I'm going to call that Yocho. And again, this is very simple to understand once you see the concrete example. And let me explain through the sending strategy with Katana. So you can see that Bob's large encapsulation key is AS plus X, and it's independent of Alice's encapsulation key. And it's only this Bob's really small ciphertext that really depends on Alice's information. So at this point, the opportunistic way of sending is that they're just going to send these large components concurrently. So Bob does not have to wait until Alice sends all of its chunks. It can already start sending its encapsulation key by chunking it and not waste bandwidth. And once it receives this encapsulation key, it just sends this really small ciphertext, and that's it. So this is a very nice way of not wasting bandwidth. And if you combine all these ideas together and write it down, it becomes our post-quantum ratchet protocol. And in the final phase, I want to talk about a preliminary benchmarking and how it kind of provides us with better guarantees. And the reason why I call it preliminary is that because benchmarking itself is a whole other talk. And we have a lot of results on this, but it did not fit. So we're going to talk about a very basic thing. And the reason why this is very complicating is because it's really hard to define what a best protocol is. Because obviously it depends on the allowed bandwidth budget. For our scenario, it's 40 bytes, but in general, it might not be. We also have to think about a lot of different communication patterns. Is it a balanced communication? Is one device offline for a long time? And depending on that, maybe your protocol might the best protocol might be different. So for this talk, I'm just going to give a very general overview. And for those who are interested, please ask us offline. But one thing to know is that so how do we define this best protocol? And what we want to do is that we want to so the criteria that we're going after is the number of exposed messages under corruption. So if an adversary corrupts a user at some state, we want to count the number of messages that's explicitly exposed to the adversary. And a scheme that minimizes that should be the best protocol. And with that in mind, we'll provide some performance with MLChem versus our optimized Katana. And since we always have to do this chunking optimization because right now we're fixing it to 40 bytes per message, the overhead. And this x-axis shows the number of exposed messages. It's not really that important, but the only thing that we want to tell in this slide is that Katana has about 60% less exposed messages because the number of actual bytes that we have to send out is smaller than MLChem. So it has a direct effect on how secure it is. And the other benchmarking that we wanted to do is Katana versus this opportunistic Katana where we do this yochoing. And since we're optimistically sending a lot of information, we further get this 25% less exposed messages compared to not doing that. So this was just to give a flavor of how much gain that we get using these optimizations. But as I said, for the full details, please let us know offline. And so this is the conclusion of this talk. And this was a preliminary talk based on the Eurocrypt paper that we had. But a lot of other ideas emerged after that, and that is on the way right now. And we'll be talking at Eurocrypt and an affiliate event called CAW, which will be talking more about this experimental results. And just from Signal, a post-quantum ratchet is in development right now. And the current plan includes many of today's ideas, but with slight differences. One of the key differences is that they're going to use an MLChem-based protocol for a first step. And Signal hopes to use these optimizations like Katana in the future. And that's the end of my talk. Thank you for listening.
Very nice talk. Thank you. The ML, the Kim thing is very cool. So about like 5 years ago, there were some ideas in the community that could also circulating about doing a different kind of optimism, which is where you had just a completely separate kind of ratchet that just got some kind of whatever it needed for the Kim whenever it could get them. Possibly not necessarily using erasure coding, using whatever, and just did that whenever it could. So I guess so 2 questions related to that. First, you're now, this 40 bytes is not sending it's not sending the full 32-byte key, Diffie-Hellman key with each thing anymore, I guess. That's also part of the erasure coding. And so would there, if you weren't completely constrained by this 40 bytes, but had, maybe 100 bytes or something like that, would it make sense to send like the Diffie-Hellman thing with everything so that you could immediately upgrade that and then still do all the erasure coding stuff and then have this idea from like 5 years ago of doing the optimistic thing whenever you finally got it? Would this make sense?
Great, thank you for the, so if I understand correctly, so this 40 bytes, sorry, it was only for the post-quantum part. So we are always going to keep on sending the Diffie-Hellman, like the classical part, as it is implemented right now. So I hope that answers the question.
Can you give any intuition for what drives the 40 byte requirement?
So that's a great question that I feel like should be answered by the Signal team. So, but there are some people here, so we can discuss this offline. I don't have a strong reason on why.
Okay, thanks.
All right, so we'll break now for coffee. The next session will start at 11:05 with the Levchin Prize and invited talks. Please join me in thanking Shuichi again. Nope, we have one announcement from Mariana before we break, sorry.
The mic is not on. If you haven't managed to pick up your badge, please pick the badge at registration. Also, if you're a student with a stipend and you didn't sign in, please sign in at the sign-up sheet. And if you have questions about getting your stipends, talk to Brian Lamacchia, who is right here.
minutes and we'll get started. Okay, so it's time to get started. So welcome to the session, the Levchin Prize Award Ceremony. This is a fun part of the morning where we celebrate contributions to real-world cryptography. So let me just remind you again, kind of read the purpose of the award. So the Levchin Prize basically honors major innovations in cryptography that have had a significant real-world impact. We've been running this award now for quite a while, but first I should say that the award basically started in 2016. It's named after Max Levchin, who is sponsoring the award and has agreed to sponsor it in perpetuity. So we award 2 awards every year, and each award comes with a $10,000 prize. And basically, Max Levchin agreed basically to sponsor this now forever. So this prize will go on forever, which is wonderful. So let's see. So the awardees so far, I kind of listed them here. I guess it's starting to get harder and harder to fit it all on one slide, but I'm very proud of the list that we have so far. These are like, all of these have made very significant contributions to the practice of cryptography in the real world. So it's wonderful to see this list growing, and it's going to grow by more today. Okay, so I guess I should just say one last thing to remind everyone that in fact the award itself, beyond the $10,000 prize, it comes with this wonderful cryptex, which the winners of this year will receive by mail. So you have to solve the puzzle to open the cryptex, and you'll find something inside of the cryptex. Yeah, so this is this beautiful trophy that comes with the award. All right, so now that I think you guys have heard me speak about this now for a couple of years, with that, let's kind of turn to the main event, which is announcing the 2025 Levchin Prize award winners. So yeah, so the award, so 2 awards. Our first award for 2025 goes to, drum roll, yes, yeah, so our first award goes to, to Adi Shamir. I have to say, we actually had trouble with the citation here because Adi made so many contributions to cryptography that we couldn't actually fit it on the slide. And so actually, if you go to the web, on the web, there's a much longer description of Adi's work. But Adi has made foundational contributions to ciphers, cryptanalysis, protocols, public key systems. I kind of picked a really tiny sliver of Adi's contributions, and it's really just mind-boggling that one person can have such an impact on one field. So of course, Adi is the S in RSA, for which he won the Turing Award, but that is dwarfed by everything else that he made, all the other contributions he made to cryptography. So just kind of going through a tiny, tiny sliver of Adi's contributions. So he invented differential cryptanalysis, which in some sense kind of launched the whole field of analyzing ciphers. He had this amazing contributions on what's now called Shamir secret sharing, how to share a secret. Again, a beautiful contribution to the field. Of course, invented the Fiat-Shamir transformation. So this is this how to prove yourself paper, which many of our works would not be possible without the Fiat-Shamir transformation. And along the way, he also proved this fundamental result in complexity on interactive proofs, which says that IP is equal to P space. And again, this is just a tiny sliver of all the contributions that he made to the field. So it's really remarkable that one person can have such an impact on the practice of cryptography. So really, it's a wonderful pleasure to award this award to Adi Shamir. So Adi, please come up to the stage and let's all congratulate Adi. And before I hand it over to Adi to say a few words, I did want to make one comment. So as I said, the award comes with a $10,000 prize, but Adi actually decided to donate this his own prize for student support at RWC. And in fact, some of the support that goes to all of you, to some of the students who are here, are actually thanks to Adi's contribution. So thank you so much for doing that too. Okay, so with that, Adi, I'll hand it over to you for some words of advice. Oh, what's doing it?
So I was asked to talk for about 5 minutes, and I thought that I'll give you some advice because I see many young faces here, many people at the beginning of their research career, and I've been in this research area for a very long time. So I'll try to distill 3 things from my experience so far. So my first piece of advice to everyone is to read. You should read every paper, both within your field and outside of your exact research area. At the beginning, in the late 70s and the early 80s, the field was so small that I made sure that I read every single paper that was published in cryptography. At some point, it became quite difficult, as you can imagine. And then I made a vow to read every abstract of every paper which appeared in cryptography. And this also worked for a while. And I must admit that in the last 10 or 15 years, the most I can do is to read every title of every paper that appears in cryptography. But please try to read as much as you can. The second piece of advice is what kind of problems you should try to work on. So here is how I suggest you divide your time. Spend about 25% of your time working on the hardest and most interesting open problems in your field. Identify them and spend some time. These are the moonshots. It's very likely that you will not be able to solve any of them, but if you do, this will base your career upon. You'll become world famous for solving one of those problems. So please spend at least 25% of your time on the moonshots. Then spend about 50% of your time on regular kinds of problems, those which have a good chance of being solved. Try to find interesting problems, those that can be published at good conferences. This will be the bread and butter of your CV, and you're likely to have many good, interesting papers based on this. And the last 25% of the time, just play. Think about all kinds of amusements, how to twist things in a very unusual way. I know, for example, that the way I got my idea about secret sharing was because I read a kind of puzzle about a bank which wanted to safeguard the safe, and it wanted to give keys to the various executives of the bank so that any 3 of them will be able to unlock the safe. And the question was, prove a law bound on how many keys they have to give each one of those executives. And as soon as I read this, I said, we are living in a new world. We now have cryptography, we have tools. Why don't we try to solve the mathematical version of this problem, not with actual keys for the safe? This led me to the paper about secret sharing. And the third piece of advice I can give you is to diversify. You saw that I haven't stayed in one area for the whole career. And I can tell you that it will be extremely useful if once every, I don't know, 5 years, 10 years you choose, you'll switch to a new topic which becomes trendy, which raises new kinds of problems, and it will do wonders to your career. I've started in public key cryptography and then moved to protocols, moved to zero knowledge, moved to complexity, moved to cryptanalysis of symmetric ciphers, moved to side channel attacks. And I can tell you that many of my recent research papers are related to combinations of ideas from different areas. So please try to keep those 3 pieces of advice, and you'll launch a great career. Thank you. And finally, I want, of course, to thank the Max Levchin and the selection committee for selecting me. Thanks. Great. I'll stay here.
Okay, perfect. That was excellent. And as I said, we have 2 awards every year. So now we move on to our second Levchin Prize winners. And the second Levchin Prize winners for 2025 is actually the KoNFS project. So Pierre Gaudry, Emmanuel Thom, and Paul Zimmerman, please come on stage. This award is for developing KoNFS and for continued factoring and discrete log records. So before I hand it over to you, let me just say a few words about KoNFS. So KoNFS is actually a complete open source implementation of the number field sieve for factoring and discrete log. The latest records in factoring and discrete log were achieved using KoNFS. I wrote some of the numbers here. You can see the computation costs. These are massive projects that were done using the software system. And so for this contribution, the team is winning the 2025 Levchin Prize. And so with that, I'll hand it over to the 3 of you to say a few words. So congratulations. Thank you.
Thank you, Dan.
The floor is yours.
Thank you. I'm very honored that we're receiving this award this year. Thanks for choosing us. The Levchin Prize means a lot to us for a software project such as KoNFS. So I'm going to say a few words about KoNFS and leave whatever negative number of minutes will be remaining for my 2 colleagues to comment on a few aspects. So KoNFS started in 2007 as mostly some kind of a team building project. And so it's gone a long way since then. I think that along the way, some people contributed, including PhD students. I think it's fair that I mention Alex Krupa, who was among the ones with the most substantial contributions to KoNFS. And KoNFS now is something like 250,000 lines of C and C++ code, which by academic standards is kind of large. So we didn't start with the goal of setting records, but we did have some backgrounds in running computations and also the mathematics behind the number field sieve, which made us kind of well equipped to deal with this task. And so KoNFS, we started with the goal of making this complete implementation of the number field sieve. And at the time, there was no such complete thing. So we decided that it was going to be LGPL, meaning that we were going to reinvent the wheel for many things. So it kind of slowed us down at some point, but it's also interesting that we did that. And then after a while, of course, we got interested in ramping up and tackling larger and larger computations. And the numbers that Dan showed kind of proved that we went a long way in this direction. So in the beginning, it was only factoring, and discrete log came afterwards. And the funny thing about the number field sieve, I mean, it's a complicated algorithm, and transferring from a factoring only software to something that deals with discrete logs brings kind of a lot of complications. So it was funny. I mean, there are many points in time where I thought I knew the number field sieve and realized that there was some glitch that I wasn't completely okay with. But so the latest records that we obtained 5 years ago, I mean, that's 250 digits for factoring and 240 decimal digits for discrete logs. And the natural question is whether we'll be doing RSA 1024 someday. I mean, it's on paper, it's like around the corner. It's like pretty clear that it's doable. but it's like 50% a question of having big pockets and 50% a question of optimizing the implementation and making it able to deal with such challenges. So if you do have big pockets, you will still have the implementation part to do. And if I had an infinite amount of time, I would still need some resources because they are not in my basement. Okay, so that's about it for what I wanted to say. So maybe I hand over the mic to my two colleagues. I don't know if I would factor 1024 first, but oh, I'm sorry. So Dan is asking whether my guess is whether me or a quantum algorithm would factor 1024 first. So I don't know about me, but I don't give a penny on a quantum computer factoring 1024 anytime soon. So it leaves us at least 20 years, if not more, to factor 1024. That's my guess.
Okay, so I will say only a few things. So, like Adi, I will say some advices for young people. So I'm very happy to have many young people here. So my motto will be code, code, code. So in my career, I have implemented many algorithms. And when you try to implement a real algorithm, you find bugs, of course. You find improvements, so it's very nice. And last thing I wanted to say, so I'm very happy to be here, but when on February 13, I entered the lab, I saw Emmanuel, I said hello to him like every day. And he told me, did you read your email? Oh, okay, I saw some email, but not. And in fact, I had deleted the mail from Dana because I thought it was a spam. Okay. So please read your mail.
Okay, just a few words. So thanks a lot for to the committee for this prize. Actually, I'm very happy that such a long-term project gets recognized. This is not always easy to have a long-term project in the academia because you have to get grants and blah 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 and get results. So it's a very good to have this kind of recognition for such a long-term project. And maybe something I would like to mention also is that I really like the incentive for cryptanalysis, the incentive given by the challenges like the RSA challenge or the Certicom challenge in the old days. Nowadays, there are challenges for lattices. Maybe there are not yet challenges for isogenies, but challenges for cryptanalysis give a good incentive to write software like KoNFS that really helps getting a hand on the real difficulty of the problems. So yeah, that's what I wanted to say, and thanks again.
Congrats to the winners of this year. So with that, let's see, this concludes the first part of the ceremony. I did want to say that we are always seeking nominations from the community, for the prizes for next year. So if you go to rwc.iscr.org, there's a Levchin tab, and there's a form in which you can nominate your colleagues. So please nominate. It really helps us in choosing the winners. We take your nominations very seriously. So please go ahead and do that. It will help us for the following year. This year, we're also starting something new with the Levchin Prize. In fact, we are the steering committee invites one of the Levchin Prize winners to deliver the Levchin lecture. And so this year, we chose Adi Shamir to deliver the first inaugural Levchin lecture. And Adi is going to talk about how to securely implement cryptography in deep neural nets. So Adi, the floor is yours.
Is the microphone working? The microphone is working, but this is not. Can I see my first slide, please? Well, I'll give you a slideless 30-minute talk. Oh, here. Okay, so I'm going to talk about a new topic. This is very recent result. It hadn't appeared so far in any conference, but you can find it in ePrint. And it's joint work with two colleagues from Technology Innovation Institute from Abu Dhabi and Eyal Ronen from Tel Aviv University. So there are two huge areas of research. One of them is cryptography, security. The other one is AI. Both of them are very active, lots of interesting results. But in the past, the intersection between them had been quite small. I'm not talking about how to use AI in cybersecurity. This had been an active research area, but cryptography per se had almost no intersection with AI. And actually, when I decided about 3 or 4 years ago to move into this area, the reaction I got when I submitted papers to Crypto and Eurocrypt and Asia Crypt conferences often included a remark by the referees that why does this topic belong to cryptography? And on the other hand, after publishing several papers and after others got into the field, my latest published paper, which is going to be presented at Eurocrypt 25, actually won the Best Paper Award. So you can see that there is a total shift, and now people are accepting questions of security in artificial intelligence as being a major part of the crypto tool set. So today I'm going to talk about a topic which is right at the bullseye center of the intersection between the two areas. And this is the question of, okay, we have all kinds of cryptographic schemes. Can we implement them in a secure way in a deep neural network? So the problem is that cryptography is essentially digital, and it maps bit strings to bit strings. On the other hand, deep neural network is essentially analog, and it is mapping real valued inputs into real valued outputs. And it's essential for deep neural network to be continuous, because without the continuity, you cannot do gradient descent, you cannot calculate the gradients, et cetera, et cetera. So there seems to be a gap. They are incompatible. The discrete questions dealt with by cryptography and the continuous world of deep neural networks. I want to mention that for about 2,000 years, we had been using analog computers, starting with the Antikythera mechanism for navigation used by the Greeks. We have been using for several hundred years the slide rule in order to solve differential equations. Bomb sight, Northern bomb sight in Second World War was an analog computer. But about 70 years ago, everything changed. We dropped all the analog computers. We started using only the Colossus code-breaking machine in order to break crypto systems. IBM introduced the mainframes. We have microprocessors, and all the analog computers were thrown to the sideways. On the other hand, I claim that in the last 20 years, there is a shift back. And the way I interpret MAGA is make analog great again. Because if you think about quantum computers, we are talking about zeros and ones as states, but the actual qubits contain a continuously varying kind of combination, linear combination with coefficients which are complex numbers. So there is something continuous. And if you think about how Grover's algorithm, for example, works, you have a vector in Hilbert space, and you continuously shift it until it moves into the right direction. So there is a lot of analog elements in quantum computers. Of course, all the deep neural networks are analog because they are mapping real values to real values. And there are all kinds of new technologies, neuromorphic computers and other models, which are also using analog ideas. The fact that even digital devices have an analog characteristic had been known for a while, at least since Kocher had demonstrated how to use side channel attacks, because if you are looking at a microprocessor, there is a continuously denominated emanations from it, how much power it consumes, what kind of electromagnetic radiation it creates, etc. These are analog outputs coming out of a digital device. When you are doing cryptanalysis by analyzing power traces, again, you are looking at the analog shape of those curves. When you are introducing fault attacks, you are creating all kinds of jitters in the timing of the clock or using unusual input voltages, etc. And this creates just a one-time kind of glitch in the operation of the device, and then you are able to break the crypto system using the analog outputs of a digital device. So if I'm trying to summarize the situation, there are users at the top, and there are adversaries on the left-hand side. So the users usually have digital data that they want to encrypt or to do other cryptographic operations on, and they can use digital data on a digital computer, or they can use digital data, but they're using a leaky computer. It's a digital computer with analog characteristics. And then there is the digital data, which is implemented on an officially analog computer, not one which unintentionally emits some analog signals. Now, the adversaries can try to use digital attacks. So the combination of digital attackers and digital computers leads to standard cryptography that we are all interested in. But there are actually users who are using digital data and leaky digital computer, and they're using analog attacks, and this leads to the side channel attacks. And there were some papers which tried to look at the issue of how do you implement cryptography on a totally analog computer, like a deep neural network. There was a famous paper by Shafi Goldwasser and Vinod and Zamir and several other researchers. But they said that even though they implement their cryptography on an analog computer, such as a deep neural network, the adversaries are only allowed to use a digital attack. And this, they missed all the fun, because I claim that the interesting results happen in this corner when you are actually allowing the users to implement cryptography on an officially analog computer, and the adversaries are also allowed to use the analog attacks. So now that I've placed the paper I'm going to talk about in context, let's define what does it mean, what is the deep neural network that I'm usually looking at. Sorry. You have many layers. In each layer, you have a linear combination with real valued coefficients of the real valued inputs coming from the previous layer. And after you perform this linear mixing, you apply a ReLU function, almost always the ReLU, which is a continuous function, 0 for negative inputs and copying the input to the output for positive inputs. And because linear mappings are continuous and the ReLU is continuous, if I'm taking the inputs and I'm moving them up and down in a continuous way, the outputs are also going to move down and up and sideways, etc., in a continuous way. There are no jumps anywhere when you're implementing cryptography on an analog computer. Okay, so let's get to the issue of how can I implement crypto systems such as AES, which will be our running example, on an analog computer like a deep neural network. I want it to be correct in the sense that for every combinations of 0, 1 as real valued inputs, I'm going to get the correct 0 1s in the output. And it turns out that deep neural networks are universal. They are powerful enough to be able to implement any digital mapping like this, but along the way, unintentionally, they also create outputs for inputs which are strange, which are not 0s and 1s due to the continuity. So DNNs are both digitally universal because they can implement and, or, and not very easily. You can write very simple DNNs which do it. And then by composition, you get any Boolean circuit. And they're also analogly universal because there are results about how you can approximate any continuous real-valued function with a wide enough deep neural network. Okay. This is now a new playground with new rules, new techniques, because the attacker can now ask the deep neural network on which the cryptography is implemented, please tell me what is the result of encrypting a plain text whose first bit is 0.3, somewhere in between 0 and 1. The second bit is even outside the range of 0, 1, so -7. The third bit is 3.1415, etc. And it will give you an answer. Now the question is, will this answer leak any information about the secret key or not? Question that no one had answered before. Another example, an attacker can apply what we call a jitter attack, in which you take one of the bits in quotation marks because it's a real number, and I can slightly shift it forward and backwards and see what kind of effect it creates on the real valued outputs. Something which is unimaginable in the binary case. A third example, the attacker can move from one plain text along a straight line to another plain text and see the piecewise linear kind of behavior of the output as you move from one plain text to the other, whereas when you deal with binary input, I can only jump from this input to that input. So I hope it's clear why the game is completely different. And I just want to mention how keys are handled. I assume that the attacker has access to a black box. He doesn't see what's inside. There is input coming from the outside for the plain text. There is an internal register which contains the key as 0s and 1s. This cannot be seen and cannot be manipulated. I'm not talking about related key attacks. So this is fixed inside. And then you get real valued outputs coming out here. Okay, so you cannot see the top of my slides, but the question is, how can you implement cryptography on the DNN? And I give the example of AES. So everything in AES can be implemented by just two types of elementary operations. One of them is a mapping of 8 bits to 8 bits. These are the S boxes or the multiplication by the constants 2 and 3 in the finite field of the AES linear mapping, or mapping 2-bit inputs to 1-bit output. And these are the XORs, where you XOR a subkey or you XOR 2 bytes when you are doing the linear mixings. So if I can implement these two operations, I can get a complete, very simple kind of implementation of AES as a deep neural network. So there is a very natural and simple way how to implement any Boolean function with a small number of inputs as a ReLU-based DNN. And this is described by the notion of corner functions. So a corner function, think about the Boolean cube. Suppose it's the 8-dimensional Boolean cube. It's supposed to describe how 1 bit of the output is mapped by the S box from 8 bits of inputs. So it's 8-dimensional Boolean cube, and each corner has 0s and 1s written on them. I'm going to concentrate on a single 1 in one of the corners, and I can use a ReLU whose the zero value of the input, the region in the 8-dimensional input space, which gives a 0 as an input to the ReLU, is kind of diagonally oriented hyperplane. And now everything which is on the far side in the direction of done is going to give negative input to the ReLU. So it's going to give a value of 0. And as you are moving in the direction of the corner with the 1, it starts from the value of 0 and it increases until it reaches a value of 1 at the corner. So if I think about this corner function, it is going to give me 1 at the correct corner and 0 everywhere else. And now if I want to implement a Boolean function which has 128 ones, in AES, for example, each bit of the output of an S box is balanced, has 128 zeros, 128 ones. I just add together 128 corner functions, where each corner function corresponds to a corner with a 1 in it. Okay? So the particular corner function here, with the 3-dimensional example, is ReLU of x1 minus x2 plus x3 minus 1. And this is going to be 1 only at 1, 0, 1, and 0 anywhere else. And if you sum them up, I will describe all the corners which should be 1. So I hope it's clear what a corner function is. And this enables me to build the 2 to 1 or the 8 to 8 functions that I need in order to implement AES. Okay, so I already explained this. How do we implement the XOR? It's a special case, 2-dimensional special case of the general small number of input corner functions. So you can easily implement XOR by ReLU of x1 minus x2 plus ReLU of x2 minus x1. If you think about it, this is just the absolute value of x1 minus x2, which gives me 0 if they are equal, and 1 if they are unequal. Okay, so this is how I'm going to implement. And we call this idea of using corner function the natural implementation of AES as a DNN. And it is correct, because for 0, 1 inputs, it gives me the correct outputs. And now the big question is this natural implementation secure when an adversary can use real valued inputs? Now, there is an interesting result in the paper you'll find on ePrint, which I don't have time to present. And this is a very unusual case where I have an exponential separation between the real valued complexity and the Boolean complexity. So I can show a very simple function which can be implemented with 1 neuron, single ReLU, so that if you are only allowed to ask questions which are zeros and ones, it will probably take exponential time to solve. Well, if I can use real valued questions, I can solve it in linear time. So look for the details. So the answer is that just as side channel attacks become very easy, all these natural implementations of cryptography can actually be easily broken. And the reason is that almost any secret key block cipher, including AES, starts by XORing each input bit to a key bit. And I'll start by concentrating on this initial XOR and show how to extract the key bit that had been XORed to the plaintext bit. And we'll use a jitter attack, which just tries to move a little bit the input and see what is the effect on the output. So here is the Boolean function of the XOR. I had the plaintext bit, which could be 0 or 1, and I have an unknown key bit, which is 0 or 1. And the XOR, the output of the XOR is 0 here, 0 here, 1 here, and 1 here. And now think about implementing it with corner functions. And let's first assume that the two ReLUs are kind of separated from each other. So I have a region here which is totally 0. Here it goes up towards 1 at this corner, and here it goes up towards 1 in this. And now, where am I? I know the plaintext bit, it's 0. So I know that I'm either in the first floor or in the second floor, but I don't know which case. If I'm jittering, I'm moving left and right here, I'm in the 0 region. and therefore the output of this initial XOR will not change as I'm jittering left and right. If the only change I make is in this one plaintext bit, it is immediately XORed, and the result is being used elsewhere. Nothing changes in any of the bits which are getting into the later stages of the encryption, and therefore the ciphertext, the outputs as real values, are not going to jitter. They're going to be stable because I lost the jittering at the very first step. Whereas if I am in the second floor, I'm in a region where moving left and right does change the value of the XOR with respect to this diagonal. And therefore, I have a very simple jittering attack which will recover all the first subkey. But this worked when the two XORs are not back-to-back as they were. If you remember, I said that I'm looking at ReLU of x1 minus x2 plus ReLU of x2 minus x1. And there, if you think about it, the two 0 are the same diagonal. So what happens if I'm in this case? I have back-to-back ReLUs. I can still solve it because if I'm moving in this direction, the value goes up from 0 towards 1. So I'm moving in epsilon up. And if I'm jittering in the other direction, it is also going up because you had a kind of V shape in the output. And therefore, at plus epsilon and minus epsilon in this plaintext bit and no changes in the other plaintext bit, I get the same output coming out. Whereas here, if I jittered in the positive direction, I'm going to have one value. And if I'm jittering in the other direction, I'm going to get a higher value coming out of the XOR. And this is going to avalanche and affect everything else. And I'm going to see a totally different ciphertext. So I can distinguish between the case in which jittering up and down will give me the same ciphertext or different ciphertext. And this will tell me whether I'm in the lower floor or upper floor, and it will leak out the value of the key. So I hope this was clear. But there is a very easy way how to solve it. And this is if you are not allowing values to be lower than 0 or higher than 1. I'll show you in the next slide a very easy way, how we call it sanitization. I can easily restrict the inputs to be in that range 0 to 1. And then I can jitter only in the positive direction here and the positive direction here, increasing the value from 0, etc. And then this is increasing the value coming out, and this is increasing the value coming out. So the ciphertext are, in both cases, going to be different. So I'm not going to see whether I'm at the bottom layer or the top layer. But this can also be solved with a more complicated solution. So we don't have perfect sanitization. I don't have any function which can be implemented on a deep neural network, which will give me, for example, the value 0 if the input was up to 1/2, and 1 if it was 1/2 or higher. Because this is discontinuous, so I cannot implement it in a deep neural network. But I can do the next best thing, which is partial sanitization. This is going to give me a value of 0 if I'm giving any negative input. It is going to grow linearly until I get to the value 1, and it will stop growing after 1. And this is actually going to chop my jitter attack. I cannot go to negative values below 0 or to positive values above 1. OK, this is implemented very easily, like ReLU of x minus ReLU of x minus 1. It gives you exactly this behavior. So we have another attack. Since I'm starting to run a bit out of time, I'll not give you the idea. So I cannot concentrate on the XOR, but I can concentrate on the first S box after that XOR. And I can identify a very special behavior if the input to the S box was 0. Sorry, if the output of the S box was 0, 0, 0, 0, 0, 0, 0, 0. 8 zeros at the output of the S box are going to behave differently with respect to jitter attacks than all other 255 inputs. And the reason is a bit more complicated, but you can easily find it. So I'm not going to find the key by looking at the initial XOR, but I'll find the key by looking at what happens the next step afterwards when I go through the S-box. Okay, so I'll skip the explanation of this. And now we come to the last part of my talk, where I'm going to answer the question, can you implement cryptography in a secure way on a deep neural network in a way which will not be easily breakable like all the attacks I showed you so far? And we know from experience with side channel attacks that it's very difficult to solve all possible types of side channel attacks. And here the attacker has even more powerful tools available to him. So at first we were quite skeptical that there will be any secure way how to implement it. But then after thinking hard, we actually found a provably secure way to implement any cryptographic functionality in a ReLU-based DNN. And I'm going to give you the basic ideas now. So first of all, I'm going to change the sanitization function, make it a bit narrower. I need some playground near the 0 and near the 1. So I'll do the sanitization so that it will, for any value below 0.1/3, I'm going to give an output of 0. And then it will go up more steeply, up to 2/3. And then any value of the input, which is more than 2/3, I'll output a 1. This is going to be applied to the inputs or to any plain text bit. When you get an input value, real value, you first of all apply this one, and this can be implemented easily by difference of two values. Next, I'm going to think about what is the region which is still dangerous. So I've already made sure that any combination of inputs, with the exception of values between 1/3 and 2/3, is okay, because I've changed the input to zeros or to ones, and then I'm back to the analog, to the binary case, and I have guarantees there. So the dangerous part is if any one of the inputs is between 1/3 and 2/3, and this is a structure which I call the multi-wall. The multi-wall in each direction is going from 1/3 to 2/3, and if I'm anywhere outside of this multi-wall, I'm safe. The values, the input after the sanitization are going to be stable at 0 and 1s. No other values are possible. So the only dangerous region is in the multi-wall. And now I'm going to use another kind of function which will guarantee that the outputs for any point inside the multi-wall is going to be 0, 0, 0, 0. The ciphertext is 0, and therefore it will not leak any information about the plain text. But I'm restricted because I have to, for 0, 1, 1, 0, etc. plain text, I have to give 0, 0, 0, 1, 1, 0, 0, etc. ciphertext, and I have to change continuously. But the multi-wall is separating the input space into a multi-wall where the outputs will be 0, and into ortants, which are separated from each other. There are 2 to the n ortants. Within each ortant, I have only one point, which is Boolean. And the value in the whole ortant, for example, the one facing you, is going to be determined by a very easy smoothing formula from the one value at the binary point contained in the ortant. So I'm going to have the correct value at the ortant, and then it will just connect smoothly to the 0 on the surface of the multi-wall. It's a bit complicated, but think about it. So this smooth interpolation will not leak any information about the key, because anyone who knows, who is given an input, can calculate what the output should be for that input if he knows what is the result of encrypting a binary input into a binary output by AES. So I've reduced any analog attack into the digital attack. So here is the, we have to use some additional filter functions. We have something which is called rectangle, and then we have mask, which is the sum of rectangles. And this is our secure implementation. I'm taking the plain text, I'm applying input sanitization to each one of them, which will make only the multi-wall the danger zone. Then I'll use any DNN, even insecure, implementation, like the natural implementation I mentioned to you. I take the output, every bit of the output is again sanitized into the narrow region of 1/3 to 2/3. In addition, I'm calculating the other mask based on the inputs. And finally, I have a masking layer, the output, which calculates ReLU of the original output after sanitization minus the mask. And for a reason that I'm running out of time in order to explain, you can show that this is provably secure in the sense that any attack, any analog attack on this particular implementation is not going to reveal any information about the key, which cannot also be obtained by being able only to ask binary questions and obtaining the binary outputs from a normal implementation of AES. Okay, so I'll just finish now. So the extra cost of the implementation, even though it looked a bit complicated, is trivial. It adds a constant number of additional layers, only 2 additional layers, and a linear number of additional ReLU-based neurons. And therefore, it is very easy to apply whenever you have to implement cryptography on a deep neural network, and it's completely practical. Conclusions. I think that this talk should open a new field of research about what does it mean to take a cryptographic functionality, which is only defined for zeros and ones, and apply it in a world where both the user and the attacker are allowed to use intermediate values or values which are outside the range. And we have a new tool set that deals with it. I defined the notion of natural implementation of schemes using corner functions. I demonstrated the insecurity of all the natural implementations. And finally, I described a different non-natural implementation, which is provably secure. Thank you very much.
Great, maybe we can take 1 or 2 questions. Actually, while people walk up to the mic, maybe I'll ask, so you described how this applies to symmetric ciphers. Do you think you can implement public key algorithms?
Okay, so in our paper, we describe, for example, what happens in signature verification algorithms. So in signature verification, the problem is not divulging information about the key because it's a public key. The problem is different. You have an algorithm for verifying a signature, which is giving 1 if the signature is correct and 0 if it's incorrect. Now, maybe someone will find a message in the signature where the signature is 0.2, 5.3, etc., which when applied, when computed by the signature verification algorithm implemented on the DNN, it will output 1. So we can actually show that our techniques can also solve this. Incidentally, it prevents you from having any input, which any signature, which when evaluated will give you a value smaller than 1. And if there is another value, S prime, which is going to give you a value larger than 1, by continuity, there must be a point in between that is going to give you a value of 1. And therefore, clearly, if you have an implementation of a signature, where for some signature it will give you value smaller than 1. For other input, it will give you a value larger than 1, I can cheat. So there are all kinds of interesting questions there. Yes.
Oh, thank you. My question is, so your fix to the analog attack is also using an analog computer, right? So you're using
the same
technology values. What if that is now implemented using floating point on a digital computer? Like, do you see a problem there with the fix being not analog anymore?
No, I don't see any problem, but I assume that you have the ReLU because in order to implement my solution, I was using sanitization, which was a ReLU, etc. So I assume that you'll have linear combinations and ReLUs implemented on a digital computer with floating point arithmetic. It will work exactly the same as a real analog computer.
Okay, thank you.
Thanks for a very interesting talk. I had a question regarding, do you have any idea on the computational efficiency if you implement cryptography into a deep neural network?
Okay, so let's do the analysis. In order to implement one S-box, each one of the 8 bits of the S-box required 128 corner functions. A corner function is a single ReLU. So I need, for one output bit from the S-box layer, I need 128. There are 128 outputs, so it's 128 squared. So it's 2 to the 14, 16,000. When you have 10 layers, so it's 160,000 neurons. It's considered a fairly small network. We actually implemented it, I forgot to mention, all our attacks were implemented and ran with 100% success rate on a PC.
Thank you.
Thank you, Adi. I'm going to go out on a limb here. Do you think that this is somehow related to the hardness of integer programming versus linear programming?
Whenever you move from the domain of integers to the domain of real values, the world becomes completely different. I can give you many examples. Linear programming versus integer programming is only one of them, but there are many additional examples where moving from one domain to the other makes the problem either much easier or much harder. So it's part of the same phenomenon that whenever you do domain extension, you have to reanalyze what's going on.
Okay, one last question, and then we'll break.
This will be a quick one. Thank you. This is a really cool talk. I'm very, very excited for the paper to come out. I'm definitely going to read it. But
the paper is an e-print, right?
The paper is in e-print.
Oh, okay.
We uploaded it a few weeks ago.
Oh, nice. I just wanted to ask a very, very silly question. Oh, well, I don't know. Just why would you want to run AES in a DNN? Where's this field going, do you think? Why would you do this?
Very good question. And the answer is that I can see many situations in the future where the DNN will be the main thing on which we are going to work. LLMs are implemented as DNNs. All the agents, new agents are implemented. Some of them are open source. You can download them, are implemented as deep neural networks. Now, why would you want to use cryptography? Because you may want, for example, to encrypt the input. You may want to verify that the input was given by an authenticated, from an authenticated source. You may want to, if you are trying to apply an instruction, you have DNN implementing an agent which has the capability to erase all files from your computer. Maybe you want to authenticate that this is indeed a legitimate instruction rather than something that a hacker gave in order to eliminate all files from your computer. So I can see many situations in which if you are given DNN, now you can implement in a secure way all the cryptographic functions directly on the DNN without having to go to another model of computation, get the result, and then give it again to the DNN. Thank you.
Terrific. Thank you, Adi. That's... Okay, so with that, we end the morning session, and we'll break for lunch, and we'll resume at 1:35. See you here then.
having too much fun talking to the speakers. So I'm really delighted to invite Rehan and Haris up to speak about their work on deploying homomorphic encryption technology at kind of billion device scale.
Thank you. Hello, everyone. My name is Rehan. I manage the machine learning, cryptography, and privacy group here at Apple. I'm joined by my colleague Haris. And today we will talk about how we are leveraging HE to power a bunch of different features that are running at scale on over 1 billion devices. Okay. Maybe this one.
I think clicker is not working. Okay, something will.
Ah, perfect. Let me go back 1 second. Am I pressing the wrong button? Nope. This one. Okay, perfect. Cool. So where we've seen a use for this stuff is there are a lot of on-device experiences that can either be enabled or enriched with information from servers. But whenever we start thinking about these features, we look at what data might potentially need to leave the device, how privacy sensitive is that data, and then how can we best design a system that protects that data's privacy. And in all these cases, homomorphic encryption is a primitive that shines through. Because of its ability to compute unencrypted data, it's able to retrieve information from a server privately. So for example, the first feature on the slide is private live caller ID, where we're able to identify real-time caller information for incoming phone calls from an index on the server to identify either registered businesses or, more importantly, spam phone numbers. And then we can notify the users, we can block the stuff on device and protect our users. And we do this in a way where the phone number is not revealed to the server. The second feature on this slide is called enhanced visual search, where we improve on-device photo search by privately tagging images for domains that are pretty hard to do just on device, such as global landmarks and places of interest from all across the world. And we'll do a deep dive into this feature to explain the system better. Finally, the third feature on the slide is categorization for email senders that are registered businesses with Apple so that we can better organize and categorize your mail. So as you can see, there are a bunch of features that can use this information from servers to improve the experiences on device. Now, we need to do this in a way where we have a formal Apple privacy commitment where any data that leaves your device, any client queries, they remain private even from Apple. However, we need to do this in realistic practical constraints. Because we have such a large device population, we're probably hitting tens of thousands of queries per second. So there's really high throughput. And then the communication cost for each of these queries should also be within, let's say, less than 1 megabyte. And on the client side, we need to be enabling these features where the client storage per feature is relatively cheap. And we need to build this in a way where the user experience is high quality. So we need exposure to all the information we can from the server. So to better explain the system, let's do a feature walkthrough through enhanced visual search. As I mentioned, we're improving on-device search for domains that are really difficult to classify with just an on-device solution, like landmarks and places of interest. And so imagine you've gone on a holiday, maybe even this conference here, and you've taken lots of photos, and you want to be able to recognize these photos and search for them at a future point in time. And so before this feature, let's say we want to search for the Chapel Bridge, the picture in the middle. And so before this feature, how you would go about doing this is you would search for a generic class, let's say monument or bridge, right? Or possibly a location where this was taken, let's say Lucerne, or a neighborhood in Lucerne when this was taken. And you would get many search results, and then you'd have to scroll through them, and you would get to the photo that you wanted. And we termed this as poor search recall because the actual result was much further down in the list, all right? And so we can improve this experience if we could tag this image with the exact location that was needed, and then you get all the search results as you see right on the top of your screen. So how do we begin? Let's say we have this image where there is a landmark in it. The next, there's an on-device machine learning model that scans through this image and detects a region of interest with a potential landmark. There's another machine learning model that runs only over this region of interest and says, okay, there's this landmark. I'm going to convert this into something called an embedding. And let's zoom into what this embedding is, because this is going to be the primary computation for our HE compute. So simply put, an embedding is generated by a machine learning model, and it's a float vector of fixed dimension. But the special property here is that it maintains some semantic meaning about the input, and it does this in a way where similar looking images are closer together in this embedding space, and dissimilar images are further apart. And so we can compute the similarity with a bunch of different metrics. The one that is sufficient for our workflow is just a simple dot product. And so here's a setting. You have this query embedding for the input image, and then you've generated an embedding for each entry in the index. And so you just take this embedding, you take all the embeddings from the index, you compute the similarity score, and you tag the label for the maximum score from the index back to the input image. Okay, and so in this case, Chapel Bridge is the second embedding, and so you take that, and then you label the input image with the label associated with that entry. So there's a trivial approach, which is perfectly privacy preserving. You take this entire index, and you download it down to the device, and then you're going to be processing all these queries completely on device, right? And then you have the tags available. You can put that next to the image, and they are available for search. Perfectly fine. And this is encouraged for small databases. But the domains that we are interested in is where these indexes can go from 5 million or like single-digit million to tens or hundreds of millions of entries. And what that means is just to power one feature for one domain, you would potentially need to sync gigabytes or tens or hundreds of gigabytes of data. Additionally, the embedding itself is probably not enough to make a decision. For example, there can be temples that look quite similar to each other. There can be bridges that look quite similar to each other. And in these cases, you need additional signals like the location of the entry in the index, a popularity score probably for something that's more popular, the locale where it's present. And all of this means you have additional metadata per entry, which is some number of bytes per entry. And so again, the database size grows prohibitively. Finally, these databases are dynamic. You can have new entries, you can delete entries, you can update the names of places, et cetera. And so syncing all these changes to over 1 billion devices is operationally very challenging. And so we do realize that we need to send this embedding off the device to power this feature. Because in this trivial approach, yes, we are definitely meeting our privacy commitment. We are meeting server constraints because you're just syncing the stuff once on device. However, we're not meeting our client constraints of a small storage and this high quality user experience. So in a setting where this needs to be sent to the server, what are you doing? You're converting this embedding, sending it to the server, you're computing this dot product server side, and you're syncing the label back down to the device, all right? And the question is, why is there a privacy issue here? You're just sending this embedding. You're not sending actual photos data. However, there's been a lot of work where there are a lot of efficient reconstruction attacks that suggest that just from the embedding, you're able to recover almost all of the input data. And so we do really need to protect this. This is very privacy sensitive. So one candidate approach is you can just use HE directly. What do? You encrypt this embedding with a secret key that stays on the device, send this encrypted embedding to the server, compute all these scores in the ciphertext space, and then you get all these scores down to the device where you decrypt them and you select the maximum score. Great, this is possible. And one of the state-of-the-art approaches that did this when we were putting out the system is called Tiptoe, which is, it does this relatively efficiently for an HE scheme. It offers full query obliviousness for privacy. And yeah, it's a great system. However, it falls short of our practical constraints, where we need to serve tens of thousands of queries per second. More critically, the communication cost for this scheme is around 17 megabytes per query. And so it's prohibitively expensive from a server point of view, but also from the client. You're generating 17 megabytes of communication for each query. For each feature, you can have tens or hundreds of queries. And so the cost on an iPhone is really, really high. And so that's where this becomes impractical. And so we need to think about this maybe slightly differently. And yes, it maintains Apple's privacy commitment. It maintains some of the practical system requirements, especially on the client where there's a small storage. And there is a high quality experience because you have access to the whole database. But like I mentioned, it's falling short of our server constraints. So we know there are two problems. We know there's this high computation problem, and we know that there's this high communication problem. And we solve this in two different ways. We use differential privacy to access some subset of the whole index. So that helps with our computation cost. And then we also leverage some cool optimizations in our HE scheme, which helps with the communication cost. To cover both of these, I'm going to hand it over to Harris.
Thank you, Rehan. So as Rehan said, we propose two-step solution. Let's look at how we reduce the server computation by using differential privacy first. At the setup stage, the server used the standard machine learning technique of clustering to first divide the entire index into the clusters. Then, at the time of the query, let's look at this simpler protocol. The client is only going to find the nearest cluster, send that, and the client can do it just by using the centroid sent by the server. Client is going to send this centroid to the server, and server's response is just the entire cluster back to the client. So note that this scheme already improves over the previous scheme where the client was sending the embedding. However, it still doesn't provide a strong privacy guarantee because the server is learning the nearest cluster. And just by learning the nearest cluster, the server might be able to know some information about the client query. For example, here, if the server knows that the client query falls in cluster C2, it may learn that the query is something about the bridges. So we want to suppress that information. So now we have another problem. We get rid of the embedding, but now we have a problem that the centroid, the cluster themselves reveal information to the server. We have this observation that in a large-scale system, something like at the scale of Apple, there are many users are making the queries at the same time anyway. So we can try to hide the client's clusters, which is a query, into the query batch of queries made by the other clients. So in other words, we propose a scheme which trade off efficiency for privacy, which provides a worst case privacy leakage through clusters, and which guarantees epsilon delta differential privacy at a user level with respect to users' entire photo library. So before I go into the details of this protocol, let me explain to you that how the intuition of the privacy provided by our scheme. Let's imagine two worlds, one on the left, where many users are making the queries to the server, and one on the right, where a particular user may not be making the query to the server. And the privacy guarantee provided by our scheme is such that the view of the server in both these worlds are similar. In other words, the view of the server's advantage in inferring the client's query, whether the client participates in a protocol or not, is bounded by e raised to power epsilon. And we selected epsilon equal to 0.8 and delta equal to 10 raised to power -9, which is quite stronger guarantee. Okay, now let's look at how we achieve this privacy guarantee. So our protocol consists of 4 steps. First, we assume that the protocol is going to run in an epoch. Every epoch, many clients are going to make a query. Second, we require anonymization. So for this, we require all the client queries go to the server through the anonymization network. We specifically use oblivious HTTP, which removes the identifiable information such as IP addresses from the client queries. Now note that even though we have anonymized the queries, but server can still might be able to link a particular query to a client. For example, if server knows a particular cluster can be accessed by a certain demographic, just by observing that that cluster has been accessed, server might be able to decipher the identity of these queries. So we require additionally each client to make certain number of fake queries. Every client is going to sample number of fake queries it is supposed to be making through a negative binomial distribution. Note that adding more fake queries improves the privacy, but we were able to find a sweet spot which does not affect too much performance. Concretely, for every real query, every client is required to make 1 or 2 fake queries only. And making a fake query is very easy. All client has to do is pick a random cluster and send it to the server. Another potential leakage can be through the timing channel. So for example, certain clients may be making the queries always in the start. That will reveal to the server who are these clients. So we want to suppress that leakage as well. For that, we require every client to pick a random slot or a random instance within an epoch for a real and fake queries, and only make the requests on that random instances. Note that for many online use cases, this may not be ideal, but for the offline use cases, such as photo tagging here, this is okay because they are delay tolerant applications anyway. Okay, so in the paper, we have already uploaded the paper, which gives the proof that by following these steps, it guarantees epsilon delta differential privacy. Here, I would like to give a little bit high-level intuition of the proof. First, we show that the server's view in a single epoch is basically a noisy histogram of clusters. Then we show that the noisy histogram provides epsilon delta differential privacy in a central model where a single curator is talking to the server. And then we show that malicious server gains no extra advantage in a distributed model where many clients are making their queries to the server. So this is for a single epoch. And then we calculated the total privacy by using the advanced composition theorem for across all the epochs a user is going to participate. Okay, so this scheme is good, that it protects the privacy, but many of you might have already noticed that it has a problem, which is that the server responses the entire cluster. This is fine for small clusters, but for the larger clusters, note that this response has become prohibitively high. So we want to compress that. To do that, we use HE. Let's quickly go over that. At a high level, for any real or fake queries, now client is going to send encrypted embedding, which is encrypted under HE to the server in every query. For this, we use BFV HE scheme, which supports ciphertext vector operations. Okay, so client is going to send that query to the server. Server will compute the encrypted scores and send all the encrypted scores back to the client. Note that because of our use of efficient packing scheme, all the scores, we were able to pack them into a single BFE ciphertext. So our response is only a single BFE ciphertext. Okay. We further use many other HE optimization. Here I'm going to touch few of them. But to understand that, we have to look at under the hood of HE ciphertext that we have implemented. In our implementation of BFV, each ciphertext consists of two RNS lim. If you zoom into the single slot of a ciphertext, you notice that the scores are at the higher order bits, noise is at the lower order bits. So in other words, useful material is in the higher order bits. So first we use a standard technique of modulus reduction, which allow us to get rid of one of the RNS lim in the response ciphertext. Then we further drop the least significant bits of the remaining lim. Note that dropping these bits does not affect the security of the ciphertext at all. However, it introduces some kind of decryption error, but we carefully monitor this decryption error and only drop the bits when the decryption error is almost negligible. Okay. We also did some other optimizations. Due to the lack of time, I'm only going to touch two more. First is we improved the server compute by realizing that a lot of this BFE operations requires modulus reductions repeatedly. So we don't have to do modulus reduction after each operation. We always allocate a slightly larger buffer and only do the modulus reduction after the buffer overflows. And the second optimization is we propose a plaintext RNS to reduce the size of evaluation key. Note that every BFV ciphertext or a computation requires client's evaluation key to be present at the server. In normal HE computation, this is fine because server can just store it and can reuse it for all the computation. However, in DP, we require anonymity, so which means that the client has to create a fresh evaluation key and send it freshly with every real or fake queries. So evaluation key is basically the communication bottleneck. So by using RNS, plaintext RNS technique, we were able to reduce the size of evaluation key by around 4x. Okay, so here are some exciting results which we were able to achieve by combining HE, DP, anonymization network. The first thing is that we were able to achieve a QPS of more than 25,000, and our communication is only 0.5 megabyte. So in other words, we were able to achieve significantly better performance than what we would have been if we only use HE. So now to wrap up my talk, before going to wrap up this talk, you can see that all our proposed approach does provide the standard guarantee of privacy. And it nicely meets both of the client and server constraints. Now, to wrap up our talk, I'm going to hand over back to Rehan. Thank you.
All right, thanks, Haris. So all the optimizations that Haris talked about, they are open sourced for our server implementation on Apple's GitHub as part of Swift homomorphic encryption. And so it's auditable. These contain all our optimizations, and feedback is absolutely welcome through GitHub. Similarly, on the client side, all our code lives inside core crypto. And again, that means it's auditable. It includes all these optimizations, and it's available at developer.apple.com/security. So to summarize this talk, we have been using HE to enhance on-device experiences that would not be possible without it, with information from the server, and there's a real need for this on Apple platforms. We are able to do this in a way where we're leveraging HE, combining it with other technologies, and we're able to deploy this for several features at scale, right? On over 1 billion devices. And the important takeaway is that maybe HE itself is not enough. You need to combine this with other privacy technologies that are available in our toolkit. It could be differential privacy, it could be anonymization networks. One thing we didn't talk about here, but we leverage this in our private live caller ID solution, is we also use privacy pass for anonymous tokens. And so we need to take all these technologies that we have available, combine them into an end-to-end system that can deliver privacy for our users. Now, we have a bunch of public documentation and resources that goes into everything that we talked about. Like I mentioned, our code lives on Apple's GitHub. There's a high-level overview in a blog post that's available that talks about all the features I just mentioned. The proofs are in our technical paper, and because caller ID is available for third-party developers to integrate as well, there are some developer docs on how they can incorporate this into their apps. And with that, yep, thank you.
So maybe I have time for one quick question while Christian comes up to set up.
Thank you for the really nice talk. I have a question. Are embeddings composed of floating point numbers? And what did you do? Well, how did you deal with that?
Embeddings are composed of floating point numbers. Like I mentioned, it's this like fixed dimension of these numbers that plays very nicely with other machine learning models. And I think your question is, how are we using that within HE? Like, how are we dealing with the issue that they're floating point numbers? You want to talk about how we convert them?
Yeah, so we realized that we did experimented with the efficiency and see, we realized that if you keep like the few bits, like rather than the whole floating point, if you scale the embeddings to few bits, that's sufficient enough to retain the performance. So for example, we keep to 4 to 8 bits for each.
Did you consider to use different schemes like CKKS?
Yeah, definitely we are considering that. However, note that there are, as Rehan mentioned, there are several use cases within Apple we are using at the moment, and we figure out that BFE was suitable for most of these use cases. But yeah, definitely we are looking at CKKS.
Thank you.
All right, let's thank the speakers again. All right, so our next speaker is Christian, who's a PhD student at EPFL, co-advised by Alessandro Chiesa and Carmela Troncoso. And he's worked on zero knowledge, fully homomorphic encryption, but today is going to talk about something real world in a very different way, which I'm very excited to see.
Okay, I think I'm all set up. Thank you for the introduction. So I want to talk about a privacy-preserving A distribution system with assessment capabilities. That's kind of a long title, but really I want to use this as a case study on threat modeling and system design. This is joint work with Lucy Chin at Georgetown, my advisor, Camilla Troncoso from EPFL and MPI-SP, and in collaboration with Justina Sukaitis and Vincent Graf-Narbel from the International Committee of the Red Cross. So we care about humanitarian aid distribution. So humanitarian aid organizations do aid distribution in the wild, and in particular, they distribute, for example, food, money, or medicine to populations. And historically, this has been mostly a manual process, which, as you can imagine, may be small, It may be slow, it may be error prone, it may be costly. And so there's been a very strong push from these organizations and their donors to digitalize the process with the hope of having a more scalable and a more effective aid distribution. So just naively digitalizing the existing workflows is very risky because these organizations enjoy a very high level of trust from the populations they serve. And in particular, they have very high access to very sensitive information. For example, the size of the households, biometric data, or your appartenance in an ethnic minority. And all those informations, in turn, they may be used, and in fact, they have been used, unfortunately, in the past, to cause harm to the populations that the aid organizations serve. So in order to kind of address these challenges, some of my former and current colleagues in Camila Troncoso's lab have developed end-to-end systems that are both kind of scalable and digitalized, but also provide strong security and privacy guarantees to, in this case, allow more effective humanitarian aid distribution. Today, I want to focus on kind of an extension of this. So we went to the ICRC with these projects, and the response was, oh, this is amazing. You have kind of these optimal privacy guarantees that we can rely on. But in practice, we also need to, well, maybe know whether the distribution was actually successful, whether we reach the right people, whether we do not discriminate against different subpopulations. So in practice, they needed some additional assessments on the side. And this isn't specific to the aid distribution setting or just the humanitarian setting. This is something that appears all over the place, right? Real-world deployments, whether they are just standard deployments or privacy-preserving deployments, need assessments. For example, for correctness, because debugging fully opaque systems is very hard. If you've ever tried to develop and debug an FHE pipeline, for example, you know what I'm talking about. It's also useful for transparency, for example, towards the users, towards the donors in this case, to make sure that the funds that are donated actually go towards aid distribution and not somewhere else. And finally, in some cases, also for legislators, for issues of transparency, of fairness, and of equity. It's also very useful just for planning. It's very unlikely that the very first version you put into the world would be the one that will be optimal for the entire lifetime of the application. And so having assessment allows you also kind of rectify and optimize ongoing deployments. So that's kind of the motivation and where we want to go. We have this kind of core privacy preserving system that does the aid distribution. And now we somehow want some additional assessments on the side. And for now, the assessments are kind of vague. We want maybe some statistics on who's coming. We want maybe some attributes. There's a notion of group. Maybe there's like a duty of care. But this is all kind of very vague. So I want to walk you through how we typically do requirements gathering, how we go from this kind of very fuzzy high-level ideas to something much more formal that we can use to then do designs. And in particular, I want to talk about how we do this. We have a bunch of tricks that we have come up with over the years to do this efficiently and from first principles. So how do we start? Well, obviously, we talk to people. In particular, in this case, we talk to the Data Protection Office, the people that do data management policies and compliance. We also talk to program managers. These are people that orchestrate the deployment from the headquarters. And we talk to field employees, the people that actually do the distribution. These are the end users of our kind of assessment system. Ideally, we would have loved to also talk to the recipients themselves. It turns out your university will not let you go to a disaster zone in order to do interviews, but in general, you should really try and talk to the end users of your system. So we go to them and we talk to them. What do we ask? So, just going to them and asking them, oh, so you said you want some kind of assessments. What exactly do you need? That is not very helpful in practice because we typically get one of two answers. One typical answer is we want everything. We want an end-to-end system that does everything that the ICRC ever does, and also does impact reporting and compliance, and also uses military-grade encryption and is post-quantum. Or what we also get is, well, we want exactly what we have now, right? We have this pen and paper system that just works. So just do this like digitally, faster, and also private. And you can see how this is kind of very difficult to extract precise requirements for design. So what we found instead is to ask, how do you do things to be much more useful? And this might be either really shadowing them through their work, so looking over their shoulder as they do their work, or in this case, asking them very precisely. So you arrive at the distribution station, you sit down at this plastic table, what do you do? Somebody arrives, concretely, what do you do? And this is useful because it allows us to very precisely scope down the functionality, particularly not to look at, okay, what information do you think you need, or what information are you collecting at the moment because of the current workflow, but what information are you actually using to do your job? What is the minimal functionality that we need for you to be able to do what you need to do? It's also useful to not restrict our design space because cryptography is very non-intuitive to cryptographers. If you try to go on a random person on the street and you ask them, oh, you know, there's like this zero knowledge property and you have like these one-way functions and we can do encryption, but also homomorphic, they're going to be very confused. And so what we found is that when people implicitly in their head try and kind of design ahead and build a system, they will often mimic physical things that they have access to. And these things do not have all the power that we have from cryptography. And so asking them what they need instead of, or what they do, how they do things, rather than what they need or what they want, allows us to then have a more open and flexible design space later on. And finally, it's useful to set boundaries. We typically design small, well-scoped systems, in this case, a distribution and kind of corresponding assessments, which is just a very small thing, a small part of what the ICSC does as a whole. And in particular, this allows us to put the human in the loop, to know where a system ends and where there should be somebody who takes management decisions or handles edge cases. So, you know, we do all these things. We have some functional requirements. We know what we want to do from the functionality. And then we need to do threat modeling. What kind of security property do we need? What is the adversary? And again, in the past, we used to just go to them and ask them, oh, what is your threat model? Turns out people are very bad at threat modeling, and this includes people who do security for a living, see all the attack talks at this very conference. And in particular, when we go to people and we ask them, oh, so what are you worried about? What are the things that, you know, make you stay awake at night? The Data Protection Office might have concerns such as privacy regulations as an existential threat to the organization. Program managers might have a more geopolitical kind of worry, you know, maybe armed militias kind of taking over stations on the ground. And the field employees, they are very pragmatic. They only care about people getting their aid and not getting sick or hungry. So, you know, you go, you ask them, they have all these things. How do you synthesize a property that looks like, you know, for all polytime adversaries, something's very difficult. So what we found instead is to break down this threat modeling process into smaller chunks that we can then tailor to the different stakeholders. So in the first step, we ask them who might interact with the system. What are all the parties that are floating around? Here, this would be maybe the recipients, the headquarters in Geneva, the internet service provider, the nation state in which you're operating, and so on. Then at the second step, we try to figure out what information might the system need. So imagine the system is a black box. Some things need to get into the black box. Some things need to get out. What kind of information do you need for the functionality to make sense? And this is often a much more collaborative back and forth between us and them to really figure out, okay, what do we care about in this environment? And here might be, you know, maybe biometrics, might be the entitlement, how much aid they're allowed to receive, maybe some information about them. For example, is this recipient pregnant or not? Are they part of this ethnic group? And so on. And then the third, to arrange those into a matrix. So we look at each piece of information and each party, and we ask what concrete harm happens if this piece of information leaks to this party. And we can tailor this to different stakeholders. So we can ask, for example, somebody in the Data Protection Office, what happens if the contact information of your recipients on the ground gets available to the headquarters in Switzerland? Does this have privacy implications on regulations or compliance? Or we could ask to people who work on the ground, if the fact that this recipient is pregnant leaks to the internet service provider in this country, do you see a concrete harm? And this allows us to map out a bunch of harms and also quantify exactly what kind of harm happened for different kind of configuration in the system. And as part of these, we'll mark some of them as fundamental harms and fundamental leakages. So these are things that will kind of leak because of the functionality itself. And this is important because everything that we deploy comes with some non-zero amount of risk. And knowing the fundamental harm, they will happen regardless of the instantiation. They will happen regardless of how much crypto or how much trusted hardware we throw at the problem. These are indifferent to your goal. So once we've had that, we have a pretty good risk analysis, and this is where we typically go back to the stakeholders and ask them, do you want to deploy this? Do the benefits that you see from the system outweigh the harms that we've now developed? Or should we just cancel this and never get to the design stage? And in some cases, this doesn't make sense. In some cases, the harms are just too high, and the benefits are not worth it. In some other cases, we have actually some benefits that outweigh the harms, and we can continue to the design. And then this is also very useful for us to understand what pieces of information do we not need to protect, right? And this, roughly, you can think of this as being the trivial wins that we will use later in our security games. So that is threat modeling. And then we get to the fun part, which is addressing all the remaining red boxes. This is where we can use finance and fancy crypto or other privacy enhancing technologies to address the remaining harms. So we did this process for the specific requirement, for the specific use case, and I want to walk you through the requirements that we came up with, and then I'll go to what we actually built of the system. So maybe to set up the stage, in the system we have 8 recipients. They go to a registration station, and they show either the biometrics or some other piece of identification. If they are deemed eligible to receive aid, they receive some tokens. And then these tokens can be redeemed at the distribution station in order to get some aid. This can be food, medicine, or money. And I mentioned that we want these assessments. So we have kind of 2 kinds of assessments. First one are queries of the form, what percentage of pregnant aid recipients successfully claimed aid in this distribution? And these things are used, for example, for transparency, for impact reporting, or for planning to understand if they are kind of discriminated against or if there's something that prevents them to claim their aid. On the other side, we have more complex assessments, and these might be queries like, can you reveal the contact information of all the recipients who are both above the age of 60 and also haven't been claimed aid in the last 3 distribution stations? So we need to talk about multiple different previous distribution periods, and we also need to talk about people, for example, not showing up to a station. In particular, people who might not be able to engage in any kind of protocol because they were not there. So these are the kind of the functional requirements. This is the functionality that we want to achieve. How do we do this in the kind of restricted model of the humanitarian sector? So we have some additional deployment requirements, for example, on computation. So aid recipients typically only have access to maybe a phone at most. In some cases, they don't even have access to any kind of computation platform. So we need to provide them with a very lightweight computation platform, for example, a smart card. The stations, they typically have laptops, so you have like some limited amount of computation that you can work with. In terms of communication and connectivity, aid recipients, we typically cannot assume that they have any kind of connectivity, save for maybe a Bluetooth connection where they physically arrive at the station to communicate with the laptops. The stations themselves, they typically have limited connectivity, think like a spotty LTE connection or maybe a satellite phone line. And then finally, there's an efficiency requirement, right? The whole reason to do this process was to also have a system that is kind of digital and more scalable. So the system in particular should not slow down the distribution process. And this is not just like a nice to have efficiency property because otherwise users get annoyed. In some cases, it might be a security property as well, because as you can imagine, a distribution might happen in a very kind of constrained time limit. For example, there's a ceasefire and you need to be distributing all the aid before the ceasefire ends. And in this case, every minute that you spend exchanging cryptographic material is a minute where you put the employees and the aid recipients at risk. So those are the deployment requirements, things that we kind of have to deal with in order to design the protocol. In terms of security, we have kind of roughly an enforgeability and the privacy requirements. It's kind of very high level, so I don't want to go too much into detail. There's a bit more nuance in how we do this exactly, but it's kind of the typical thing, just kind of specialized thing. And what I want to talk about more is these kind of meta requirements that we also have to have. These are maybe more specific to the humanitarian sector because of a kind of inherently chaotic deployment environment, but I think these are also applicable in general to other settings. And the first of those is some kind of agility requirement. So when we put a protocol into the world, we kind of design a threat model, or we have a threat model against which this is kind of proven secure. But especially in the humanitarian sector, the situation in the ground might change very rapidly. There might be an armed militia kind of coming in that you didn't really kind of intended to be there. And so now suddenly your protocol is kind of invalidated. Your threat model is invalidated. So what you want to do ideally is to be able to either safely deploy a stronger protocol that may be slower, less efficient, but is secure against this newer threat model, or to safely shut down the existing protocol. And we should, in the case of the shutdown, we should also do so without impacting the rest of the system. For example, here, maybe we want to shut down the assessments collection and evaluation, but still keep the distribution running. And kind of as a dual property, we have something that we call graceful degradation. So in the period between you detecting that the threat model has been invalidating and the protocol being kind of deployed or shut down, your protocol will fail. It will not be fully secure against this new threat model. But it shouldn't fail catastrophically. It should maybe do minimal harm. And the way we achieve this in practice is by looking at each protocol and each threat model and deriving the harms, the concrete harms that derive all the stronger threat models that we can think of. So those are all the requirements that we have with. Now, let's get to the tip of the iceberg. So now this is the thing that you will see in the paper. So we have a privacy-preserving aid a humanitarian aid distribution system with assessment capabilities. Our starting point is functional encryption as a very natural paradigm to use to collect statistics and evaluate them once. However, there's a very simple attack, which stems from the fact that in FE, you can evaluate many different times. And in particular, in the setting, the adversary is allowed to can evaluate this FE evaluation for different subset of inputs. So you can do a partitioning attack and learn more than you would expect it to learn. How do we counter this? Well, we define this notion of one-time functional encryption that only allows a single evaluation. And this turns out to be enough for the semi-honest case. And for the malicious case, we additionally need to bind cryptographic material to some piece of physical inventory because we have some control and some auditability of the physical goods. And then we can use a predicate version of our one-time functional encryption primitive to achieve the result. Finally, we show how to instantiate this using public key encryption signatures and then either 2PC or threshold homomorphic encryption. And we also derive the harms. So just the system existing may lead to discrimination or leakability because now you're collecting statistics about people. That concludes my talk. I need to thank many different people that have worked with and around Camilla Troncoso to kind of really scope out all of these protocols and without whom this talk wouldn't have been possible. Thank you.
Time for a couple questions.
Hi, thank you for the talk. This is very interesting and indeed a very needed solution. I'm wondering how you're thinking of tackling the actual lack of internet accessibility in the aid places and clinics and so on.
So we have to work around that, right? So we use very lightweight primitives. So the base system that was designed by some other people uses anonymous credentials. We can kind of issue relatively efficiently at the stations. And to collect statistics, we use a lightweight form of threshold encryption, for example, where you just encrypt a bit, and then you can kind of collect those. And this turns out to be just enough so that you can exchange this using a Bluetooth connection, for example, when you arrive, or by scanning a QR code.
Thank you.
All right, so let's take one more quick question.
Thanks very much for the great talk. In some regions or situations requiring aid, the deployment of any technology or aid system may in fact be dependent on the approval of the aggressor party. And so have you considered this as part of your threat model, especially in situations where that aggressor may demand, for example, access to data or modifications to the system simply to allow it to be deployed?
Yes, so this is one of the big concerns we look at, and especially the system is designed such that there is, for example, no centralized store of information that you could even leak, right? So in the base system that we start with, these anonymous credentials, there's no centralized list of who has access to aid. People arrive, the entitlement is checked, they get a credential, and then they don't exist anywhere in the system. So that's one example where you can address this and remove information. And same here, you would only really collect the statistics, and you would aggregate those and thresholdize those to make sure that they're kind of safe to output potentially.
Great. Thanks, Christian.
Thank you.
All right, so our next speaker is a principal scientist at Science Laboratories, was a postdoc with Claudio Orlandi, a student of Abi Shalat, and has done a bunch of influential work on threshold ECDSA. So very looking forward to the talk.
Thanks for that really nice introduction. So this is joint work with Nidish Bemrajka, Daniel Noble, and Supreet Varadarajan. Okay, so I'll begin with a quick introduction to the account aggregator ecosystem, which is an open finance framework in India that's regulator-driven. I will talk about some gaps that we've identified in this context in terms of trust and incentives. So we will show that we can use MPC as a way to mitigate some of these gaps, to mitigate some of these problems. In particular, we're going to address concerns of data duplication and come up with a more fair compensation model for all the actors in the ecosystem. And I'll also discuss our main design principle in constructing these protocols, in particular that of designing a drop-in replacement to decentralize entities that already exist as part of the existing protocol. And I'll talk about why this has been difficult for us technically. Okay, so this is a quick refresher. Secure multi-party computation at MPC considers a setting in which a number of parties have some private inputs and they wish to evaluate some function on their joint inputs. So ideally, they should be able to do this by sending their inputs to some trusted oracle that is able to compute the output without revealing any intermediate state. But of course, such oracles don't exist in the real world. And so MPC protocols let us achieve this effect in a secure manner. So that out of the way, let's talk about open finance. And so open finance at a high level consists of frameworks that enable people to securely mobilize their personal financial data in order to avail of some services of some financial nature. So think about scenarios in which you have to prove your financial health to some third party. For example, if you're applying for a loan or if you're applying for an apartment or something like this. So in a lot of scenarios, this can take physical unverifiable forms, or like other sort of heuristics could be used. Think of using like physical documents to certify your bank statement or something like this, or also think of other even worse things where you have to hand over your banking credentials to some third party that then logs in on your behalf and does some screen scraping or something. So open finance frameworks basically replace these kinds of heuristics with rigorous cryptographic protocols. So the account aggregator ecosystem in India is one such framework, and that's going to be the focus of this talk. It is regulated, albeit indirectly, by the central bank in India. So in this framework, users are able to consolidate their financial information across multiple regulated FIPs or financial information providers. Think of these as banks and so on. And upon the user providing consent, the AA shares a curated view of the user's finances to licensed third parties, licensed financial information users or FIUs. Think of this as maybe insurance underwriters or loan granting authorities and so on. So according to Sahamati, which is the which handles governance in the AA ecosystem, the ecosystem as of last year had over 80 million users, over 100 FIPs, and over 400 or so FIUs. But there are still some issues that pose some barriers to scalability of the system, which I will discuss. So these are the actors involved at a high level: the financial information providers, information users, and the data principal or the users of the system. And the account aggregator is an entity that sits in between all of these and coordinates them. So the first step in the workflow for the account aggregator system is for the user to consent to its data being shared. And upon receiving a request along with the public key from the FIU, the account aggregator forwards these things to the FIP, which then retrieves the relevant data, encrypts it, and then forwards it through the account aggregator to the FIU. And on receiving this ciphertext, the FIU decrypts this data and processes it as required. So if we zoom out for a second and see who puts in what and gets out what, we see that the user provides consent to move its data from the FIP to the FIU through the account aggregator, which basically acts as a pipeline that maps consent to data being available. And the FIU is compensated by whatever business model it has. The account aggregator is explicitly compensated through fees from the FIU, and the user presumably had some reason to initiate this process to begin with. And already we start to see a gap in incentives and that the FIP gets nothing out of the system, at least the way that it stands. But perhaps a more pressing concern is the fact that the FIU gets to see the plain text data of the user. And this can be a problem, especially if the FIU were to be compromised at some point, right? In more detail, if there's, imagine a scenario where there's a data breach or an insider attack or an FIU, or even just a rogue entity operating the FIU, this could result in the data ending up in the wrong hands. So this directly affects users because they lose control over their personal financial information. And also in a larger scale or at a macro level, FIPs are also affected because user data is considered their proprietary data. And having it lost can cause many problems reputationally and also for their business. So this issue has already been identified, and to our knowledge, there are already heuristic solutions that FIPs use to address this problem. Specifically, one that we know of is that they throttle the response rate. That is, they respond only to a fraction of the requests that they get. And on the one hand, this undermines faith in the ecosystem because now this compromises liveness. And on the other hand, this is still a bad solution because data is still leaked. Like there's no rigorous guarantee of privacy or anything. So what we propose is using a more compliance by design approach in this framework. Let me say a bit more about that. So this is our workflow back up on the slide. Let's zoom in on what the single point failure is. It's clearly the FIU endpoint. So our proposal is to replace this single point of failure endpoint of the FIU with a decentralized system that is a network of financial information compute units, each of which are operated by entities that are carefully chosen. And the idea is to have the FIU's role be fully decentralized. So these FICUs get together and jointly emulate a single FIU. So who actually operates these nodes, right? The idea is to pick operators who are naturally incentivized not to collude, such as the FIU itself, the FIP, or a proxy that represents the interests of the FIP, and also the infrastructure provider who's interested in maintaining the credibility of the ecosystem. So this gives us a solution that addresses both these things at once. It addresses duplication. It addresses concerns of data duplication, because now the only way you can access the data is through this MPC. And at the same time, this also allows us to come up with some sort of compensation model for the FIPs, because we can track how frequently data is used and what is used for and so on. And this gives some way of valuing the services that the FIP provides, which is a general problem. Okay, so in a little more detail, what we're proposing on a technical level is an MPC in which there are 3 parties, and we assume up to 1 active corruption. So we're in the malicious security setting. And the ideal functionality that they have to realize is as follows. First, they create a public key and secret key pair. These little box brackets indicate secret shared values. Then through the AA ecosystem, they're able to get a ciphertext that encrypts this relevant data. And then they decrypt the data and operate on it as per their business logic. So the last step, that's operating on the data, is something that can be studied as an independent MPC problem and is not going to be the focus of this talk. What I'd like to focus more on is how the retrieval of data from the ecosystem works. So roughly, this corresponds to this problem of threshold decryption, which is a well-studied problem in the MPC literature. So as a simple baseline solution, you can think of the encryption algorithm being, what if we could tweak the encryption algorithm so that it just directly encrypts secret shares instead of something more that needs a more involved MPC. Right? And therein lies the problem, in that the moment we start thinking about how do we tweak the standards, we run into issues with real-world adoptability. So there's this old cartoon and this old saying on the internet that on the internet, nobody knows you're a dog, which I interpret roughly as being that as long as you follow the protocols as prescribed on the internet and you provide a standard interface and so on, like nobody actually cares what you're doing behind the screen. And like extending this logic a bit, like in the same way, if we're using an MPC to decentralize one of the endpoints, let's say, the rest of the ecosystem doesn't really care that we're doing this. All they care about is that we conform to the standards that apply to everyone, right? And that we're compliant with whatever protocols there are. So this informs our design principle, which is that we acknowledge that the protocol specifications for the ecosystem are set independently of MPC, and we aren't going to sit around advocating that the entire ecosystem change to be more MPC friendly in some sense, right? So we design a solution to be a drop-in replacement for the FIU role as it exists today, so that we can integrate with the AA ecosystem right away. So this is all well and good, but this does cause some problems for us at a technical level. That is, from an MPC protocol design point of view, we encounter these challenges. The first challenge is that now decryption is now a non-trivial function to handle within MPC. The next challenge is that after we've decrypted, even assuming that we've decrypted the data, the result of decryption is an XML file, right? And we now have to parse this XML file into a format that we can actually operate on inside of the MPC. So let me give a quick overview of how this works. So decryption involves 2 steps. The first step is some sort of key encapsulation that's pretty standard. And then the next step is to use this sort of derived shared key to key AES, to evaluate AES. So the first step of the key encapsulation, which is a public key operation, is best represented through the standard elliptic group operations. And the next stage of key derivation is to like hash the resulting thing, which is best represented as a Boolean circuit. And luckily, it turns out that there's prior work on like oblivious TLS and so on that we can borrow some ideas from. And at a high level, what we are able to do, so what we do is we are able to convert these elliptic curve shared values, value shared in the elliptic curve group to value shared in ZP as arithmetic shares, where this corresponds to the base field of the elliptic curve. And then we convert these arithmetic shares to Boolean shares using standard techniques. And then we're able to evaluate these Boolean secret shared values in MPC. Once we have secret shares of the key, we can then evaluate AES securely inside of an MPC. And now the question arises as to how do we do this, or like what's the most efficient way to evaluate AES in this context? Right? So conventional wisdom suggests that using a low latency approach, using an approach that optimizes round complexity usually wins out. That is, if we use garbled circuits, which have, which permit constant round protocols at the expense of a lot of communication, this does suit a lot of settings. But interestingly, in this setting, given that AES is used in GCM mode, all the AES invocations are done in parallel. And so the decryption function for the circuit that corresponds to decryption over here is a very parallel, like a very wide circuit. So as the ciphertext grows in size, the decryption circuit effectively grows in width and not in depth. And what that means is we noticed that rather quickly that for ciphertexts that are just the order of kilobytes or larger than that, the so-called secret sharing based approach where the rounds of the computation scale with the depth of the circuit, like this wins out pretty quickly. So we opt for a more secret sharing based approach and so like think of these BJW, GMW type protocols. Right, so that's decryption handled. Now what about the next stage, which is parsing the data after it's decrypted? So to see why this is challenging, let's consider like a naive way of solving this problem, right? So the plain text that we get after decryption or other secret shares of this plain text that we get consist of a list of transactions that are formatted as shown on the slide. So think about how you would parse this value in plain text, right? The first step would be to identify where the delimiters are. The next step would be to read, between the delimiters to like cast this into whatever structure you want and then use it however you desire. So what if we were to do the same thing in secret shared form? Right, so the first step would be to identify where the delimiters are. We expose the locations of these delimiters. And it turns out that doing this already has an unacceptable level of leakage. Specifically because the length of each field is variable and the length of the field depends on the payload that it carries. This causes some significant issues. For example, the second field over here corresponds to the amount value of the transaction. And just the number of characters required to represent it leaks the order of magnitude of the transaction amount. And so we can't do something as naive as just exposing delimiters and working from there. So the ideal situation would be if each entry were to be padded to some maximum length value so that it's safe to expose delimiters at the very least. To make this a bit more concrete, in this scenario, this would look something like this, where there's some public max row length parameter, and every field consists of some actual payload and some number of padding characters that make the difference between the payload and the maximum length. And so if we had a situation like this, it would be ideal because it would make parsing very simple. And our approach roughly is to construct an MPC protocol that effectively derives a string of this format, or a secret shared string of this format. The protocol is a bit involved, so I'm not going to get into the details so much, but I would like to convey a flavor of how this works. So we begin with the secret shared string, and then we compute using some comparisons the locations of all the delimiters, and that for every index we check if the corresponding secret shared character is a delimiter or not. Using this, we can then compute a relative index value, which is what is the distance between any given character and the last delimiter that was encountered in parsing the string. And with the relative index in hand, we can compute an absolute index. That is, if we were to complete the padding process, what would the index of every given character be? Right? So this is also an easy computation. And after this, we do a similar but complementary thing, which is we start with a public padding array. And using a secure protocol, we figure out which indices of these pads are actually required. So we get the absolute index of the required pad values. And the effect of this is now we have two arrays, right? One array that consists of the locations of the actual payload values, and another array that consists of the locations of the padding values, post-padding. So all that remains to be done once we have these arrays is to securely merge them, because these are basically two perfectly complementary arrays, in terms of indices at least. Yeah, so that's how a secure parsing protocol works. So like this is roughly how a padding and then parsing routine is structured. So this is not terribly inefficient in that it costs a constant number of operations per character, so constant number of additions, comparisons, and share conversions, like the latter being the most expensive, and also needs some small number of shuffles, for which we use a simple custom protocol. And what we achieve is a protocol that has an overall round complexity that's independent of the size of the file that's being parsed, which is useful. But still, at the end, this ends up being the most expensive component of the gadget that integrates our MPC with the account aggregator ecosystem. So while this is the most expensive part, it takes, I think, from what we found, on the order of a few minutes, a few minutes to process a relatively small encrypted bank statement, but nonetheless an encrypted file that's obtained from the actual account aggregator API as it exists today. There is, of course, plenty of scope to improve the protocol design and also to tighten our implementation and so on, but we do already have a pilot deployment in the works with multiple partners, including an FIU, a technology service provider, and also a service provided by Samati, which is the regulator for the ecosystem. Right, so to conclude, open finance frameworks are increasingly used worldwide, with India's account aggregator framework being one such example. And we showed that certain gaps in these frameworks can be plugged using an MPC-based solution. So this is not a problem that's unique to the account aggregator ecosystem. This is really a concept that can be generalized to different jurisdictions and so on, under more general terms such as data fiduciaries instead of FIUs, data custodians instead of FIPs, and so on. And the main design principle behind our solution is to really prioritize it being a drop-in replacement to operate within the ecosystem as it exists today, rather than trying to advocate for MPC-friendly standards and so on. And pretty soon, we will have our full protocol specifications and so on online, along with a report on our pilot deployment and so on. And if you're interested in the meantime, we do have, we are consolidating some resources at this link on our website. Yeah, thanks for your attention.
Hi, so this bank statement's about a few kilobytes, yeah? And then you decrypt it in MPC, you do the ECIS and decryption, and then you've got this really cool parsing protocol, which I really liked. And you said the whole thing, I think on the previous slide, took a couple of minutes or something. Is that right?
Yeah.
A couple of minutes. So what percentage of that is the ECIS bit?
So what percentage of that is the?
It is the elliptic curve and then the threshold GCM. Is that the majority of the effort?
No, it's a small minority, like in the order of minutes, like that's on the order of seconds.
So most of it is the parsing bit.
Yeah.
Oh,
exactly.
okay.
So maybe this last question.
For the parsing, the format is XML, right? Why not just require the data source to pad it with spaces so that it lines up nicely?
Yeah, I mean, if people are willing to change things in the ecosystem for us, we could do that. And ideally, once this system gains some traction, maybe we can advocate for it. But at least the principle that we have now is that we want to work with data exactly as it comes. And it's at the moment done by banks and so on that are not very willing to change what they do.
Great. So let's thank the speaker again. And so I'm pleased to welcome Jewel, who's a PhD student, final year PhD student at MIT, co-advised by Srini Devadas and Mengja Yan. And he's also a co-founder of a startup working on AI with confidential computing.
Hi, everyone. I'm very excited to be here today to tell you about Verifiable FHE using commodity hardware. So this is joint work between with Fisher, Ed, Srini, Amar, and Guru Raj. And I need the clicker. Okay, so let's start with FHE. So I think we talked a little bit about it in the previous talk, but yeah, if you have an FHE scheme, you can take like two numbers, encrypt them using a FHE scheme, and then you can like do operation on the ciphertext. And the great thing here is that if you decrypt that ciphertext, like you will get like the resulting operation on the original number. So you can do additions, you can do multiplication, and that means that you can compute an arbitrary function like that. And so obviously there's a catch, there's significant performance overhead, so far like between 3 to 6 order of magnitude slowdown. So there's a lot of application for FHE. It can be used to build other interesting cryptographic primitive. It also has like many real world applications as we just saw. And so in this talk, we're gonna focus on FHE in the client server setup, right? So you have a client that wants to perform some like computation over some sensitive data, and they want to like outsource that computation to a server. And so the client, here the phone, is gonna encrypt its input, send it to the server, that will evaluate the FHE circuit over that encrypted data, and then send back like their encrypted results, which will be decrypted by the client. And so the problem with that setup is that there's no integrity. So another way to say it is that FHE schemes are only passively secure. So that means that if you have a malicious server here, first the server is able to like compute arbitrary circuit, which can be bad if you like use FHE in a more complex protocol where you can have like serious security implication. But to give you another example, like an attack that malicious server can do is like you can take the resulting ciphertext and like tweak it a little bit, and that potentially result in like decryption error on the client side. And if the malicious server is able to observe these errors, so for instance, like the client tries again if the decryption fails, well, that's actually enough to mount full key recovery attacks. So that's pretty bad. So how do we solve that problem? Well, the solution is to add a layer of verifiable computation, right? So verifiable computation is a primitive that allows a remote user to verify the result of a computation. So you have the remote client, the distant server, and so the client is gonna send like the circuit plus the data that it wants the server to evaluate, and in return, like the server is gonna send the result and a proof. So that sounds great, but current solutions are insufficient. So first, starting with cryptographic solutions, we have zero knowledge proofs. They're like amazing, but they have like between 5 and 6 order of magnitude overhead. And so keep in mind that this is like on top of FHE, and these overhead are multiplicative. So you get in the realm of things that like don't have a lot of like real applications. You could also do replication, but this is hard to achieve in practice. Like you need a distributed trust setup that can be like a bit difficult, and it also has like a bunch of performance limitation. So the other solution is to use trusted hardware, right? So if you can use trusted execution environment or secure enclave. I'm gonna use these two terms interchangeably in this talk. And basically, when you hear about this technology, you often hear about like the isolation part, which means that you can like really like make sure no one can see what's happening inside of a T execution, for instance. But another interesting properties of this system is that they can prove what code and which data they're actually like executing on. And this is what we call remote attestation, and I'm gonna explain it now. So remote attestation, it looks a lot like verifiable computation, as I presented earlier. But here, the hardware is gonna like create the proof of computation, right? So it leverages trusted hardware, as I just said. The hardware is gonna measure by hashing the code and the data inside of the enclave. Then the hardware is gonna create what we call an attestation report by like using this measurement. And then the hardware is gonna sign that report as an attestation proof. And so these technologies are usually based on like root of trust and chain of trust. So here I describe like, for instance, a fully like software like root of trust where you're gonna have like chain of trust, sorry, we're gonna have a root of trust that's gonna measure like the next stage of the booting like sequence, and then the firmware is gonna measure the operating system, and then the operating system is gonna measure the application, right? And there's no performance overhead beyond this fixed setup. But the problem, as you might all be familiar with, is that like any other trusted hardware, these solutions are vulnerable to microarchitectural side channels. So what are microarchitectural side channels? So if you consider two programs, a victim program and an attacker program, and these programs share some microarchitectural state, well, the attacker program might be able to use contention over that like shared state to actually like observe the victim usage of that shared resource. So for instance, for a cache side channel, the attacker is able to infer which address was accessed by the victim program. And so how bad is this attack? If you just consider them as is, like they're bad, but you can like mitigate them just in software, for instance. So take the example of like a cache side channel. As I just said, like you're leaking the addresses that the victim program is accessing. But if you write your program, like for instance, your cryptographic library using like constant time programming, like one of the rules here is that you're not gonna do a memory access which address depend on a secret, right? So we kind of know how to like contain this attack, even just in software. So the conclusion here is like keep calm, just write good code, for instance, like constant time code. But unfortunately, this attack can get way worse. So in 2018, you have like the discovery of Spectre and the rest of the logo mafia. And these attacks are called transient execution attacks. And basically, they're going to use speculation. So speculation is a microarchitectural like optimization to make sure that your processor can actually like try to guess what it should do next and go much faster. And so it's going to use this speculative mechanism to weaponize side channels. So now you don't have to be like super lucky and have like a very nice piece of code in the victim code that like does your side channel. You can just basically like speculatively jump a bit everywhere and do a lot of things you were not able to do before. And the bad news here is that this breaks isolation for all existing and known TEs. So now it's actually time to panic. Okay, and so beyond this vulnerability to side channel, existing TEs also have limitation, like they require like dedicated hardware, and in terms of availability, they're mostly available on like server grade processors. So the goal of this talk is to present a side channel resistant mechanism that makes it possible to have verifiable FHE, and I'm going to show you that we can actually do it with commodity hardware without like any special hardware in place. And so the key insight on how we're going to achieve this is by remembering that in FHE, all sensitive data is actually encrypted. So enclaves do not need to guarantee any program privacy. We can really focus on our effort on providing integrity only. And so that's how we build Argos. So Argos is an integrity-only TE for maliciously secure verifiable FHE. It can be used to build like more complex protocol based on FHE, such as like fully malicious and authenticated private serial intersection or private information retrieval. It's secure by design against any microarchitectural side channels, and it requires no specialized hardware. It's compatible with commodity processor, and it has like less than 3% performance overhead on FHE computation, and less than 8% for a complex protocol. Okay, so how do we do this? Oh, sorry, what's the catch here? So once again, Argos only provides integrity. So that's great when you're doing like encrypted computation, such as FHE or MPC, but like it's kind of limited to this use case, or at least like the other use cases are like less clear. It's obviously a weaker threat model than zero-knowledge proof. I want to insist on that. Like zero-knowledge proof are based on like strong mathematical assumption. Here we're more in the realm of like system security, right? And it requires a custom hypervisor and a custom runtime to like work efficiently, and so that's kind of also the catch. Okay, so this was the introduction. Now I'm gonna do a quick history of trust, then a quick design overview. I'm gonna show you one of the performance optimization we have, and then we're gonna talk about prototype and evaluation. So a threat model is pretty standard for a trust execution environment. We assume a strong privileged software attacker that has compromised like most of the privileged software stack. It's able to mount any type of side channels. And our assumptions are pretty standard. And for now, we'll consider out of scope physical attacks and fault injection attacks. So let's do a quick history of trust. So back to 1990s, this is very similar to like the remote attestation mechanism that I showed you. Everything is like implemented in software. We have a trusted code base, which is like the set of code that we trust to be like bug-free and correctly implemented. And so here it's pretty big, right? It includes the firmware, the operating system, and everything. And so it's a bit of an anachronism because we didn't know at the time, but the hardware also contains a bunch of side channels, and that means that any software that manipulates secrets is potentially exposing these secrets to side channel. Okay, so in 2007, we have the invention of dynamic root of trust. And so here by using like a TPM and a bunch of like hardware mechanism, we're actually able to remove the firmware from the trusted code base. So that's a nice reduction in the amount of code we need to trust. Then in 2008, with the invention of like hardware virtualization, we're actually able to isolate virtual environment between one another. And that means we can use a small hypervisor as a security monitor. And the TPM here can be virtualized in the hypervisor, which like is great for performance, as we're gonna see, but also means that we expose a bunch of secrets to side channels once again. Then you've probably heard about secure enclaves such as SGX. So here the design is a bit different, but what we need to keep in mind is that the final cryptographic step for remote attestation are still performed inside of an enclave on the CPU, and that also leaks secret through side channels. And finally, you might also have heard of like trusted VMs such as like AMD SCV or Intel TDX. And so these are also a bit different in terms of architecture, but here again, like you need to, the last step of attestation is gonna happen on the CPU in a paravisor and also like leak a bunch of important attestation secret. Okay, so that was kind of the background. What do we do from here? So one of our conditions is that we don't want any like special hardware. So we're gonna start back from hypervisor-based isolation, right? So that looks more or less like that. And now we're gonna remember the key insight of this talk, which is in FHE, all sensitive data is encrypted. And so that means that here, we actually don't have any secrets and we're not vulnerable to side channels. And that also means that the only secret that is left on the CPU is actually that final attestation key of the final step. And so a good idea would be to hide that key and keep it on like separate hardware, for instance, the TPM. So this like trusted platform module. And if we do that, that's really nice because that means we have no side channel beyond the TPM. So let me make that argument. So TPM does not share microarchitecture with the CPU, right? Like it's a separate chip that's on your motherboard or that's integrated, but basically doesn't share any microarchitectural state. Similarly, the TPM cannot run attacker arbitrary code. And the TPM microarchitecture is like intentionally extremely simple, right? So it doesn't have speculation or a bunch of things like that. And so that means that there's no shared microarchitectural state between the TPM and a potential attacker. So by definition, like the attacker cannot exploit shared microarchitectural state to actually mount a microarchitectural side channel. So the only side channel that we have left are TPM-based timing or completion time, but this is addressed by using like constant time cryptography in the TPM, and also TPM physical attacks, but we'll talk about this later. Okay, and so that's kind of the evaluation of trust here between like the beginning and like our platform. Okay, so now let's talk about like some performance optimization. So the problem with using like hardware TPM is that communication and operations are actually very expensive. So this is true for a discrete TPM, but also an integrated TPM that's like on the same SOC than your CPU. A signature, for instance, can take up to like 200 milliseconds. So that's very expensive, especially if you consider like complex interactive protocols where you want to do like one signature per message, for instance. And so the current solution for that is to use a virtual TPM. So a virtual TPM is gonna live on your CPU, and you're gonna need to attest it once using the real TPM. But once that is done, you can go much faster, everything run on the CPU, your signatures only take 1 millisecond, and you've only paid the cost of like one real TPM signature. But the problem here is that you've brought back these like orange keys back on the CPU, and you're exposing them to side channel once again. So how do we keep secrets in the TPM without having a performance overhead? And so the key here is to remember our key insight once again, which is that in FHE, all sensitive data is encrypted. So first, the first hashing step doesn't manipulate any secrets, so we can keep it on the CPU. And then what is interesting to understand is that because the inputs from the clients are encrypted, we actually don't need to establish authenticity of the code, integrity of the code before like sending the private input. So we can skip that step for now, or like delay it for later. Similarly, we, depending on the protocol, very specifically, if the client doesn't open an FHE encryption, we also don't need to verify integrity yet. So we can like remove the signature of intermediary messages. And that means that we can push all of this like measurement to a final transcript and only sign that one. And so here we're back to like only paying for like one hardware TPM signature. Okay, so now let's talk about our prototype and like some evaluation. So the really cool thing here is that we have minimal hardware requirement. We're actually compatible with most machine from 2008 onward. So we prototype on an Intel machine that we had like laying around in the lab. In terms of software, we have a bunch of building blocks. So Argos is based on a mini hypervisor from EPFL that's called Taishi. In terms of we have an operating system for resource management that is not trusted once again. And so that's gonna be like Linux plus KVM. In terms of runtime, we wrote our own custom runtime, but we're also compatible with Grameen, just as Taishi is. And in terms of FHE library, we use SEAL 4.1, and we show more complex applications, such as like private thread intersection and private information retrieval. And so putting all of that together, the TCP is between like 40 and 80,000 lines of code, which is to be compared, for instance, to Linux, which is like 28 million lines of code. So we're like definitely like a different order of magnitude. And it's pretty small considering like the size of this FHE library. Like that's most of the code here. So in terms of evaluation, unsurprisingly, Argos is like 2 to 7 order of magnitude faster than zero-knowledge proofs. We also show a 83x improvement over previous work on SGX v1. So that's mostly due to our custom runtime that we can optimize for this specific application. We also, using our custom runtime, we see that we have similar performance that commercial TEs, but with better security, as I explained here. And so for more complex protocols, we also have like very reasonable overhead. And interestingly, we have like negligible communication overhead, like under 1%. Only like this final transcript needs to be sent at the end. Okay, but I told you that physical attacks and fault injection were out of scope, but what about if we try to consider them right now? So Argos actually protects against some physical attacks. So cold boot and BIOS tampering attack are taken care of by the dynamic root of trust, so we're not adding anything here. But something interesting is that Argos also protects against physical side channels on the CPU because we don't keep any secret on the CPU once again. And so that's a big difference compared to existing trust execution environment. Argos does not protect against rowhammer or fault injection attack, but to our knowledge, like there's no published rowhammer attacks that demonstrate the capability that you would need to attack Argos, meaning like gaining hypervisor privilege on a hardware VM. And for this kind of attack, you can also, like for other fault injection attack, you can also like harden the software by adding like control flow check against this type of attacks. So nothing like completely, nothing is a death blow here. And Argos does not protect against physical attacks just side channel on the TPM. No, but as I told you earlier, TPMs are now more and more integrated on the same SOC than the CPU. And so that makes it like a lot harder to attack. And so to our knowledge, once again, there's no published attack on this like specific setup. Okay, and for the most part, you can also access like this addressed attack using constant time cryptography. So that was Argos, and we have the archive paper that's out. The paper is also going to be presented at PETS this summer, and we also have like all our code is open source on the GitHub. So if you have any questions.
We have time for one question before the break.
When you compare against verifiable FHE using SNARKs, which scheme are you comparing against when you say it's, or is it at least 5 orders of magnitude? Because there are some recent schemes in 2024 that are much less than that.
Yeah, so I'm comparing to like honest but curious FHE. So basically I take the same FHE evaluation and I evaluate like outside of Argos, basically like on like bare metal, and then I place it inside of Argos and I compare like the difference in terms of performance.
No, I meant when you're comparing it to the VHFE from SNARKs.
Yes. Oh, so that is the same, like I measure it like without any integrity, then with Argos, and then like inside of the ZK system, right? Of this proof system.
This sounds like it might be a longer discussion, yeah, so we
Yeah.
can take it offline.
The best schemes, they don't run the whole FHE and the
Yeah, absolutely. Now you have like schemes that are like more integrated and they obviously have like better performance overhead. Yes.
Great. All right, let's thank Joel and the other speakers of the session. And I guess we have a coffee break now and we're back at 3:25.
start. Right, so welcome back to the next session. The next session is in an invited talk by Yael Kalai. I think for this audience, I probably shouldn't need to introduce Yael, but let me do it anyway for those of you who don't know her. So she's a professor at MIT. You may have heard of a little thing called a ring signature. Like that would be kind of something that she gave us. In fact, she's so accomplished, she won an ACM prize for computing. For many of you in the room, what will probably the most important bit of information, he's currently program co-chair of crypto. So Yael is judging you harshly right now. So without further ado, Yael, the stage is yours. How does that, where's the, how old are they?
Thank you so much. See, does this work?
Maybe point it at the laptop.
No? Okay. So apparently you need to turn this on. Shows you how detached I am from the real world. So hi, thank you very much for inviting me. I'm super happy to be here. I have to say, so I'm going to talk to you a little bit about succinct proofs and kind of their interplay between theory and practice. And I have to say that when Martin and Nick sent me an email saying, we would like to invite you to give a talk at Real World Crypto, you know, I read this line and I was thinking to myself, like, is this a joke? And why was I thinking that? Because, you know, I kind of tend to live on the cloud, playing around with math and theoretical computer science. And of course, this conference is all about the real world. And thinking to myself, what do I have to do with the real world? Actually, I'm really trying to avoid this real world in any way I can. But actually, after reflecting on this for a bit, I'm thrilled to stand here and speak. And because I really think, while I do enjoy living in the clouds in my ideal world, I do think that this interplay between theory and practice is extremely important. And what I want to do today is tell you a little bit about my journey and kind of my own kind of interplay, how I interplay between theory and practice. And in particular, I want to tell you about my journey when kind of thinking about succinct proofs. So first, before I start, let me say, like every journey, the best part of the journey is the people who take the journey with you. So I just want to spend a second acknowledging my amazing, amazing collaborators, students, postdocs, and colleagues who made this journey kind of the best ever. Thank you. And actually, my journey started as a grad student when I learned about kind of the evolution of proofs in computer science. So let me spend like 5-10 minutes telling you a little bit about this in a nutshell, because it's just so beautiful that, you know, I would like you to know about it. So, you know, classical proofs have been studied for thousands of years, starting in ancient Greece, and it's a, you know, well-studied branch in mathematics until today. And a proof is typically, when people think about proof, they think a long kind of, you know, pages of pages, and you kind of read and verify it line by line. It's kind of a bunch of logical deductions. That's what a proof is. And that's what a proof was and still is for thousands of years. And this changed in the mid-'80s with the notion of interactive proofs, which was also kind of motivated by the concept of zero knowledge, which I'm not going to get into. But what is an interactive proof? As opposed to just kind of just pages and pages of proof, now a proof is an interactive process. It's actually a conversation between a prover and a verifier. And the verifier, crucially, tosses coins. He's probabilistic. And there's some probability of error. So the only guarantee is that a false statement, it will be, it may be accepted, but with negligible probability. So you can make this probability kind of go to zero. So practically it's zero. But there is still a slight probability that the verifier will accept a false statement. Turns out that by relaxing proofs to be probabilistic and interactive, turns out that these proofs are much more powerful. In particular, what was shown is that the time that there exists an interactive proof for any kind of statement where the verifier's runtime is essentially like the space required to do the computation. And this is kind of Shamir's celebrated result, which is known as IP equal P space. So any language in P space, there exists an interactive proof for proving it where the verifier is polynomial time. Wow. Okay. So whereas with classical proof, we can do what's called, we can do NP. With interactive proof, we can do P space, much bigger class. Wow, very powerful. Shortly after interactive proofs were introduced, multi-prover interactive proofs were introduced, also for the sake of zero knowledge, getting this time information theoretical zero knowledge. But what are multi-prover interactive proofs? So here we have two provers, okay? And we have a verifier, probabilistic verifier. The verifier sends queries, questions to these provers, gets answers. So, and importantly, it is assumed that these two provers do not interact. So these two provers are put in separate rooms, okay, with no interaction. Turns out that this proof system is extremely powerful. In particular, any proof, classical proof, can be made exponentially shorter using a two-prover interactive proof. And if you think about it, why is it so powerful? Like how can any, and by the way, this is called the celebrated MIP equals next, MIP for multi-proof interactive proof equal next. Because for polynomial time verifier, he can be verified of any statement in non-deterministic exponential time. Now, intuitively, why is it so powerful? Intuitively, it's because you can think of the two provers as kind of two different suspects. It's much harder to cheat when there's two suspects, and they're kind of in different rooms, and now they need to cheat consistently. And indeed, this interactive proofs really what they use is kind of a bunch of consistency checks to catch these cheating provers. Okay, so this is very powerful. And now listen to this. Here's the next observation, a very simple observation due to Rumpel in Sipser, is the following. Well, if the communication is so small, so if a proof of size t, now the communication, then the size of queries and answers is like log t, because it's exponentially shorter, their observation is actually, forget about the provers. Ask prover one to kind of write down the answers to each and every possible query that he could have been questioned. And he'll put all the answers to each and every possible query that he could have received from the verifier. Similarly, prover two, we don't want to interact with you, just put in the sky, like give me this long list of every possible answer that you may, for any query that you may have gotten from the verifier. And now basically, you can think of kind of all these answers as one big proof that the verifier verifies by randomly choosing kind of two cells in this proof and only reading them, the answers in these two cells. Wow. And this led to like this really celebrated and beautiful PCP theorem that actually says any proof can be converted into one that the verifier can verify by reading 3 bits. 3 bits of the proof. And he's convinced with probability 7/8. So of course, the cheating prover may be lucky, But with probability, he'll catch him with probability 7/8, and you can repeat it to amplify the soundness. I find this amazing. So this is what I learned as a grad student, and I remember thinking, wow, beautiful. So this is kind of the evolution of proofs, classical and proofs, IP, MIP, PCP. Since there's a lot more. When I was a grad student, I remember Eli Ben Sasson was a postdoc with Madhusudan, and he was studying PCPs at the time. I remember once we were sitting in the lounge at MIT, and we were talking, a bunch of us from theory and more practical people, and they started challenging Eli, who was really deep into these PCPs, telling him, we don't understand, like, what motivates you? I mean, come on, nobody's ever gonna use these things. They're so inefficient. There's no way they're ever gonna be practical. And I remember Eli kind of, you know, really trying to get out, like, struggling to give a good answer. Basically, if I remember correctly, the answer he gave was something like, oh, come on, this is so beautiful, beautiful and simple, like beautiful ideas will eventually find use, or something like that. And of course, people were like giggling and laughing, like, oh, come on, you know, there's no way, no way, no way. And as many of us know today, so now Eli is giggling, he's happy. And a couple of years ago, his company with Ale and others were evaluated to be worth $8 billion using PCP technology. So, you know, I want to emphasize that I think really beautiful ideas, I agree with Eli, tend to have, applications in practice. And what we need to do is to be able to talk about them and learn from each other in order for this to happen. And I want to say, I understand why the giggling at that time, where it came from. Because at that time, all this theory of interactive proofs, or MIP or PCP, all the work on proof systems was really with a theoretical viewpoint. And really the way we thought about it as the verifier is efficient meaning polynomial time. That, you know, for theorists, that's the definition of efficient, polynomial time. The prover, all powerful. We don't care about the runtime of the prover. What can we prove to an efficient polynomial time verifier? And even in one of the papers, we referred to the prover as a Merlin, a wizard. Like, he's all powerful. Now, of course, in the real world, there is no all powerful, as we all know. So, of course, this is theoretical work which will never be used. And let me even say, even if you look at the IP equals P space theorem, the prover there, not only it wasn't, no one cared about its runtime, it was really inefficient. If you look and try to compute the prover's runtime, you'll see it's like 2 to the space squared. So it is grossly inefficient. Now again, that wasn't the emphasis. Okay, so at that time, the emphasis was to get a polynomial time verifier. What can be proved a polynomial time verifier? So together with Shafi and Guy Rothblum, we started talking about what about a doubly efficient interactive proof? This was kind of towards the end of my PhD and also during my postdoc. But thinking about kind of making this closer to being, you know, ever have any chance of ever being used, of course you want a proof system where the verifier should be very efficient, so it should be very easy to verify the proof, but also the prover is not all powerful. So when we say doubly efficient, we mean also the prover should be somewhat efficient. And by somewhat efficient, what we want to say is that a prover can prove the correctness of a time t computation while running in time not much larger than t. Okay, so what do we mean by not much larger? Ideally, linear in t, quasi-linear in t, polynomial in t, you know, ideally as close as possible so we can actually use these things. Okay, we defined it at that point, remember, to be polynomial in t, okay, but not exponential in t. Now, do we have such a thing? How can we prove, how can we have an interactive proof where both the verifier is very efficient and also the prover is efficient? So we came up with such a interactive proof for low depth computations. And let me tell you the gist of it, because it's really, the idea is extremely simple. So here's the basic idea. Say here's a circuit. Think of it as very shallow circuit. Okay, so it's a circuit with gates, ands, ors, for example. And let's say I'm a prover, and I want to prove to you that the output is 1. Your goal is to catch me if I'm cheating. How will you catch me? You'll say the following: well, I don't believe you. Give me the value of the 2 children. And you'll check that it's consistent with the gate, with the output 1. Now, if I cheated and the output was not 1, and the 2 children are consistent with the output being 1 of these 2 children must be false. I must cheat on one of the 2 children. So now you can guess which one I cheat on. Maybe you'll guess I cheat on the left one. Okay, then ask me, give me the 2 children of the left child. I'll give you the 2 children, the value of the 2 children. You'll check consistency with the gate. And again, if I cheated, if the left child is indeed false, one of the children will be false. Guess which one. So maybe you'll guess the right is false. And we continue in this manner until we reach a leaf, an input, and the input the verifier knows. Super simple, prover extremely efficient. Everything is efficient and simple. What is the problem? The problem is, it's enough that the verifier guessed one time incorrectly and got a correct label, and now the prover can freely cheat and will be accepted. So in order for the verifier to actually catch the prover, he needs to guess each time correctly where kind of the misbehaving, where the false statement, where the false claim is. And that, he can guess with probability 2 to the minus the depth, which is extremely small. So no good. However, you can easily, maybe not that easily, but you can get around this by basically applying kind of an error correcting code to each layer of the circuit. Think of the circuit as layered. You apply an error correcting code, and what an error correcting code allows you to, what it gives you, that if there's one thing incorrect, almost everything is incorrect. That's the idea of an error correcting code. And now we do the exact same thing of kind of going from layer to layer, but on the encoding. So we say, well, if the output was false, we reduce it to a value in layer below, but not on the actual wires, but on the encoding of the wires. And we kind of go reduce wire kind of layer by layer until we reduce to a point in the error correcting code of the input. And that the verifier can check on his own. So that's really all it is. And now, of course, doing the reduction from layer to layer, because we're an error correcting code, it's not as simple. It involves what's called a sum check. But that's basically the idea of the GKR protocol. That's it. Great. So this is how, that's the interactive proof for low depth computation. Of course, kind of everything grows with the depth because we kind of go from layer to layer. There's interaction for each layer. So if it's very deep, it will result with a lot of interaction. Now, let me mention, in practice, usually when people want to do these succinct proofs, they want to do it for NP, not for a deterministic computation of low depth. So how does that relate to what we want to do today? So the idea is, it's okay, we can actually make it work for NP too. How do we make it work for NP? Well, instead of putting my input X in the leaf, I'll put the X and the witness. So I want to prove to you that X is in a language and I have a witness. We'll do the exact same thing, but now the input is X and a witness. And we do the exact same thing. But now, you know, when we said the verifier can check on its own because he knows the input, now it doesn't know the input. Because we don't send W. W is large. We don't want to send W. W is like the actual proof, the non-succinct proof. We're trying to shrink W. So the verifier doesn't know W. So what do we do? So now, verifier cannot compute it. What do we do? The idea is the prover first sends some commitment of W, and then when they do the GKR protocol, when they reach the leaf, now the prover kind of reveals this commitment. Okay, so it needs to kind of reveal a point in the error correcting code of X and W. Now, in order to do that, you cannot use any commitment. You use what's called polynomial commitments. I don't want to get to it, but I just wanted to mention that these things are used also for NP. But once you do it for NP, it becomes kind of, that's where crypto comes in. When you do the GKR for just bounded depth computation, there was no crypto. Just algebra, error correcting codes, just pure algebra, no cryptography at all. When you go for NP, now there's a commitment, there's a succinct commitment, actually a polynomial commitment, whatever that is, and now crypto comes in. So it becomes from a proof to an argument. Argument meaning computationally sound proof. Okay, so I just want to emphasize that this succinct interactive argument for NP is interactive. There's a lot of rounds of interaction, like the depth of the circuit, as I mentioned. In practice, usually people want non-interactive arguments. Okay, they want succinct non-interactive arguments known as SNARGs. How do we get non-interactive arguments? Well, it turns out that the interactive argument that I showed you, GKR, is public coin. The verifier's messages are just random, random bits. So we can apply the FHE to it. Why not? So now let's kind of talk a little bit about the FHE paradigm and ask, well, is it secure? We want to apply FHE to this GKR protocol. Is it secure? Okay. In practice, yes, it's secure. It's used all over the place. ECDSA, which is, probably one of the most useful signatures, is based on this heuristic. And we use it all the time. FHE heuristic is used all the time. Never a problem in practice. Okay, so it seems like it's secure. But is it? There was no breach, but is it secure? Can we prove security of this? So, it's used all over the place. We should have an understanding of whether it's secure or not secure. So, yeah, I was Adi's student a while ago, and, I learned about this heuristic. I thought it was beautiful, very elegant, lovely, beautiful. And I wanted to impress Adi and say, I'm going to prove that it's secure. So I worked a lot to try to prove the security of this paradigm. And after working so hard and failing, I remember coming home one day, kind of feeling down that I've been working on this thing, no progress. I remember my dad telling me, well, maybe it's time to look for a counterexample. I'm like, no way, there's no counterexample. But actually, so there's a question, do we have a proof? Can we prove that it's always secure? Sorry. And the answer is no. Actually, there are contrived counterexamples where you start with an interactive protocol that's sound. When you apply FHE, it's not sound anymore. Now, does it mean that you should worry about using it? No, these are contrived examples, okay? But it still means don't try proving the FHE is secure in general, because you won't succeed. So now, when is it secure then? So this kind of led us to believe, okay, we totally don't understand this paradigm. Because now we have a counterexample. So when is it secure, when is it not secure? So there's been a lot of work on this. And let me tell you, we know that for the GKR protocol, if you apply to the GKR protocol, we can apply it securely. Okay, again, I don't want to go into this paradigm and exactly how it's done, but let me just say, we can actually implement the FHE heuristic in a sound way, provably sound, under standard assumption, in particular the learning with error assumption, which is not today one of our favorite assumptions because it's believed, or maybe somewhat believed, to be post-quantum secure. So we do have a proof for the GKR protocol. And just let me tell you, maybe in a word, I think we have, so we do believe that this paradigm is secure when applied to proofs, not to arguments, to proofs. When applied to arguments, it's shaky. We don't have a good understanding of what's going on there. Okay? Now, here's a result that just blew my mind. I just learned about it a couple months ago in Oberwolfach. So Ron Rothblum, we had a meeting, Ron Rothblum came and presented this work saying the GKR protocol, when applied to NP, like done in practice, it's actually when if you apply Fiat-Shamir to it, it's actually insecure. So actually he's like, here is a computation where you would want to apply, to run the GKR protocol on. And no matter how you try to instantiate the Fiat-Shamir on this, it will break down. But for NP, so for an argument. So that really blew my mind. He gave a talk, it was very insightful. And I want to say one thing about, so Ron, like me, he lives in the cloud. Okay, he's theory, in theory land. However, this year, I guess in the beginning of the year, he joined the real world and he works now at Succinct. It's a blockchain company, and they implement GKR. Okay, and they hired him to do security analysis. And I think it is really kind of understanding how things are done in practice and kind of being a theorist, kind of observing, is what really led to this result. So this is kind of yet another example of how important this interplay, where theorists should come and talk to real world people, understand what's going on in the real world, to understand what's the right questions to ask. And people in the real world should try to tell us what's the right, what we should think about. And without this connection, our work as theorists becomes a bit irrelevant, and you don't get to enjoy, our fruits. So really, this interplay is, in my opinion, crucial and for the success of our field. So I want to say this kind of, in my opinion, this journey towards succinct proofs has been a real success story for theory of cryptography and cryptography at large. So as a perspective of a theorist, I can tell you we learned a lot from this process. There's been a lot of work done, a lot of connections between kind of other areas in theory. While working on this, connection to quantum physics, non-signaling, connection to hardness approximation, connections to the hardness of computing Nash equilibria, all these kind of very bizarre connections we found kind of during this journey. There's been a really nice interplay between theory and practice, where a lot of our schemes have been taken by more applied researchers and prototyped. And finally, from theory to deployment, today these things are used by various blockchain companies, Starkware being one of them, but now there's many others, most notably Ethereum, and others. I'm sure there's more I didn't write on the slide, but it's now starting to be used. And now we have kind of a joint effort with a bunch of us here called ZK Proofs. Actually, there was just a conference here in Sofia that just ended, I believe, yesterday on ZK Proof. And it's an effort to try to standardize these succinct proofs so it can be hopefully useful and easier to use in the future. Okay, thank you very much.
All right, we have time for a few questions.
Yeah, very clear talk. The one thing that wasn't clear, you said, I think, that the GKR is okay with Fiat-Shamir for LWE. What's the LWE bit there? Can you explain there a bit more detail?
Yeah. So what we managed to prove is that if you take this interactive GKR protocol and apply Fiat-Shamir heuristic, there exists a hash function, a Fiat-Shamir hash function, that if you use this specific hash function, then it's secure. And this hash function is kind of based on learning with error assumption. There's kind of a there's an LWE kind of thing. So we didn't prove that it's secure using SHA-256 or whatever people use today, but at least it's a proof of concept that if it's broken, the problem is in the hash function, because there are hash functions which are secure. I should say the hash function on which we proved security is not practical. So I'm not advocating to use that hash function, but at least it's a proof of concept that it should be secure. There are hash functions that are secure. If SHA-256 or whatever is not the right one, then dump that one and find another one. But there are hash functions for which the problem is not with the paradigm. So I guess my point is, if what we proved is if you use GKR today with Fiat Shamir and it's broken, the problem is that you use the wrong hash function. Because if you use the right hash function or a right hash function, it would be sound, unless you broke LWE. Thanks for the question, Nigel.
All right, I'm sorry we are out of time. So let's thank Yael again.
Thank you.
So now it's my pleasure to introduce the last session of the day, authentication in practice. We will go back in time and talk about some simpler cryptographic primitives before going back to succinct proofs at the end. So keep in your head what you learned in the invited speak that we just heard. So now I introduce Miro Haller, who is giving us an attack on radius.
Thank you very much for the introduction. This talk is joint work with Sharon Goldberg, Nadia Henninger, Mike Milano, Dan Shumoff, Mark Stevens, and Adam Sul. And in this talk, we're indeed going back to the time where everyone used MD5. So this talk is going to break radius. So let's start with what radius is. There we go. Okay, so you might have never heard of radius, but the infrastructure that you're depending on most likely is using radius. Radius is often hidden from the end user, but it's a de facto standard for enterprise network authentication. And as such, it's basically supported by every piece of networking gear that was produced in the last 25 years. So for example, radius is used to authenticate access to internet backbone routers. Almost all non-cable ISPs are using radius internally. Radius is also used to authenticate access to internet control systems and power grid controllers. It's also one of the supported ways of integrating with identity providers such as Okta and Duo, and to support multi-factor authentication. Radius is also used inside 802.1x, and therefore used for authenticating access to enterprise Wi-Fi or eduroam. Here is one slide summary of our work. Let's start with how radius is used to connect the user to enterprise network. So let's consider a user that wants to authenticate to a router to connect to Wi-Fi. In that case, the user sends their username and password to the router. But in most enterprise deployments, the router doesn't actually store all of the user credentials. Instead, there is a centralized authentication database. And so the router, acting as the radius client, asks the radius server whether or not it should grant this user access. And it does this by sending an access request radius message to the server. The server will then consider the authentication database and decide whether or not to give the user access by sending back a message that's called an access accept or access reject radius message. And based on that, the router then grants the user access or not. So this is really hard to believe, but radius is actually using a custom MD5-based MAC to authenticate packets, and it's also sending most of its packets over UDP, in many cases even over the public internet. The attack that I'm presenting here is called Blast Radius. It's a protocol vulnerability that allows the machine in the middle to change an access accept to an access reject, the other way around, a reject to an accept. The impact of this is that an adversary using this attack can authenticate as any user. So for example, if radius is used to authenticate access to internet backbone routers, then this allows the adversary to authenticate as administrator. Our work also helped to accelerate the ongoing efforts to deprecate radius over UDP in favor of radius over TLS. We disclosed this attack to over 90 companies, including all vendors, all big vendors of network equipment, such as Cisco and Microsoft. I hope I piqued your interest in blast radius, and in the remainder of this talk, I'm going to talk about how this attack works on a technical level, as well as how mitigations are going. So let's start with a few aspects of the radius protocol that are important for our attack. In radius, all packets start with a 4-byte header that specifies the packet length and the packet type. The access request then has a 16-byte nonce that ensures the freshness of responses. And finally, it also has attributes, including the username and the scrambled password. This scrambling, by the way, is also extremely sketchy. It uses MD5 as a block cipher with a custom cipher feedback mode in cipher feedback mode. But that's actually not the part that we're breaking. So back to the packet formats, the access accept has a response authenticator, which prevents the forgery of responses. It also has attributes. For example, it defines what kind of privileges the radius client should give the user that is authenticated. The reject has a similar structure, but usually less attributes. So as you can probably guess, the target of our attack is this response authenticator. So let's see how this is constructed. As the name suggests, the response authenticator should prevent an adversary from forging packets that are sent, for example, by the radius server. And for this, it's using a custom MD5-based construction, which is the following. To compute a response authenticator of a packet like this, we take the MD5 hash over the response header and attributes that are copied from the response, the request nonce that's copied from the access request to which this is a response to, as well as a fixed pre-configured shared secret. This shared secret is set up at the time when the radius infrastructure is set up, and it's hard-coded on both the radius client and the radius server. And this is exactly what should make it hard for an adversary to forge packets, because the adversary doesn't know the shared secret. Now, at this point, probably all of you are thinking, was MD5 maybe broken like 20 years ago? And you're right. That is exactly the case, and that was the start for our research. So let's see how the blast radius attack works. The goal of our attack is to forge an access accept without actually knowing this shared secret. And in order to be able to do that, we need to get around this response authenticator. And that's exactly where we're going to use the MD5 collisions. So basically, roughly speaking, our goal is to create an MD5 collision between a forged access accept and the predicted access reject, such that both of them produce the exact same response authenticator. So on a high level, this works as follows. The adversary logs into an account with some random bogus password, which then causes the radius client to send an access request to the radius server. But this request is intercepted by the machine in the middle, which is then using the information in the request to predict what access reject the server will send back. And it's then running a collision algorithm to compute a matching access accept that has the same response authenticator. But at this point, the adversary doesn't know what this response authenticator is. So to learn that, it modifies the request to make sure that the server sends back the access reject that is predicted. And once it gets a reject, it can just copy over the response authenticator to the accept. And this will trick the radius client into giving the adversary access to this user, although the adversary never actually knew the correct password. Now, I've been very hand-wavy about how this collision works. So let's look at this in more detail, starting with a quick refresher on the MD5 collisions. The first weaknesses were discovered in 1993. And then in 2004, the first full MD5 collision was discovered. So this is a collision between two unstructured strings of bytes that we like to call gibberish. And the adversary can compute these in seconds on a laptop, but they don't actually have a lot of control over the collision. And so that means it's pretty hard to use these type of collisions in real-world attacks. And as we all know, to get broken cryptography out of applications, we need the clicker stopped working. We need exploitable attacks that break real-world applications. Ah, there we go. There you have your meme. All right. So the next stronger attack is called an identical prefix collision, which basically gives the adversary, given a static prefix, can compute two gibberish strings G1 and G2, such that the MD5 hash of the prefix appended with the gibberish strings collides. This was famously used for the shattered attack to create two PDFs that have the same SHA-1 hash. And while this was a very expensive computation for SHA-1, this is actually not so expensive for MD5, so you can do this in seconds to minutes. The strongest type of attack is called the chosen prefix collision attack, where the adversary gets to specify two different prefixes, P1 and P2, and then can compute with the attack gibberish strings G1 and G2, such that the MD5 hash of P1 concatenated with G1 is the same as the hash of as the MD5 hash of P2 G2. And this was used in 2009 to create a rogue TLS certificate on a farm of 215 PS3 machines, and it still took over 28 hours, or it took 28 hours. So this is clearly more expensive. An interesting fact is that once we have a collision, we can also append an identical suffix to both of the MD5 inputs, and due to the Merkle-Damgard structure of MD5, this still creates a collision, given that you have the right padding. So now that we've seen that you can compute, although you can compute MD5, generic MD5 collisions within seconds, what we need for blast radius is actually the more expensive chosen prefix collision attacks. And actually we need to compute them in less than 5 minutes, and while satisfying additional constraints, but more on this later. Let's first discuss how we use those collisions to refine our understanding of the attack. So recall that the goal is to use these MD5 collisions to forge an access accept that has the same responsive indicator as a predicted access reject. So to do this, the adversary sets the header, nonce, and attributes of both the accept and the reject as the prefixes, then runs the MD5 chosen prefix collision attack to compute gibberish strings for the accept and the reject. And at this point, the prefixes and the gibberish both collide. But as we've seen before, this value still collides if you append the same suffix to both of them, which is very convenient for our attacker because the adversary actually doesn't know this shared secret that's appended, but it is the same in both cases. This is also, by the way, where the discussion of the IETF working group was focusing on protecting against length extension attacks, which they protect against with this secret suffix, but that doesn't help them against collision attacks. And so that's one of the sources for this, why this attack happened. So at this point, you in the audience might wonder if it can really be that easy to break radius with MD5 collisions. And on that, even the IETF working group, they were aware that MD5 was broken, of course, but they thought it's a testament to the design of radius that there have been back then no attacks on the radius authentication, authenticator signature, which is actually a MAC. And indeed, there are quite a few challenges to pull this attack off in the protocol, and I'm going to discuss 3 of them. The first challenge is that we must convince the server to include the reject gibberish in its response authenticator computation. And that seems a little bit impossible at first, because why would the server include some arbitrary bytes that the adversary picks in its computation? But lucky for the adversary, the standard defines something called the proxy state attribute, which is truly perfect for our attack. And this attribute is mandated by the RFC that this attribute must be returned without any modifications in the response. And so what the adversary can do is it can put the reject gibberish in a proxy state attribute in the access request, and then this attribute will be copied over to the reject. And so it will be included in the response authenticator computation. But there we run into the next problem that it's actually too expensive and too slow to compute a reject gibberish that's short enough to fit into a single proxy state attribute. And so to resolve that, we had to improve on existing chosen prefix collision attacks and to allow us to fix a 4-byte proxy state header in the middle of the gibberish string. And that allows us to spread the gibberish across multiple proxy state attributes. The last challenge that I'll talk about is that, unfortunately for the adversary, the response authenticator also includes a request nonce that's picked at random for the request. And so it can't actually pre-compute the MD5 collisions. It needs to first observe the nonce, and then it can use the prefixes. And so that adds a time constraint because the adversary needs to compute this collision before the Radius client times out, which in practice is at most 5 minutes, usually less. And so we had to optimize our computation. At the first, when we implemented this, it took multiple days to run this, and we got it down to below 5 minutes. You can obviously ask, can we go faster? Can we go below 1 minute? The answer to that is yes, we can definitely do that. That's just all we got out of our 10-year-old hardware, banging our heads against it for a while, but you can definitely go faster. Let's move on to impact and mitigations. Our attack breaks the POP-CHOP and MS-CHOP authentication modes of Radius. It doesn't affect the EAP authentication mode. And this is because that authentication mode requires an additional attribute that's an HMAC MD5. And this attribute is not vulnerable to MD5 collisions. And an interesting fact is also that Radius, the EAP TLS authentication mode, which nests the which nests EAP TLS inside the insecure Radius, is also saved by this HMAC MD5 attribute and not actually the fact that it's using TLS. And so this is not to be confused with the correct way of doing this, which is nesting Radius inside a secure TLS channel. That's called Radius over TLS. Our attack also requires machine-in-the-middle network access. And so that means if your deployment sends Radius traffic over UDP over the public internet, then you're definitely vulnerable. Now, you might ask, or you might think that no one is doing this, but it turns out that surprisingly many organizations are doing this, including most non-cable ISPs, as well as major cloud providers. Or to put it into the words of the Free Radius maintainer, Alan DeCock, lots and lots and lots of people are sending Radius over UDP traffic over the public internet. Now, if your deployment sends Radius traffic over a separate VLAN or an IPsec tunnel, then the adversary would first need to compromise that network. But once they have compromised it, they could use blast Radius to spread onto all devices that use Radius for authentication over that network. We discussed this attack to over 90 vendors. And in the long term, we suggest to wrap Radius traffic inside TLS so that we can rely on TLS for integrity and confidentiality. And there is an ongoing effort in IETF to standardize Radius over TLS and also afterwards deprecate Radius over UDP. However, in practice, this is hard to deploy. One of the reasons is that Radius is used very broadly. For example, one of the use cases is even to for remote access to windmills in power plant controllers. And so some of these implementations are really hard to upgrade, which makes backwards compatibility a major constraint. And so on the short term, in discussions with vendors, we suggest to use the message authenticator attribute that I discussed before, because that's already supported in the standard. However, this only works if you use this attribute to authenticate all requests and responses. So let's see how this is going. The good news is that all of the Radius server vendors already had patches available at the time when we went public, and by now most of the equipment vendors also upgraded their systems. However, there is some trouble, some inconsistent interpretations of where to put the message authenticator. So Juniper devices require it to be the first attribute, and Cisco devices put it at a random place in the packet. So if you upgrade both of your Juniper and Cisco devices in your network, you might find that authentication is no longer working. The correct way to do this would be to put the message authenticator as the first attribute when you send packets, but to mandate that it's present, to only mandate that it's present when you receive packets. Why is this so complicated? Well, it turns out that there's an extension to our attack that applies to partial mitigations. Basically, you can hide a message authenticator by extending our attack such that the accept gibberish ends in a proxy state header, in which case the client will parse the message authenticator as a proxy state and never actually verify it. There's more information about our attack on our website, and I'm happy to take questions now or on the hallway later. Thank you.
So there's time for one quick question.
I assume that in most cases, the accept or reject answer is obtained within less than a second. Is there any reason why you allow the system to wait 5 minutes before getting the answer? It would be very easy to put a much more reasonable upper bound, which will not stop any the actual use of the protocol.
Yes, that's a very good question. In practice, most of the applications allow an upper bound until 5 minutes, but the ones that are usually used are between 15 seconds and a minute. The reason why you sometimes want to have a minute is if you integrate it with multi-factor authentication, then you might require the user to go to their phone and click some second factor. And if you set a too low timeouts, then you break the authentication functionality for that. But yes, usually it's used for 1 minute or so, but 5 minutes is how much time we wanted to spend on optimizing our code. You could definitely get to 1 minute.
In relation to that, was the speed up from 28 hours to 5 minutes just modern hardware, or was there new cryptanalysis?
We did a bunch of trade-offs that are different from the previous chosen prefix collision attacks. Definitely all of this is in the paper, but the short summary is that we traded off more computation power by spreading the attack across multiple machines rather than one, and lower success probability for shorter latency so that our attack succeeds less but is faster and requires more compute but is faster. We also outsource or did more pre-computations and so forth. Yeah, I think the most algorithmic or cryptanalytic improvements are, for example, the inclusion of fixed bytes inside the gibberish, which is a capability that wasn't present before.
Thanks.
So thank you, Miro. Join me in thanking him again. And now I'm inviting on the stage Sylvia Meller. So Sylvia Meller is going to shake us up with authenticated encryption. Stage is yours.
Thank you for the introduction. This is a joint work with Johan Damen, Seth Hoffert, Gilles Vanache, who is also here this week, and Ronnie Vanker. So let me start by explaining the title of this talk. So what do we want to do? We want to do authenticated encryption, and I think this was the clear part of the title. Let me spend a few words on authenticated encryption. So this is a cryptographic mechanism that allows parties to provide confidentiality and integrity of their communication. And it consists of two functions. So we have the wrap function that takes as input a secret key, a nonce, associated data in plain text, and returns an encryption of the plain text, and an authentication tag that is computed on the associated data and the plain text. And then we have the unwrap functionality that takes the secret key, the associated data and nonce, ciphertext and tag, and data returns the plain text if the associated tag, the authentication tag is valid. Otherwise, it returns an error. So ideally, the ciphertext looks random for each input, and an unwrap call fails when the ciphertext and authentication tag pair is invalid. There are different famous examples of authenticated encryption schemes like AES-GCM, AES-CCM, the lightweight authenticated encryption scheme ASCON, and CHA-20 Poly 1305, and many others. So we want to do authenticated encryption, and we do it based on shake and turbo shake. And this is the shaking up part of the title. So shake is an extendable output function. It's similar to an hash function, but where the output has arbitrary length. It was standardized by NIST in the context of the SHA-3 standardization process. And it's a sponge function. So it's based on Keccak. It's a sponge that uses the Keccak-P permutation with 24 rounds. So after many years of public cryptanalysis, it became quite clear that actually 12 rounds of Keccak-P give a comfortable safety margin. And this is why TurboShake was introduced. So TurboShake is the counterpart of Shake with 12 rounds of Keccak permutation. And all the cryptanalysis that has been applied to 24 rounds also applies to the 12 rounds version, because actually all the cryptanalysis was conducted on reduced round versions. So Shake comes with the flat sponge claim, that says that Shake provides a security strength of 128 bits or 256, depending on the variant. In the KID setting, that is when the input of Shake is prefixed with the secret key, then it is possible to prove that KID Shake is indistinguishable from a random oracle. And we build on this. So why do we do this? There are different reasons. So we think that the scheme that we build has different advantages compared to existing solutions. But also relying on Keccak allows us to have so different functionalities based on the same cryptographic permutation that is advantageous when we implement it, but also because its security can be reduced to the security of Shake. And actually, so to give more details on this, I want to show you some comments that were sent to NIST in the context of their initiative to review the SHA-3 standard and the special publication on SHA-3 derived functions. In fact, while we were working on this, NIST announced this initiative, and they also announced that they were considering whether to approve SHA-3 derived functions for authenticated encryption with associated data. And as usual, NIST opened a call for comments, and now we have a look at the different comments that they received. So first of all, there was support for this initiative. So we can read here support for the plan to specify and approve additional SHA-3 derived functions, including those for authenticated encryption with associated data. And also we support NIST plan to specify SHA-3 derived function for authenticated encryption with associated data. And also I think we should standardize more flexible uses of Shake to, for instance, encrypt and authenticate. So happy to read that also other people think this can be interesting. But the comments sent to NIST also highlighted some of the limitations of current solutions. So for instance, methods such as AES-GCM are challenging and error-prone to deploy, primarily because of strict limits of encryption when using random nonces. And also, they highlighted the limited nonce length and the absence of nonce resistance for both GCM and CCM. And also comments about the fact that indeed, Keccak has enough capacity to accommodate longer nonces. But also some comments about the limit of AES modes due to the border mount. Also here we should investigate beyond border mode usages. And then other security requirements like, security properties that people would like to have, like committing security that is not guaranteed by GCM and CCM, and also resistance to the release of unverified plaintext. And there were also some indeed desired properties that cryptographers would like to see, like the support for sessions. Here again, allow sessions. And there were also comments indeed about the number of rounds of Keccak that I already said. So we have now confidence that like halving the number of rounds to 12 will still offer a reasonable security margin. And still, we suggest NIST uses the 12-round permutation, and still there is broad agreement that the number of rounds is too high by at least a factor of 2. And there were, in the end, also some comments about the fact that catch-hacking hardware is more efficient than AES. So with increased architectural support, we can expect authenticated encryption based on catch-hack to be more efficient than AES. And also, finally, this last comment I put, thanks to its degree 2 nonlinear layer, catch-hack is also easier to protect against side channel attacks. Okay, so if we want to recap these desired properties, we have long nonce and nonce resistance, beyond 2 to the 64 border bound, committing security, security against release of unverified plaintext, support for sessions, and something faster than shake. Okay, how do we do this? So we build our schemes by different layers. At the bottom layer, we have the sponge function that we instantiate with the shake and turbo shake. On top of this, we define the overwrite duplex interface. This is like the duplex, but in this case, the input block, instead of being XORed to the outer part of the state, overwrites it. And this has some implementation advantages. And then we can build our authenticated encryption schemes, and we do it by using 2 different approaches. The first approach is duplex-based, so we define a mode that we call OD wrap, and when we instantiate it with shake and turbo shake, this gives rise to these 4 possible variants. And the other approach is based on DEC functions. So first we define a DEC function on top of the override duplex. And a DEC function is a doubly extendable cryptographic KID function. That means it's a KID function where both the input and output can be arbitrarily long. And then we can build authenticated encryption schemes by using any DEC-based mode. In this presentation, we focus on DEC-BO, but there are other options. And again, we have then 4 possible schemes. So we look now at the duplex-based version. So this is what we call the shake wrap or turbo shake wrap. It's a nonce-based authenticated encryption with sessions. I spent a couple of words on sessions and what we mean with this. So we should consider that in modern application, we want to go beyond authenticated and encrypting individual messages. So we may want to authenticate long streams of messages or bidirectional communications. So in this case, we want to authenticate sequences of messages. And so we do this through incremental tags, intermediate tags. That means that the authentication tag of a message actually authenticates all the previous messages that have been sent in the same session. So this is what we do. When we merge the different layers that I show in the previous slide, this is the result. So this is one wrap call of shake wrap. So we have, we have different objects here. So of course, the secret key that goes into the outer part of the state. Then F is the catch-hack P permutation with 24 or 12 rounds. Then A1, A2, and so on are the blocks of associated data, while P1, P2, and C1, C2, and so on are blocks of plaintext and ciphertext, respectively. Then here we have these numbers. These are what we call trailer bytes. They are bytes that accumulate the domain separation bits coming from the different layers, and they allow to merge these layers together and get this nice duplex-based figure. So this is a duplex-based mode similar to sponge wrap. And indeed, you can notice that in this figure, we don't have explicitly a nonce, as we are used to see. What we do instead is that we require the first associated data of a session to be a nonce. Then we can prove that this scheme is secured by formally proving that its security follows from the PRF security of KID shake. And thanks to the collision resistance of shake, we can also prove that the scheme offers committing security. In fact, this authentication tag here is simply the hash of all the input blocks. Okay, then the second approach is based on DEC functions. This is how the scheme looks like, again, when we merge the different layers. This is a session supporting version of the SIV mode. And this is based on DECBO, which is a mode that was presented by Bakuyeti et al. At AsiaCrypt 2022. In this case, we don't have nonce requirements. And similarly to shake wrap, we can prove that this scheme is secure following the PRF security of shake, and it also offers committing security. Okay, so this table recaps the features of our schemes. So we have the security strength that follows from the PRF security of KID shake. Then shake wrap doesn't have nonce misuse resistance because we require the first AD of a session to be a nonce, while shake bow does. Then they all support sessions and they all offer committing security. The level of committing security depends on the version of shake and turbo shake. And then we compare them with some standard authenticated encryption schemes. So we have their security strength, where we can see that AES-based modes have the limit of these 64 bits due to the border bound. Except from AES GCM SIV that offers nonce misuse resistance, the other don't. And the consequences are different depending on the scheme. So they can be, so here the resistance is, let's say the no resistance is as in shake wrap, so it can leak at most the difference of plain text, while in these other cases you can recover the authentication key of the repeated nonce or of all nonces. They don't support sessions, and also, except from ASCON, they do not provide committing security. We also performed some evaluations. These are results of fully software implementations and conducted on a Raspberry Pi 4. We can see that shake wrap and shake bow outperform AES-based schemes, but again, this is fully software. So of course, if we have hardware acceleration for AES, we should expect different kind of figures. And if we look at the turbo shake versions, they are also very competitive compared to ASCON and ChaCha 20 Poly 1305. Okay, where you can find more details if you are interested, there is a preliminary version available on ePrint with this number. And the final version will appear at Euro SMP later this year. So to conclude, we define two approaches to build authenticated encryption based on shake and turbo shake, and they offer committing security and support sessions. One approach takes advantage of the performance of duplex-based modes, while the other approach has the robustness and flexibility of DEC-based modes. And as I said, we can also define schemes using other DEC-based modes, and here there are some references if you are interested. And also, once we merge all the layers, we think our schemes are really simple. Thanks for your attention. Okay, sorry. Yeah.
You have time for questions.
Sorry. On the slide that had the security strength for other schemes, yes, this one. That security strength is it expected number of attempts to break either authentication or confidentiality with the authentication being an online attack, is that right?
Yeah, sorry, I couldn't hear very well the question. Yes, thank you. Maybe it's better.
So the security strength column, is that the minimum number of bits for either an online attack against authentication or a confidentiality attack? Is that right?
It's for authentication.
Right, I see. So it's 2 to the 106, for example, for Char 20 poly 1305, it's 2 to the 106 attempts to forge a MAC. Okay.
Sorry, can you repeat?
It's 2 to the 106 attempts to forge a MAC, because that's an online attack rather than.
Yes, it's 106 bits of, yes.
Thank you.
Security.
Did I read the BO slide correctly that there was no randomization?
That is, sorry.
Did I read the BO mode slide correctly that there was no randomization within the encryption? You hashed the authentication and then you got the tag. So there's no randomization here. So it seems deterministic. What am I missing?
Yes, that indeed. Okay. We require the AD of the first session to be announced.
In the wrap one, you said that the AED has to be randomized. Is that the same true in this one?
Yeah, so yes, we still have announced. The fact is that if it repeats, what we leak is just a quality indeed of plain text.
Hi, thanks for the nice talk.
Can you make it quick?
Yeah.
Okay.
Yeah, you're using the duplex in both, right?
Sorry?
Both BO and the other one, they're using the duplex?
Yes, because at the bottom we always have duplex. It's not really the duplex, but overwrite.
So does that keep the API the same, or you mean to change the API of Shake? You can't use Shake as a black box, can you?
Yes, we can prove that the overwrite duplex is equivalent to Shake.
But
because
you can use Shake as a black box without changing the API.
What do you mean with black box?
So the same interface that Shake, if someone implemented Shake already, you can use that implementation and plug it into your scheme.
Yes, maybe it wouldn't be as efficient as implementing, because yeah, with Shake you have a sponge, so you don't have this, alternation of input and output blocks. So it's more efficient if you implement it as a duplex directly. But so we use the sponge more as for the security proof. So we can prove that this is equivalent to the sponge, and the sponge has a strong security now claim. And
so yeah, unfortunately we're out of time, but I guess you can find the speaker later at the reception. Let's thank the speaker again.
Thank you.
And for the final talk of the session, the day and before the reception, I'm inviting Zachary de Stefano. He will talk about NOPE, strengthening domain authentication with succinct proofs, circling back to the keynote previously. So thank you, Zach.
All right, thank you very much. So I'm going to talk about a fundamental question in internet security. That is, how does your browser know it's talking to the right server? Relevant to everyone here, maybe you're wondering, am I connected to a server with very practical, real-world cryptography content? Or is there a malicious server with slightly less practical cryptography content interjecting into the web page? And so the way this is solved today is via TLS, an authenticated, encrypted network communication protocol, wherein if I knew the public key of the server I wanted to talk to, I can be assured that I'm communicating with them and just with them. This is only a partial solution because it requires that I know the public key of who I want to talk to. To get around this, avoid storing thousands of public keys or millions of public keys in the browser, we have CAs. Prior to communicating with the browser, the domain owner will first convince the certificate authority that they own the domain. They will get back a certificate if they're successful. That certificate wraps the public key of the domain. It's signed by and verifiable by the public key of the certificate authority. This gets transmitted to the browser. The browser is able to verify this and gets trust in the key, and TLS proceeds. This is what I've depicted here, unauthenticated domain validation. But I've already lied to you. Picture looks a little bit more like this. There are many, many, many CAs, all of them trusted by the browser. And all it takes is a compromise in a single one of them for some other malicious server to get a certificate and masquerade as the domain of interest. This isn't just a theoretical setup or theoretical attack. This has happened over and over and over, both by nation-state attackers and by random hackers in their basement. So other people have thought about how can we improve this state of affairs. There are all sorts of solutions, but all of the solutions out there require modifying infrastructure in some way. When I say infrastructure, I'm talking specifically about the certificate authorities and the broader certificate ecosystem. There are all sorts of nice features that come with certificate authorities that we'd like to preserve in any new system. So we asked the question, can we improve security without changing infrastructure? Our reply is, nope. Name ownership proved efficiently. So, because I had to submit my slides as a PDF, this is a demo that you can follow along on your computer, and I have screenshots here. If you go to nopetools.org, you'll connect to it. You can look, you see the connection is secure. Certificate issued by Let's Encrypt is valid. Inside that certificate, if you look very closely, there's a succinct proof. This is a succinct proof proving that the person you're talking to, well, the person who requested the certificate, is in fact the legitimate owner of the domain. This is in a real live certificate. This is accepted by browsers. This is fully backwards compatible. You might be wondering, what does this proof exactly say? To do that, we have to look at a different public key infrastructure, DNSSEC. Now hold up. If you've heard of anything about DNSSEC before, you've probably heard there are all sorts of objections here, all sorts of problems with DNSSEC, both historical and contemporary. Lucky for us, our system gets around every single one of these common objections. So you could think of our system as almost a proper way of using DNSSEC in this context. High-level idea of DNSSEC is that it's a public key infrastructure implemented on top of the DNS hierarchy. There's a well-known root of trust public key. That's the root. This then signs keys for various top-level domains. These will sign keys for their subdomains, and on and on. And you could verify this hierarchy of keys. A first attempt at building NOPE would be say, well, let's just stick the whole DNSSEC chain inside the certificate. Surely this would work. Unfortunately, CAs aren't going to let us submit lots and lots of extra little bits of data into the certificate. The DNSSEC chain is simply too large to fit. So we need succinctness. This is where we come with the idea, let's prove the existence of the chain, exploiting the setup of succinct proofs with a prover and a verifier. Here the domain owner takes on the role of the prover, and the verifier is the browser. And we're using the certificate as a method of transporting this proof in a way that's familiar to the browser. Now, despite all the hype around succinct proofs, they are very expensive. The nice thing is that the actual proof computation happens offline, happens infrequently, but still we would like for this to at least be tractable. And so we try and make this more efficient. Give you a sense of what those optimizations would look like. Let's break open the prover and see why it's expensive. At a high level, when you want to take a computation and prove something about it, you need to convert it into a long list of arithmetic low-degree constraints, and then you get an execution, so running the program produces the values that satisfy these constraints. Both of these get plugged into some somewhat magical cryptographic machinery. And if the execution satisfies the constraints, you get out a proof. The costs here scale with the number of constraints. And each constraint is adding quite a lot of clock cycles here. Of course, all of the nice things that we have in real-world programs aren't single constraints. They're many, many, many constraints. And I'm going to illustrate what this blow-up looks like with an 8-bit XOR. On any machine today, this is 1 clock cycle to execute. It's also over 4 million clock cycles to prove. And so it becomes very, very important to optimize down the constraint representation of the computation of interest. In this case, DNSSEC verification. There we go. So DNSSEC verification consists of parsing this legacy format, these DNS records. It also involves verifying all sorts of digital signatures. So hash functions, there's large integer arithmetic there, potentially elliptic curve operations. This is very, very, very expensive. In our work, we introduce a variety of optimizations. I believe this has stopped working. There we go. We've introduced a variety of optimizations that make this problem tractable. So you might be wondering, what exactly did we implement and how performant is this system actually? Okay, perfect. So we implemented this in 2 pieces. On the server side, we have a NOPE server application, takes in the public key server of interest. It then collects the DNSSEC chain. This is a real DNSSEC chain here depicted. That then gets compressed down into a succinct proof, which is encoded in a subdomain of the domain of interest. We do that so that it can be smuggled in to our certificate request and ultimately into the certificate. Certificate authority is oblivious to this. It returns us a certificate with this proof included. I've highlighted this proof in blue here. And then the server can then use this with whatever server application it's running, just in place of its normal certificate. If the browser is unupgraded and doesn't know to expect a proof, it simply verifies this certificate as normal. This is fully backwards compatible. However, if the browser has our NOPE client installed, it will detect the proof in the certificate, parse it out, verify it, and provide additional assurance to the browser. Now you might be wondering, I talked a little bit about optimizations. What does the performance actually look like here? The proofs themselves are succinct, so we expect this is a marginal increase in bandwidth. I talked about the prover time potentially being expensive, but with our optimizations, it's incredibly reasonable. If we're looking at the verification time, the picture is slightly different. We see that in the status quo, certificate chain verification is very, very, very efficient in the browser. However, the proof verification is not quite as efficient. Still somewhat fast, but not as efficient. However, we note that natively, it can be made much, much more efficient, which suggests that if the browser was to include native code for cryptographic verification, the components that we need for succinct proof verification, in the same way that it does various primitives for signature verification, certificate verification, we would see that this is incredibly practical. Now, this work sits at the intersection of all sorts of related fields. There's domain authentication. There are a whole wide variety of works trying to solve this or improve this from different angles. We will note that our work is compatible with most of the other incremental works that improve the broader ecosystem. And so we benefit from any improvements to the certificate ecosystem. This is also in the vein of other applications where people want to take real world programs, find efficient constraint representations, and then ultimately produce some sort of succinct proofs from those. And there's a very, very new field on succinct proofs for networking. Within this field, I specifically want to mention Cinderella as a paper of interest. This was about 10 years ago, and they were interested in taking the entire certificate chain and producing a proof of its existence. And so in some ways, our work can be seen as a spiritual successor or most closely linked to this other work. If I'm going to leave you with a few things here, one is that we can enhance internet security right now without making any breaking changes to infrastructure. And the thing that allows us to do that precisely is succinct proofs, these incredibly powerful proofs that we have, and they allow us to connect interfaces that normally wouldn't talk to each other. In this case, connecting DNSSEC to the certificate infrastructure. As future work, we'd like to see Note potentially deployed natively in browsers to get that extra performance boost as well as to get it to more clients. And we're interested in proofs of DNSSEC chains beyond just server authentication. And with that, happy to take any questions.
We have lots of time for questions.
Thank you.
Thank you for the talk. So you're essentially offloading a lot of the trust to DNSSEC, right?
Yeah.
And I was wondering, if we're trusting DNSSEC anyway, why don't we just add a TXT record with the hash of your certificate instead of including a proof of the DNS chain in the certificate?
Yeah, so there are proposals that suggest what you're suggesting in various different ways, where why don't we just use DNSSEC itself? And there are two answers here. One of them is that DNSSEC has various problems, one of them being availability. And so clients trying to access DNSSEC records don't really have a reliable way right now of accessing it. The other answer is that our security, if you imagine that there are some attackers who can attack the CA system, some attackers who can attack DNSSEC, by combining the two together, you need an attacker who's able to compromise both. And so the security of our system is at least on par with either, but in some cases strictly stronger than both. And in the paper that we've written, we do a full security analysis and show that if you specify attackers in specific ways, this is actually strictly better in that case. I will say also DNSSEC doesn't have all the nice certificate infrastructure. So things like revocation or these lists or logs that allow a domain owner to see when someone's issued a new certificate, you don't get any of that in DNSSEC. And so part of it is compatibility with infrastructure.
Yeah. Okay. Thank you. Yep. But then you also don't get any security from that side, right?
Right.
Thanks.
I just have a technical question. How many constraints in total, if you had represented it as equations, and what proof system you use? Does it use trusted setup?
So for the first question, it was, I believe, between 1 and 2 million constraints. We do use a proof system with a trusted setup. You can instantiate this without a trusted. You can instantiate this with a variety of different proof systems. We chose Route 16. And we pointed out that DNSSEC itself has a trusted setup, that you can go in person, I think every 6 months, or watch online. It's about a 5-hour ceremony. And so it was natural for us to say, we're not introducing a new trusted assumption that there is a trusted setup in this case. But again, there is space for a transparent solution here.
Okay, thanks.
Good. Thanks for the wonderful talk. This was really, really fun. Very, very cool. I have a more boring technical question is where do you stick the proof in the certificate signing request? Which field?
So it's a subject alternate name.
Okay.
As a short historical digression, if we were doing this project about a decade ago, you used to be able to include logos in this request, in which case this work would have been trivial. But there are all sorts of security vulnerabilities, it turns out, if you allow people to include logos in certificates. And so since we need to encode this as a subdomain, then we need the succinctness, and all this comes out of that.
How long do subdomains, how long can SANs be?
So the subdomain itself is, I think, 253 characters, pulled from a limited subset of 37 characters. Each little subdomain needs to be delimited by dots, and they have limited length as well. There are all sorts of requirements. Each individual subdomain can't be led by a certain character. When you break all this out, it turns out that even with all those restrictions, we only need to overflow into a second subdomain occasionally.
Okay.
So I have a question related to the first question. Why not using TLSA records, which can also endorse a certificate? And specifically, how do you deal with the freshness of all the chain of signatures on the DNSSEC front? Arguably, you don't get revocation, but you get short-lived DNSSEC signature, which is a reasonable counterpart.
Yeah, so you don't get revocation, all these other nice features, but I will note that some certificate authorities, I think Let's Encrypt very recently announced that they're moving to short-lived certificates. The other thing the proof allows you to do is the proof could technically allow you to specify some sort of short-livedness and get that. We talk more about that in the paper.
Thanks. Thank you for the talk. I had a question related to the earlier SAN question. And so, as you mentioned, you smuggle this proof via a SAN. How do you handle the case where certificates have multiple SANs? Is that handled in your scheme?
So yeah, we have identifiers that allow for the extension to figure out which SANs the proof is coming across. Even if the certificate authority is reordering SANs, it's still able to parse out the ordering. It's a sort of a somewhat basic identifier scheme, but they end up being pretty easy to identify in practice.
Great, thank you.
You're using Grot16 with non-native arithmetic, I think. Have you considered, and you say that 96% of TLDs use P256. Have you considered constructing a curve that would have a native field suitable for P256? And what happens in the case? So how do you handle chains of different lengths? Or do you just choose the circuit size so that it will handle the maximum possible length?
So I'll answer your last question first, is we have actually various different circuits, and then the proof is specified, I guess in the proof encoding, we have a couple bytes that specify which circuit picks from. We did think about other proof systems. We were really interested in succinctness here, and we ended up not needing, but using zero knowledge as a prover optimization. And so Grot16 ended up being the natural choice in that these other systems might have larger proofs or they don't have the same sort of desirable features. But I do think that this space could be explored a lot more, and there's, depending on the needs of the system, there are different proof systems that could be chosen that are potentially more efficient.
Pretty sure you can do it in less than 2 million constraints.
Yes.
So last question.
Okay. Last I checked, the Grot16 was like elliptic curve stuff. So do you have a post-quantum story for this?
So the post-quantum story for this is that there are various post-quantum succinct proofs that are being developed. They're certainly larger right now, but the post-quantum keys and signatures themselves are larger. And so proportionally, when you look at that in real-world certificates, it's certainly possible to include those.
Thanks.
Thank you.
So join me in thanking the speaker again.
Thank you.
Just a short announcement. So first, I wanted to let you know that tomorrow evening, after the conference here, Kenny Patterson is giving a talk at the INSAIT Institute. And since I heard there are people interested in this, you can register to attend at the insight.ai. You can just Google, or you can search for the institute. Space is limited, so if you want to attend, please do register. And apart from that, now we will have the reception, which is just outside here of the doors. Around 5:40, there will be a short musical and dance performance. So if you want to see that, please stay on this floor. It will be on this floor. Yeah. Well, thanks everyone and enjoy the reception.